welcome to our Deep Learning full course by Simplilearn. Have you ever wondered how Instagram knows which filters you like, or how Netflix recommends the next movie you can't wait to watch? That's the power of deep learning. Now, deep learning is what allows computer to recognize patterns, make decisions, and even understand images, text, and speech. It's everywhere today, and the demand for deep learning experts is exploding, with industries relying on this technology to create smarter systems from e-commerce to healthcare. But don't worry, if this sounds complicated, we are going to break it all down in this video, step by step. So whether you're just starting out or looking to level up, this video is designed to help you understand deep learning in fun and simple way. We'll start with what deep learning is and clear up the difference between ML, DL, and AI. Then we'll dive into neural networks, walk you through hands-on tutorial, and cover deep learning with Python as well as TensorFlow. We'll also explain you math basics, explore RNNs and CNNs, and show you how to use Hugging Face. Lastly, we will prepare you for deep learning interview questions. And by the end, you'll be ready to jump into deep learning. Now, just a quick information, guys, if you're interested in growing your career in AI and machine learning, then this course is a great way to start. The Professional Certificate in AI and Machine Learning by Simplilearn, Purdue University Online, and IBM will help you master key AI skills like ChatGPT, LLMs, deep learning, and agentic AI through live and hands-on projects. In just 6 months, you'll work on real-world industry projects, work on popular tools like Python, TensorFlow, and earn certificate from Purdue and IBM. So what are you waiting for? Hurry up and enroll now, and you can find the link below.
Welcome to Deep Learning Tutorial. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified. Get ahead. What's in it for you? We're going to go over applications of deep learning. What is deep learning? Why is deep learning important? What are neural networks? The activation function in our neural network, the cost function that comes in for processing our neural networks, how do neural networks work, deep learning platforms, and then we'll do introduction to TensorFlow and a use case implementation using TensorFlow so you can see how it works and get some hands-on. So start off with the applications of deep learning. Deep learning helps us make predictions about the rain, earthquakes, tsunamis, etc., allowing us to take the required precautions. With deep learning, machines can comprehend speech and provide the required output. Deep learning enables a machine to recognize people and objects in the images fed to it. And with deep learning, advertisers can leverage data to perform real-time bidding and targeted display advertising. And these are just a small sample of the myriad of different uses for deep learning today. So what is deep learning? Deep learning is a subfield of machine learning that deals with algorithms inspired by the structure and function of the brain. When we look at this, we have the larger category, which is artificial intelligence, very generic, comprehensive ideal. And in there we have machine learning, and then a subcategory of machine learning is deep learning. So when we talk about artificial intelligence, this is the ability of a machine to imitate intelligent human behavior. So when we look at something, can it solve a problem the way humans do? Can we take it to that next level? So it's just not repeating some kind of simple output that we programmed it to do. Can it actually start imitating human intelligence? When we look at machine learning, we have the application of AI that allows a system to automatically learn and improve from experience. So machine learning, the most basic machine learning, is your linear regression model. You put a bunch of dots on the graph and you draw a line through them, and you have a guess of what X and Y are based on what X is, you can guess what Y is. And finally, we have our deep learning. Application of machine learning that uses complex algorithms and deep neural nets to train a model. Why is deep learning important? It works with unstructured data. Machine learning works only with large sets of structured and semi-structured data, while deep learning can work with both structured and unstructured data. Handles complex operations. Deep learning algorithms can perform complex operations easily, while machine learning algorithms cannot. Feature extraction. Machine learning algorithms use labeled sample data to extract patterns, while deep learning accepts large volumes of data as input analyze the input to extract features out of an object. Achieve best performance. Performance of machine learning algorithms decreases as the amount of data increases. So to maintain the performance of the model, we need deep learning. And this is always a challenge of when do you go from machine learning, doing linear regression or other regression models, to deep learning neural networks. It really centers around both the complexity as it becomes more and more complex, or the problem becomes harder to solve, along with the amount of data. So both of those play a huge part in deciding which would best serve your purposes to predict what your data is going to do and try to predict the outcome. So what are neural networks? With deep learning, a machine can be trained to identify various shapes. So here we have a square coming in. You can see we've broken it up into the pixels, and we want the label to come out square. And if we turn the square slightly sideways, it's still a square. And we want it to still say it's a square. With deep learning, a machine can be trained to identify various shapes, or the different patterns of those shapes as they are, in this case, being rotated. But how is the machine able to do this? So we'll look at a nice grid, 28 by 28, 784 pixels. And when we look at that grid, we can look at each one of those pixels as inputs. So a neural network is a system modeled on the human brain. And so we have all our inputs, kind of like your eyeball coming in there. It has the sensors in the back, your different input sensors, which are your cones and rods. So each one of those is an input coming in with information. And it goes into a neuron, and then it sends out a pulse. So the data is fed as an input to the neuron. The neuron processes the information provided as an input. The information is transferred over weighted channels. And this is very central to our neural network. Each one of those pulses coming in gets a different weight. And the output is the final value predicted by the artificial neuron. In this image, we're only looking at one neuron. So remember, we're talking about a lot of neurons working together. And we'll look at how those fit together in just a moment. When we look at one neuron, so let's just take a look at that one neuron. Let's dig a little deeper so we can get some concepts in here so we can understand the neural network. So what exactly happens within a neuron? We have an activation function. So within each neuron, the following operations are performed. The product of each input and the weight of the channel it's passed over is found. Sum of the weighted products is computed. This is called the weighted sum. And a bias unique to the neuron is added to the weighted sum. And you can always look at that as if you have an XY graph, where's your y-intercept? You know, the old Euclidean geometry, x or y equals 3x plus 5. That's your plus 5 is that bias, is where does that come in. And this is a little bit more complicated because it's not like 3x, it's more like 3x1, 5x2, 6x7, and usually you're dealing with float numbers. So it doesn't even look like that. It looks like 0.001 times x1, 0.13 times x2, and so on. So the numbers get a little confusing, but the concept is very straightforward. We're going to multiply the weight times the value coming in, and we're going to add that all together plus the bias. And the final sum is then subjected to the particular function known as the activation function. And the most simplest one is if it's greater than 0, it's 1. If it's less than 0, it's 0. They usually use there's a lot of other functions that are more reliable than that one. But that one gives you the most basic understanding of what you're looking at. 0 or 1 coming out. In most cases, you actually have a value coming out. And in some cases, we use like a tangent wave so that there can be a value between 0 and 1, but it might be, it tends to shoot right up to 1 rather quickly. But those are things you can fine tune in your neural network as you start getting to the solution. Let's keep into the generals here and let's see what's the next step. We're going to look at the cost function. And this is so important in understanding how the current neural networks that we're working with are able to learn things. So we end up with the cost value. The cost value is the difference between the neural net's predicted output and the actual output from a set of labeled training data. The least cost value is obtained by making adjustments to the weights and biases iteratively throughout the training process. And when you think about this, we're not just sending one set of numbers through, we're sending all kinds of data in here. So you might have 100 samples or 1,000 samples, and each one of those samples comes in, and then we look at the cost for that. and we want to get that cost the average minimal among all the different samples. So we want a general answer on there. You can see here we denote the predicted output with a little half triangle over it, and then the actual output is just a straight Y on this. Let's learn how neural networks work. Let's dig in a little deeper in how we program them. How do neural networks work exactly? In this, we're jumping from a single node into a larger picture. So our neural network will be trained to identify shapes. And we'll start with the square again, 28 by 28 or 784 pixels. And this is kind of one of the standard images we work with a lot of times. Our shapes are images of 28 by 28 pixels. Each pixel is fed as an input to the neurons in the first layer. So here we have our input layer. Each one of those, we might flatten that out. That's the most easiest way to process that, but not the only way to process. So we flatten it out so it's just one long array. And then we have hidden layers that improve the accuracy of the output. And you can see here we're not looking at just one neuron. We actually have a row, two hidden layers, and each layer is a row of neurons. And data is passed on from layer to layer over weighted channels. Each one of those inputs is then weighted to each of the next neurons in the next layer, in the hidden layer. Each neuron in the first hidden layer takes a subset of the inputs and processes it. Let's look into what happens within the neurons. So here we have step 1, and we can see in here where we have x1 times weight 1, x2 times weight 2 plus b1. That's that top neuron up there. And then we have the next neuron down, which is step 2. And then in step 2, they denote with the Greek symbol phi, and phi is the activation function based on step 1. So it might be if it's close to 0, it's 0. If it's close to 1, it's 1, and it might be a value in between. It's very common, depending on what activation function you use. The results of the activation function determine which neurons will be activated in the following layer. So you can see here we have B1, that's what we looked at with x1 and weighted 1, x2 and weighted 2, and then you would compute B2 the same way, and B3 the same way, and B4 and B5 and so on. So each neuron has an input from all the input layers go into each of the hidden layer neuron, the first hidden layer. The result of the activation function determines which neurons will be activated in the following layer, and then that activation number goes off to the next layer. So we see here B11, B12, B13, and B14, and the weights coming in from B1. So let's say B1 fires and it goes into B11. Usually you would see the weights going all the way down. So B2 would have their weights going into B1, and B2 would then go into B11. B1, B2, B3, and B4 and B5 would then go into B11, and they would have their weights depending on what came out. It might just be 0, so there's nothing coming through, or it might be a value between 0 and 1, and so forth for B12, B13, B14, and B15. And then we take those, and they'll have the weights attached to each one of those coming out, and they go into the final layer. In this case, we have a neuron that represents a square, a neuron that represents a circle, and a neuron that represents a triangle. And just as before, the information reaching this layer is processed, after which a single neuron in the output layer gets activated. But our input was a square. What went wrong here? Remember, we started with a square. What do we have coming out? It said a circle. Well, that's going to be a problem because we don't want it to tell us that squares are circles. Well, our network needs to be trained first. How do we train a network? The predicted output is compared against the actual output by calculating the cost function. Remember our cost function at the end? We take whatever we said it was going to be and what it actually is, and we just subtract those two. And the most common way used to generate the cost function is as follows. We're going to take the actual value minus the predicted value, where you have y, and then you have y with the half triangle over it is the predicted, and then y is the actual value. We subtract them, we square that value, and then we divide it by 2. So that's usually how they generate the cost function. The cost function determines the error in prediction and reports it back to the neural network. So we're going to do some backpropagation. That's what this is called, backpropagation. We're going back through the network the other way, and we're sending that error back the other way. The weights are adjusted in order to reduce error. The network is trained with the new weights, and you can see here we have c equals 1/2 y minus y predicted, or y actual minus y predicted squared. Once again, the cost is determined and backpropagation is continued until the cost cannot be reduced any further. Now, keep in mind, if we have one picture of a square and it goes through, we actually do just a little training. We don't change it all to match that first one. Otherwise, you'll have what they call a bias. So each of those data goes back with our back propagation, and we'll send hundreds of samples on there until we can get that cost as a whole down as low as we can get, so that our average cost is very low without it being biased towards one specific figure. And you can see here we have our input layer, hidden layer, and our setup on here. Similarly, once we've trained it for our square, the network must also be trained to identify circles and triangles too. So we need sets of all of these. We need lots of squares, lots of circles, and lots of triangles. The weights are this further adjusted in order to predict the 3 shapes with the highest accuracy. We can now rely on our neural network to predict the input shapes. And you can see we have a triangle coming in here, and it goes through. Here's our circle going through, and it's going to light up the circle, and so on for the square. So before we dive into some hands-on, let's take a look at some deep learning platforms. The primary programming language, we're going to look at 4 of these platforms, and we're going to start with Torch. The primary programming language is Lua with an implementation in C2. Torch's Python implementation is called PyTorch. And this is interesting because Python has become one of the leads in data analysis. So you'll almost always see a PyTorch or any one of these will have a Python equivalent, and that's slowly spreading throughout the languages. So I'm sure there's within Torch, it's also probably got a Java set up, and definitely has a C because its primary implementation is in C. And so we have Keras. Keras is a Python framework for deep learning, and USP is reusability of code for the CPU and GPU processing. We have TensorFlow. TensorFlow is deep learning platform by Google. It was developed in C++ and has its implementation in Python. And just a quick highlight, Keras and TensorFlow have slowly been working together. So there's a lot of things that you can actually put Keras on top of TensorFlow and access TensorFlow. Although there are still some tools in TensorFlow that Keras doesn't fully access. But it is a great interface for doing that. And then there's the DL4J. It is the first deep learning library written for Java and Scala. It is integrated with Hadoop and Apache Spark. And you remember Apache Spark is written in Scala. That's one of the reasons the DL4J came about, is so that it would run on the Spark platform. So let's take an introduction to TensorFlow. Google's TensorFlow is currently the most popular deep learning library in the world. It has really, once they open sourced it, it was just amazing how much it spread in use and how many tools are linked into TensorFlow. Tensors are vectors or matrices of n dimensions. And you can see here we have dimension 5, we have a dimension 4 by 5, or 5 by 4 as the case is, 5 rows by 4 columns. Here's one where it's 3 by 3 by 3. And so this is kind of nice because when you're processing pictures, there's certain things you want to do where you want the pixels to be next to each other. That's very important. Same thing if you're processing, say, a movie. You might want a 3 by 3 grid coming in where you have the layers of the frames coming in to be processed. So you can see how having different dimensions is really helpful in analyzing certain data structures. And this is what's so great about tensors, is you can, of course, flatten them out like we did earlier, or you can process them based on their location. In TensorFlow, all computations performed involve tensors. So everything going through is always looked at as tensors, as a matrix, or matrices of n dimension. TensorFlow architecture is as follows. Pre-processing data, build a model, train and estimate the model. And what we'll do is we'll go ahead and dig into use case implementation with TensorFlow. To do that, I'm actually going to go into, in this case, I'll be using the Anaconda Navigator. And you can use either Jupyter Lab or Jupyter Notebook. Most people are very familiar with Jupyter Notebook. It's very commonly web-based. The Jupyter Lab is the next version of Jupyter Notebook, and it just lets you have multiple tabs open when you're working on it. And if you're using Anaconda, you'll go under Environments, and you'll want to make sure that you have your TensorFlow installed. And you can simply, we'll do this, I have it installed, but you could do all, we'll do all. You can do a search under all for tensor, and you can see all the different tensors. It's actually installed in here, version 1.13.1. If it wasn't, you could check the box and then run the install on there and it'd bring it right in. But we'll go ahead and start up our Jupyter Lab, which is going to open up, in this case I use Google Chrome. And in our Jupyter Lab or Jupyter Notebook, if you're in the notebook, you only have one tab and you won't have the added options, like there's a folder and different things you can do in the lab that you can't do in the notebook. But everything we're going to do, you can easily do in the notebook. And you'll start up a new project. Deep learning is what I'm going to call this. And if you're not familiar, you can we have some tutorials out on the use of Jupyter Notebook and how to run it and set it up and things like that. The most basic is we put our code in here. It has a nice display, a nice interface, especially for data science. I can display all kinds of things on this page, and then you can just run this page right here. There's no code in it, so it's not going to show any thing until I put some code in there. And of course you can cut your cells and things like that. So the first thing we want to do is we want to import our tools. Now if you haven't, remember you got to install TensorFlow, and we'll also use Pandas. Pandas is a nice database setup. And that again is underneath your environment, and you can see here your whatever you're working on, my Simplilearn setup, where I've installed TensorFlow and Pandas in here. And I'll simply go up here and run this. I'm not going to see anything, so we've just imported those into our notebook that we're working on. So those are now available to us. And it helps to have some data to work with. And we have here, I'm going to create a path and a test path. And we'll go ahead and let's just highlight this whole path. And you can always post a note either down below in the YouTube video, or you can post a note on Simplilearn.com and ask for this path if you're not quite picking it up. But it is over here at the UCI EDU on their setup, and it's in their archive. So it's archive.ics.uci.edu/ML for machine learning /machine-learning-databases/adult. That's quite a mouthful. And in this case we have adult data and adult test. But let's go ahead and just take a look at that. Let me just paste that right in there to our browser window. And here's our adult data, and if I click on there it's going to come down as a download. I'm going to go ahead and open it as a text in my notepad. And the guys in the back were kind enough to look up to find out what the actual columns were in this coming across. So let me go ahead and take that to pull that information. And it doesn't matter whether I put it before or below because these are just variables. But we can see here that we have age, work class, final WGT. I'm guessing that's final. We'll look that up in just a second to see what that matches. In fact, let's pull that up and just put them next to each other so we can kind of see what we got here. So we have age, we have our working class, state gov, maybe final wage, 77,516, education of bachelor's, education number 13, marital, never married, admin, clerical, relationship not in family, so on and so on. So it goes all the way across here. And so we've pulled out this information, native country, label, etc. We'll go ahead and run this. And so now we've loaded all our different paths. And this path, by the way, this is the same columns on here, so I don't need to create a separate columns on the adult test. And once we've run this, we've set those variables. Let's go ahead and pull that data in. And to do that, we'll use Pandas. And we'll create a df train, a df test. Each one's going to have our PD for pandas.readcsv. It'll have our path we put in there, our path test. The first one we went ahead and skip initial space, true, names columns. There's our columns in there. Index column equals false. There's no index column. On the second one, if we went back into here and we open up adult test, let me just go ahead and open that up, pad. You'll see there's an actual row up here we want to skip. 1x3 cross validator with all the same data in it. So we're looking at the same data in there, and here we're going to go ahead and bring in our data. And then once you bring it in, it's always nice to see what kind of shape your data is in. And of course, when we talk about shape, we're talking about how many rows and columns, not whether it's been lifting weights. We can see here we have, each one has 15 columns, and that goes with our columns right here. If we counted them, there's going to be 15. And the first data set has 32,561 rows, where the second one has 16,281 rows. And it's also good to see just how the data came in, so we'll use the Pandas D types. We'll run that. And you can see here where age came in as an integer 64, working class as an object, which makes sense. And then we have our FNLWGT, the education as objects, or, well, this is an integer object, so on, all the way down. And if we flash back to the data, we look at the last column, it's less than or equal to 50K. And if we scroll down enough, we'll see it's also greater than or equal to 50K. So we'd like to kind of give that its own special setup on that label. So on that feature, we're going to set the label equal to, if it's less than or equal to 50K, it's going to be 0. And if it's greater than or equal to 50K, it's going to be 1. So it's one or the other. That's always an easy thing to read. And then we can take this and we can go dftrain.label equals label item for item in dftrain label. And this just loops through all the labels. There's a lot of ways we can do this. pandas, this might be actually kind of a slower way. There's a way to do just that setup and do the logic within the setup instead of doing a loop. But for this thing, it'll work fine. We're not dealing with a lot of data. It's a large data set, but it's not that big of a data set as data goes. And we also want to do it for our test data. I didn't really mention that we created we're looking at two different data sets. One, we're going to train the data, and then we're going to take it and run the test data to see if it works. So we have our two different data sets, and we didn't catch it off the bat. If you were pulling up this, you're going to pull up one, this is the training set. And if we go back in here and open up the test set, let me just go back and do that, adult test. One of the things that we didn't notice that you'll want to pull up is at the end there's a period. So we're pre-processing our data. We want to make sure that we include that period in every line on the second setup. So when I go back to my Jupyter Notebook, I've got to have a label T, which is less than or equal to 50K period, or greater than or equal to 50K period for 1. Otherwise, it's doing the exact same thing. We're going to change the DF train label and the DF test label to 0 or 1. We'll just run that. We'll go ahead and print the DF train label value counts and the DF test label value counts. And this is always a good idea because we want to know, is there any weird stuff going on there? If there's null values, stuff like that, this will turn up on that setup. And we can see here we have zeros, how many ones, and so on there. Just a quick view of the data that we're going through. And if we go back up here, go ahead and print the train D types again. And we run that. You could actually run it up there and it'd give you the new answer because this loaded this information. We now see it's an integer. And if you go back up here, it was an object. So that makes life a little easier as far as what we're doing with this. Now at this point, we're going to look at the data and we can see we have a lot of numbers and we have a lot of categories in here. So categories would be United States, male, never married versus 7. And we can also see that when we looked at this, we have our integers, we have our objects, working class. So the next thing we want to do on there is we want to go ahead and take that where we have integers and the objects, and we want to bring that down here. We want to create those categories in a way that the computer can see them. And we'll start with our continuous features like age. We can see age integer, FNLWGT is an integer, capital gain is an integer, educational number, there's our educational number as an integer, and so on. So if we're going to have these as continuous features where they're an integer, we also need to make a list of the categorical features we want to work with, such as working class, education, marital, occupation, relationship, race, sex, and native country. And again, these are all objects, so that makes sense. And when we flip back over to the data, we can see here we're actually looking at United States. If we continue down, see if I can find another one. A lot of United States on this particular one. I was getting worried there for a second that we only had United States and it was a very biased census, which it probably is for wherever it came from. And of course, bachelor's, associate, vocational, some college. So you can see this is more categorical versus an actual number. So now we have our categorical and we have our continuous features. And this is just the list of these. So let's go ahead and run that and load that list in there so we can now start manipulating our data with it. Now we get our first line of TensorFlow code, which is exciting. And we're going to create a variable continuous features. And what we're doing in here is we're going to go into TF feature columns. So we have the feature columns. We're going to set those up. Numeric columns K for K in continual features. So this is going to go in here and says each one of these is a continual feature, and we're going to feed that into the feature column. Not very exciting on the output because we're just creating this variable here, letting it know what columns are what. Then we're going to create a relationship setup. So we have continuous features and then we have a relationship. And again, we're doing TF, but in this case we use feature column. So just like this one, we're telling it feature column, and now we do categorical column with vocabulary list. So that's one of the things we can do with TensorFlow. And we're going to feed it one. We have relationship, and so we're just drilling down to the relationship column. And these are the options they had. So this is going to be the vocabulary attached to this column. And we'll go ahead and run that. So we load up our relationship. And then we're going to do one more way of loading. In this one, we're going to do categorical features. And so in categorical features, we're going to do TF feature column. There's our command we've already seen before. And it's going to be categorical column with hash bucket. we're going to create buckets. In this case, for k and categorical features, so it's going to create a bucket for each one of these categorical features, and the bucket size is 1000. So we're looking at, and we've actually kind of repeated something because relationship is also in the bucket setup on there. But we wanted to show you three major ways of loading in your different features. One is our features that we know where it's going to be a number, so our continuous features. Then we can set it as a relationship. In this case, we actually created a vocabulary, husband, not in family, very clear vocabulary on there. And then we also are loading just general categories into buckets. You can set different bucket settings in here. We went ahead and just went with 1000, so pretty much everything, since there's not a huge number of categories, each one gets their own kind of bucket setup in there. And as far as the initial setup, we need to go ahead and create a model. And so this is where it starts to come together. We've, as far as the pre-setup, we have our TF, we have an estimator. We're going to do linear classifier on the estimator. In classes equals 2, so we know there's only 2 classes we're looking at. We have ongoing train feature columns. And then we have our different, we have categorical features plus continuous features. So this basically creates our model, what data is going in. And we'll go ahead and run this, and you can see here that it gives us a little information that we had our TensorFlow using default config. You can change a lot of defaults you can change as far as the model directory, random seed, saving summary, checkpoints. There's all kinds of things you can go in here and set up. Rewrite options, keep checkpoint mix, etc. At this point, the model hasn't done anything. All we've done is create the model. So let's just do a real quick rehash of what we've done so far. What we started off with is we grabbed some data. In this case, adult and adult tests. We have a training data set and a test data set. We set the columns up. We took a very short, brief exploration of the data and its shape as far as what we're working with. We changed our label around a little bit so that the label makes a little bit more sense of 0, 1. Instead of, for the machine, it's easier to spit out a 0 or a 1. We can look up here, we double check to make sure how many zeros and ones we have. Double check our data, make sure it's integer 64, nothing weird's going on. And then we looked at 3 different ways that we can kind of label the data as far as the way we're going to read it. We have our continuous features and a categorical features. Here's our relationship, which is one of them. When we went ahead and created our model, we did not put the relationship in here, which you can do. You can actually maybe take it out of categorical and then have its own on here instead of having categorical features and continuous features and so on. So we've created our setup for our model. The next thing we need to do is we need to go ahead and create a function letting it know how to read the data into our model. How are we going to train it? And let's go ahead and create 2 variables. The first one is going to be features. This is just all the features that are in there. And then the second one is going to be our label. And this is basically, we're looking at all the different information we can put into it, and then is that person, based on that information, going to make less than or greater than 50K? That's what that comes down to. Now, the next part, the definition we're going to create has a lot in it. And we're going to feed this definition into our model training. So there's a lot of stuff that goes on here. First, we'll call it get input and function. Def get input function. We have our data set, number of epochs equals none, in batch equals 128, shuffle equals true. So we're running this, and this is going to return a TF estimator inputs pandas input function. And in this case, it's going to be x equals our PD data frame k data set k values for k and features. Y is PD series dataset label values. Batch size equals in batch. Number of epochs equals number of epochs. Shuffle equals shuffle. So in here we're passing in the number of epochs. We're not too worried about, we're going to just go once through the data because there's a lot of data in there. We don't need to rerun it. Epochs is how many times do you cover all the data? And then how many groups of data do you pull in and batch at a time? So we're only going to look at 128, do the reverse propagation like we talked about, and then it'll go to the next batch, and the next batch, and the next batch, and it shuffles them. So shuffle means that we're randomly picking where they're coming from. And we're not too worried about the number of epochs for this particular model. Depending on how much data you have and depending on what you're running, depends on how many epochs you need to run. And there's a lot of rules on how many epochs you need to run. One of them is if your training data and your testing data, because you'll check your testing data against your training data. If your testing data starts having a better results than your training data, that means you're no longer fitting towards the data, but you're fitting to the answer. So it's kind of these little weird things you start to on here. And TensorFlow is really cool because it actually checks a lot of that for you. But we're just going to set number of epochs equal to 0, and then we have our data set going in. So we're creating our get function. How do we get the data into training our model? And we'll go ahead and run that. So now we have our data function, and now it knows where the data is coming from. So we need to go ahead and train it. And that's simply we take our model we created way up here. That's where we take the model there. We've told it what columns it's going to pull in, so it knows what columns it's looking at, know what the definition where it's going to get the information from. So now we want to go ahead and train it. And here's our input function equals, in this case, get input function. And here we tell it that our data set is a df train, number of epochs equals none, which is already automatically set up there, in batch equals 128, which is what we have up here, shuffle equals false, and we're going to do 1,000 steps. So we're actually going to go through 128 batches, but we're going to do that 1,000 times. And we'll go ahead and run this. And I just ran an update, so it's going to give me some warnings because of that update. And then we're back here and it's still going. To construct pipelines, use TF data module. Not a big problem. We let it go ahead and run all the way through on here. And it takes it just a moment. There we go. There's our 1,000 coming out. And as you can see here, here's checkpoints for 1,000, ongoing training, 1,001, global steps. And this is just all the reverse propagation going on. That's what we're doing here. One of the things we didn't cover is we do it in small increments. So it's not all done like one error goes all the way back. You'd only do a part of that error, and each one sends back a little piece, and so you slowly adjust your different weights going all the way back. And then if you're going to train your model, we want to know how it did. So we're going to do model evaluate. And our input function equals, remember our input function up here that we created? Way up here. We're going to take this input function, and instead of the data set that's coming in, we put in the data set here for training. Where's our training? Input train. There we go. df underscore train. Now we're going to go ahead and evaluate, and here it is, get input function test. So we're going to test the data out. Number of epochs 1, we don't need to rerun it more than once. Per batch 128, so on, shuffle, and steps 1,000. So we're going to go ahead and evaluate this. Let's just see how good our test data did, how good our model was programmed on our training data, and how it evaluates on the test. And we can see it going on down here where it's got the evaluating graph was finalized. Let me just highlight that. Ongoing model checkpoint, TensorFlow running local init, evaluate 100 out of 1,000, and so on. And once it gets to the end, we get a nice output here. We have an accuracy, in this case, of 0.79 with a baseline of 0.76. So now we've created a model. Let's go ahead and tweak it a little bit. So we have our accuracy up here. What we're going to do is we're going to look at age. And let's just go ahead and create a new square value for age. And the reason we want to look into the square value of age is we know that if you really look through the data, you'll find that as a young person, the age keeps increasing. And as you get close to retirement, it begins to decrease. So we square the value of age. And that's very data specific when we're looking at data. You'll find that any kind of data that has that kind of like uptick and downtick, by squaring it or square rooting it, you can get some very different results. And so we're going to go ahead and square our age. And this is kind of, it's interesting because at this point, even at the beginning of this, we're focused on deep learning and on TensorFlow. But before I would begin even looking at any of this, I would have probably run some kind of heat map or some kind of evaluation in R or sklearn in Python to find out the correlation between different features, to see just how well they correlate to each other. And there certainly are some wonderful tools for that, because sometimes you can just mark off some features and other features you bring in. But for the deep learning, we can see how we can just dump it all in there and let it sort it out itself. And we're going to just write a quick little function here to take the square variable. In this case, we have dft, dfte. And this is our training and your test variable, and the variable age coming in. And we just want to go ahead and create a new under dft, and the new is going to be the variable name, whatever we put in there, which will be age. So let's load this. Here's our functions now loaded. And certainly we could have just done that as a line of code. But you start to get the feeling that when you build these functions, you might use it. You can now use this function if you had a number of different features that had this kind of quality to them. And we have our df train new. So we're going to create a new training and a new test. And it's going to equal the square variable df train or df test. And the variable name is age. Let's just go go ahead and run that. And so now we have our df train new and df test new. And just like we did before, let's just double check the shape of our data and make sure it all matches. And when we look at the output here, really what's important is that each one of these has 16 features in it. We want to make sure we're not getting something weird on there. And our training set has 32,561 rows in it, and this one has just over 16,000 in there. And everything's pretty much the same, except that in our continuous features new, we now have the new column we put in there. So we need to change that. And we have our continuous features new down here, which we're going to load up with our TF feature column numerical. This would all look familiar because we just did this. And so we're going to load that up with the new being the new value in there. Let's go ahead and run that. And we'll create a model, but we'll call it Model 1. And this is the same that we did before, except now we have our continuous features new in here. So here's our new model. In this case, Model 1 instead of model. And we're going to build that model right there. Now we haven't trained it. All we've done is told it where to get the data and how to get the data and what features are coming in. We haven't actually told it everything on the features coming in because we still need to also build our get input function. So where's the input coming from? So we built the model with the features in it. And now we need to go ahead and create our get input function. This is the same as before, but you'll see we now have it with the data set coming in is going to be the same data set up here. And so if we scroll a little bit to the right, we should see the new. And there it is. Sure enough, there's our new on the right. And so let's go ahead and run that. Now we've defined our model. We've defined where the information is coming from. And again, you can go back and review the first part because this is identical that we did before, except now we have new as the column for the age. And we'll go ahead and do our Model 1 and let's go ahead and train it. There's our input function, get input function that we defined up here. df train is going to be the same and everything else is going to be the same. Let's go ahead and run that. And it should go through here and run the tensor info coming in. And it's going to go through, in this case, what we have, steps 1000, shuffling. So it's going to go randomly, 128 per batch. And then the epochs is automatic. We're not worried about that today. So now we have a trained TensorFlow model. And with our new model, just like we did before, we want to go ahead and evaluate it. So it's the same setup we had before with our same get input function with our df test new in here coming in. So there's our new data coming in. And this is really common when you're doing these models. You make little tiny tweaks to see if you can improve it. One of the best articles I read recently was you build your model to fail. You want a running model so that you actually have something to compare against. And then you continually tweak it till you get a better accuracy. Now, I don't expect the accuracy necessarily to get better on this because of the way we partition the data. But we can see here we now have an accuracy of 0.76, which is a little bit over the baseline. And it's about what I would have expected it to be, kind of the same. The reason is because we split the data at the people making over 50K and those making less. And so the age factor shouldn't be a huge factor. It would be if we were looking at more discrete buckets, like 40 to 50, 50 to 60, 60 to 70 when we create buckets. But in this, I didn't really expect it to go up that much. In fact, we could probably run it a dozen times, which would be very bad data science. And we see we actually had a slightly better one up here, but our baseline accuracy was 0.76. And we come down here, we still see, here's our accuracy baseline, 0.763. That didn't really change. And the accuracy didn't really go up that much. I could hit the run button a few times, and I would probably upbeat the one above. So not a big change, but that's all right. This is how we learn. This is how we go through and figure out what's going to work with our data and what's not. What's going to improve the quality of our data so we have a better prediction and what's not. And we can now go ahead and utilize this model. This is where it gets exciting when you're actually working with somebody or with your clients and you come in and you say, okay, here's my predictions. We're going to create a list and we're going to use Model 1 and we're going to predict. And our input function is get input function, df test new. Again, this probably doesn't make too big of a difference, but we'll go ahead and stick with the new data we created. Number of epochs 1, batch 128. So all this should look pretty familiar, but we're running the prediction. So we're going to load all our predictions into the predictions. And let's go ahead and run that. And you'll see it go through the TensorFlow setup. So it's running, done running local ops. And then let's just go ahead and print the df test new iLocation 0, so row 0. And we're going to look at the predictions also for the same location 0. And let's go ahead and run that. And we can see here that we have age 25, work class private. It has all the information coming in for that individual. And then it comes down here and we go ahead and get our prediction. And in this particular instance, there's our label 0. And then we we come down here and we see, it takes a little bit for the setup to look up, but there's our array which also returns a 0, and it has information for us on there, probabilities, logistics on here. So you can see there's all kinds of additional information you can pull from this. And likewise we could do it for position 3. Let me go ahead and run that. And what's kind of nice about this is you can now see here's label 1, and here's our logistics output. And again, we have to kind of hunt for it a little bit in this particular setup, but here's the output array, and there's our 1. And they match, label 1, 1. So we predicted for the very first one, location 0, that it's going to be a 0 on the label. It's going to make under 50,000. And the individual in 2, working class, private, whatever setup on here, capital gain, capital loss, etc., came up as 1, meaning they're going to make over 50,000. So we covered a lot. I mean, this is the basics, and you can see as you dig deeper, when you look at some of this code, let me just go back up here. We're way back up here at the very top, a little too far overshot. As we start working in here, we have 1, defining your features. And at this point, we didn't show this, but I would probably use either Python or R to show a relationship correlation, because they have some really easy packages in there to pull that up. So you can see what features are really connected and how they're connected. And then we showed you different features. Like we have ones that are integers, and then we have ones like sex that are objects. Your 0 or 1, your male or female. Your same thing with race. Probably have just maybe 16 different races listed there. Ethnicities, things like that. Native country. Again, that's, you don't have like infinite number of native countries. You just have a handful. So when we look at this, we have our features. We looked at that. We have our continuous features like age, which is a number, or in this case an integer, and education number, how many years, and so on, along with your race, your sex, your relationship, which are just very abbreviated categorical data. So we looked at that. We went in there and we showed you how to, where was it? Here we go. We go back up here. So we create our model. The model knows what categories are coming in. That's really important. And this is probably one of the more complicated parts of this is our input function. And this input function is so important. So I want to just rehash the input function for that reason. This lets us know how we're pulling the data. It lets us know if we're going to go through all the data 20 times, or we're just going to let TensorFlow itself keep going until the training model reaches a point. That point is based on what they call bias. You can become biased on your training data. And so when it hits a certain point where it becomes overly biased to just that data, then it doesn't really work really good in the outside world. You start losing. You want to keep it generic, but as close as possible to the right answer. So generic answers for a huge amount of data. And then we have our batch size. Are we going to shuffle it, which we did. And then also our estimator inputs. So you have your estimator function here. And then of course where the actual data is coming from. So you can see all this is in that get input function. That's where a lot of the work comes in putting this together. And then we train our model. That's pretty straightforward. Once you have your input function and all your setup, training the model is quick. And then we go ahead and evaluate, and then we can go ahead and create a predict, and then look at our predictions and how they work on individuals. So it gives you a whole roundabout setup on here and how this is set up and how it's working. Certainly there are a lot more things you can do with TensorFlow. This is the basic TensorFlow, and it's always developing, so it's exciting. This is going to be one of the most exciting fields right now because it is really in an infant stage and just exploding in the market.
This tutorial is about object detection. We will walk you through a TensorFlow code using which we will do object detection in images. We will tell you what are the libraries that are required, a little bit about the COCO dataset, and then we will show you the implementation code itself, a demo of the code. Alright, so let's get started. So what is the TensorFlow Object Detection API? It is an open source framework which is actually provided by the TensorFlow team, and there are trained models available, and the sample code is also available which we can use in order to easily detect objects in images and videos. This is pretty robust and can detect objects fairly quickly, and this is very easy for people to use as well. People with very less or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. This is a list of libraries that are required, and they have been shown in the code as well. The exact purpose of each of this library, why it is required is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The COCO data set. COCO stands for Common Objects in Context. So this data set consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source. And let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial, we are using this SSD model, which is SSD MobileNet version 1. So that's the model that we'll be using. So in this cell, we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. Might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is, your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now each of these will obviously, the numbers will not make any sense to the outside world, so we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I am storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach 1, beach 2, beach 3, and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2, and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically we will be filled with either 1, 2, or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop, and what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected, and then against each of the object a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code, and here is basically where we are calling this function. So we are loading these images and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here, and the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available and it will be shown in the other video, and frame by frame we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video, just look out for that, and actually the information about that is provided in the cards, the I symbol. So that's the video object detection in video. That's the separate tutorial. Alright, so now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there is something in the sky and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images.
Simplilearn welcomes you to machine learning versus deep learning versus artificial intelligence, some of the most exciting technologies evolving in today's world. My name is Richard Kirshner, and I'll be hosting this talk for Simplilearn. Before we start covering the basics of these three topics and how they connect and how they are different, let's just look at a few examples so we get an understanding of what's going on. Here's an example of artificial intelligence in today's world, Amazon Echo. Amazon Echo is a wonderful tool. We can go in there and you can say, hey, Alexa, what's the temperature in Chicago? And the Amazon Echo then translates that into zeros and ones and something the computer understands. Then it comes in and processes that information to identify what you're asking and what you need and where to get that information. And then it comes back and says the current temperature in Chicago is 6 degrees Fahrenheit or whatever it is at the moment. So this is a wonderful example of artificial intelligence that we're using right now today and where that's at as far as a commercial deployment. Machine learning. A machine learning example out there is Google. You're on your Google search engine. It comes up. You spend a lot of time on the first link you come into and you read the page. And Google looks at that and says, okay, he spent 5 minutes on this. Let's give it a thumbs up. And then you go to the second page and the third page, you just kind of skip over them and glance at them for a couple seconds. And Google says, I wasn't interested in those pages. Let's give them a thumbs down. So this is a good example of machine learning as it starts guessing what you like and what you don't like. So it gives you more information along what you're going to read and actually use. And then we have an example of deep learning. In this example, we have a black and white image. It comes into, in this case, a neural network. Some people like to call it a magic box because it's hard to follow all that's going on in there. There's all these different weights and connections and nodes. And then it comes out and colors the beach ball, the people, the background. What's going on in here is the black and white image goes into this neural network. And before it's ever gone in, the neural network has looked at all these different pictures on the web or wherever it pulls the data from. And it's already itemized them and kind of separated them that we have some that look like beach balls, we have some that look like people, and it programs that so that when the black and white image comes in, it goes, okay, that piece right there resembles this and all these other photos. And the neural network is able to identify that and then color the beach ball with the colors that you see on there. So it gives it this is really wonderful because they did a wonderful job coloring this picture. And that's the full setup is where the deep learning example comes in, and they usually center around neural networks. So we looked at a few examples. What's in it for you? First, we're going to talk about human versus artificial intelligence. This is very important because this is our marker. We as humans are amazing, and so we want to understand how artificial intelligence compares and what it does that it can accelerate above humans and how it can integrate with the human experience. What is machine learning and deep learning all about? Are they really all that different? We'll have a few more examples in here, and then we'll talk a little bit about types of AI and machine learning and comparing machine learning and deep learning. And finally, a glimpse into the future. Human versus artificial intelligence. Humans are amazing. Let's just face it, we're amazing creatures. We're all over the planet. We're exploring every niche and nook. We've gone to the moon. We've gone into outer space. We're just amazing creatures. We're able to use the available information to make decisions, to communicate with other people, identify patterns in data, remember what people have said, adapt to new situations. So let's take a look at this. So you can get a picture. You're a human being, so you know what it's like to be human. Let's take a look at artificial intelligence versus the human. Artificial intelligence develops computer systems that can accomplish tasks that require human intelligence. So when we're looking at this, one of the things that computers can do is they can provide more accurate results. This is very important. Recently I did a project on cancer where I was identifying markers. And as a human being, you look at that and you might be looking at all the different images and the data that comes off of them and say, I like this person, so I want to give them a very good outlook. And the next person you might not like, so you want to give them a bad outlook. Well, with artificial intelligence, you're going to get a consistent prediction of what's going to come out. Interacts with humans using their natural language. We've seen that as probably the biggest development feature right now that's in the commercial market that everybody gets to use, as we saw with the example of Alexa. They learn from their mistakes and adapt to new environments. So we see this slowly coming in more and more. And they learn from the data and automate repetitive learning. Repetitive learning has a lot to do with the neural networks. You have to program thousands upon thousands of pictures in there, and it's all automated. So as today's computers evolve, it's very quick and easy and affordable to do this. What is machine learning and deep learning all about? Imagine this. Say you had some time to waste. Not that any of us really have a lot of time anymore to just waste in today's world. And you're sitting by the road, and you have a whole lot of time passes by. There's a few hours. And suddenly you wonder, how many cars, buses, trucks, and so on passed by in the 6 hours? Now, chances are you're not going to sit by the road for 6 hours and count buses, cars, and trucks, unless you're working for the city and you're trying to do city planning, and you want to know, hey, do we need to add a new truck route? Maybe we need a bicycle lane because we have a lot of bicyclists here, that kind of thing. So maybe city planning would be great for this. Machine learning. Well, the way machine learning works is we have labeled data with features. Okay, so you have a truck or a car, a motorcycle, a bus, or a bicycle, and each one of those are labeled. It comes in, and based on those labels and comparing those features, it gives you an answer. It's a bicycle, it's a truck, it's a motorcycle. Let's look a little bit more in depth on this. In the model here, the features we're looking at would be like the tires. Someone sits there and figures out what a tire looks like. It takes a lot of work. If you try to figure the difference between a car tire, a bicycle tire, a motorcycle tire, so in the machine learning field, this could take a long time if you're going to do each individual aspect of a car and try to get a result on there. And that's what they did do. That was this is still used on smaller amounts of data where you figure out what those features are and then you label them. Deep learning. So with deep learning, one of our solutions is to take a very large unlabeled data set and we put that into a training model using artificial neural networks. And then that goes into the neural network itself when we create a neural network. And you'll see the arrows are actually kind of backward, but which actually is a nice point because when we train the neural network, we put the bicycle in and then it comes back and says, if it said truck, it comes back and says, well, you need to change that to bicycle. And then it changes all those weights going backward, they call it back propagation, and let it know it's a bicycle, and that's how it learns. Once you've trained the neural network, you then put the new data in, and they call this testing the model, so you need to have some data you've kept off to the side where you know the answer to. And you take that and you provide the required output, and you say, okay, is this neural network working correctly? Did it identify a bike as a bike, a truck as a truck, a motorcycle as a motorcycle? Let's just take a little closer look at that. Determining what objects are present in the data. So how does deep learning do this? And here we have the image of the bike. It's 28 by 28 pixels. That's a lot of information there. Could you imagine trying to guess that this is a bicycle image by looking at each one of those pixels and trying to figure out what's around it? And we actually do that as human beings. It's pretty amazing. We know what a bicycle is, and even though it comes in as all this information. And what this looks like is the image comes in, it converts it into a bunch of different nodes. In this case, there's a lot more than what they show here. And it goes through these different layers and out comes and says, okay, this is a bicycle. A lot of times they call this the magic black box. Why? Because as we watch it go across here, all these weights and all the math behind this, and it's a little complicated on the math side. You really don't need to know that when you're programming or working with the deep learning. But it's like magic. You don't know, you really can't figure out what's going to come out by looking what's in each one of those dots and each one of those lines are firing and what's going in between them. So we like to call it the magic box. So that's where deep learning comes in. And in the end, it comes up and you have this whole neural network that comes up and it says, okay, we fire all these different pixels and we connects all these different dots and gives them different weights and it says, okay, this is a bicycle. And that's how we determine what the object is present in the data with deep learning. Machine learning. We're going to take a step into machine learning here, and you'll see how these fit together in a minute. The system is able to make predictions or take decisions based on past data. That's very important for machine learning, is that we're looking at stuff, and based on what's been there before, we're creating a decision on there. We're creating something out of there. We're coloring a beach ball. We're telling you what the weather is in Chicago. What's nice about machine learning is a very powerful processing capability. It's quick and accurate outcomes, so you get results right away. Once you program the system, the results are very fast. And the decisions and predictions are better. They're more accurate. They're consistent. You can analyze very large amounts of data. Some of these data things that they're analyzing now are petabytes and terabytes of data. It would take hundreds of people hundreds of years to go through some of this data and do the same thing that the machine learning can do in a very short period of time. And it's inexpensive compared to hiring hundreds of people. So it becomes a very affordable way to move into the future, is to apply the machine learning to whatever businesses you're working on. And deep learning. Systems think and learn like humans using artificial neural networks. Again, it's like a magic box. Performance improves with more data. So the more data the deep learning gets, the more it gives you better results. It's scalability, so you can scale it up, you can scale it down, you can increase what you're looking at. Currently, we're limited by the amount of computer processing power as to how big that can get, but that envelope continually gets pushed every day on what it can do. Problem solved in an end-to-end method. So instead of having to break it apart, and you have the first piece coming in and you identify tires, and the second piece is identifying labeling handlebars, and then you bring that together, that if it has handlebars and tires, it's a bicycle, and if it has something that looks like a large square, it's probably a truck. The neural networks does this all in one network. You don't really know what's going on in all those weights and all those little bubbles, but it does it pretty much in one package. That's why the neural network systems are so big nowadays and coming into their own. Best features are selected by the system, and this is important. They kind of put it's on a bullet on the side here. It's a subset of machine learning. This is important. When we talk about deep learning, it is a form of machine learning. There's lots of other forms of machine learning, data analysis, but this is the newest and biggest thing that they apply to a lot of different packages, and they use all the other machine learning tools available to work with it. And it's very fast to test. You put in your information, you then have your group of test, and then you held some aside, you see how does it do. It's very quick to test it and see what's going on with your deep learning and your neural network. Are they really all that different? AI versus machine learning versus deep learning. Concepts of AI. So we have concepts of AI. You'll see natural language processing, machine learning, an approach to create artificial intelligence. So it's one of the subsets of artificial intelligence. Knowledge representation, automated reasoning, computer vision, robotics. Machine learning versus AI versus deep learning, or AI and machine learning and deep learning. So when we look at this, we have AI with machine learning and deep learning. And so we're going to put them all together. We find out that AI is the big picture. We have a collection of books. It goes through some deep learning. The digital data is analyzed. Text mining comes through. The particular book you're looking for, maybe it's a genre of books, is identified. And in this case, we have a robot that goes and gives a book to the patron. I have yet to be at a library that has a robot bring me a book, but that will be cool when it happens. So we'll look at some of the pieces here. This information goes into, as far as this example, the translation of the handwritten printed data to digital form. That's pretty hard to do. That's pretty hard to go in there and translate hundreds and hundreds of books and understand what they're trying to say if you've never read them. So in this case, we use the deep learning because you can already use examples where they've already classified a lot of books, and then they can compare those texts and say, oh, okay, this is a book on automotive repair. This is a book on robotic building. The digital data is then analyzed. Then we have more text mining using machine learning. So maybe we'd use a different program to do a basic classify what you're looking for and say, oh, you're looking for auto repair and computers. So you're looking for automated cars. Once it's identified, then of course it brings you the book. So here's a nice summation of what we were just talking about. AI with machine learning and deep learning. Deep learning is a subset of machine learning, which is a subset of artificial intelligence. So you can look at artificial intelligence as the big picture. How does this compare to the human experience in either doing the same thing as a human we do, or it does it better than us? And machine learning, which has a lot of tools, is something that learns from data, past experiences. It's programmed. It's comes in there and it says, hey, we already had these 5 things happen. The 6th one should be about the same. And then there's a lot of tools in machine learning, but deep learning then is a very specific tool in machine learning. It's the artificial neural network, which handles large amounts of data and is able to take huge pools of experiences, pictures, and ideas and bring them together. Real life examples. Artificial intelligence, news generation. Very common nowadays as it goes through there and finds the news articles or generates the news based upon the news feeds or the backend coming in, and it says, okay, let's give you the actual news based on this. There's all the different things. Amazon Echo, they have a number of different Prime Music on there. Of course, there's also the Google Command, and there's also Cortana. There's tons of smart home devices now where we can ask it to turn the TV on or play music for us. That's all artificial intelligence. From front to back, you're having a human experience with these computers and these objects that are connected to the processing. Machine learning, spam detection, very common. Machine learning doesn't really have the human interaction part. So this is the part where it goes and says, okay, that's a spam, that's not a spam, and it puts it in your spam folder. Search engine result refining, another example of machine learning, whereas it looks at your different results and it is able to categorize them as far as this had the most hits, this is the least viewed, this has 5 stars, however they want to weight it. All good examples of machine learning. And then the deep learning. Deep learning, another example is as you have like a exit sign, in this case is translating it into French, sortie. I hope I said that right. The neural network has been programmed with all these different words and images, and so it's able to look at the exit in the middle, and it goes, okay, we want to know what that is in French, and it's able to push that out in French, and learn how to do that. And then we have chatbots. I remember when Microsoft first had their little paperclip. Boy, that was like a long time ago. That came up and you would type in there and chat with it. These are growing. It's nice to just be able to ask a question and it comes up and gives you the answer. And instead of it being where you're just doing a search on certain words, it's now able to start linking those words together and form a sentence in that chat box. Types of AI and machine learning. Types of artificial intelligence. This and the next few slides are really important. So one of the types of artificial intelligence is reactive machines. Systems that only react. They don't form memories, they don't have past experiences, they have something that happens to them and they react to it. My washing machine is one of those. If I put a ton of clothes in it and they get all clumped on one side, it automatically adds a weight to recenter it. So that my washing machine is actually a reactive machine working with whatever the load is and keeps it nice, and so when it spins it doesn't go thumping against the side. Limited memory. Another form of artificial intelligence. Systems look into the past. Information is added over a period of time and information is short-lived. When we're talking about this and you look at like a neural network that's been programmed to identify cars, it doesn't remember all those pictures. It has no memory as far as the hundreds of pictures you process through it. All it has is, this is the pattern I use to identify cars as the final output for that neural network we looked at. So when they talk about limited memory, this is what they're talking about. They're talking about, I've created this based on all these things, but I'm not going to remember any one specifically. Theory of mind. Systems being able to understand human emotions and how they affect decision making to adjust their behaviors according to their human understanding. This is important because this is our page mark. This is how we know whether it is an artificial intelligence or not. Is it interacting with humans in a way that we can understand? Without that interaction, is just an object. So when we talk about theory of mind, we really understand how it interfaces that whole, if you're in web development, user experience would be the term I would put in there. So the theory of mind would be user experience. How is the whole UI connected together? And one of the final things is, as we get into artificial intelligence, is systems being aware of themselves, understanding their internal states, and predicting other people's feelings and act appropriately. So as artificial intelligence continues to progress, we see ones that are trying to understand, well, what makes people happy? How would they increase our happiness? How would they keep themselves from breaking down if something's broken inside? They have that self-awareness to be able to fix it. And just based on all that information, predicting which action would work the best, what would help people. If I know that you're having a cup of coffee first thing in the morning is what makes you happy as a robot, I might make you a cup of coffee every morning at the same time to help your life and help you grow. That'd be the self-awareness, is being able to know all those different things. Types of machine learning, and like I said on the last slide, this is very important. This is very important. If you decide to go in and get certified in machine learning or know more about it, these are the three primary types of machine learning. The first one is supervised learning. Systems are able to predict future outcome based on past data. Requires both an input and an output to be given to the model for it to be trained. So in this case, we're looking at anything where you have 100 images of a bicycle, and those 100 images are bicycle. So they're preset. Someone already looked at all 100 images and said, these are pictures of bicycles. And so the computer learns from those, and then it's given another picture, and maybe the next picture is a bicycle, and it says, oh, that resembles all these other bicycles, so it's a bicycle. And the next one's a car, and it says, it's not a bicycle. That would be supervised learning, because we had to train it. We had to supervise it. Unsupervised learning. Systems are able to identify hidden patterns from the input data provided by making the data more readable and organized. The patterns, similarities, or anomalies become more evident. You'll heard the term cluster. How do you cluster things together? Some of these things go together, some of these don't. This is unsupervised, where it can look at an image and start pulling the different pieces of the image out because they aren't the same. All the parts of the human are not the same as a fuzzy tree behind them because it's slightly out of focus, which is not the same as the beach ball. It's unsupervised because we never told it what a beach ball was, we never told it what the human was, and we never told it that those were trees. All we told it was, hey, separate this picture by things that don't match and things that do match and come together. And finally, there's reinforcement learning. Systems are given no training. It learns on the basis of the reward punishment it received for performing its last action. It helps increase the efficiency of a tool function or a program. Reinforced learning, or reinforcement learning, is kind of, you give it a yes or no. Yes, you gave me the right response. No, you didn't. And then it looks at that and says, oh, okay, so based on this data coming in, what I gave you was a wrong response, so next time I'll give you a different one. Comparing machine learning and deep learning. So remember that deep learning is a subcategory of machine learning. So it's one of the many tools. And so we're grouping a ton of machine learning tools all together. Linear regression, k-means clustering. There's all kinds of cool tools out there you can use in machine learning. Enables machines to make decisions on their own based on past data. Enables machines to make decisions with the help of artificial neural networks. So it's doing the same thing, but we're using an artificial neural network as opposed to one of the more traditional machine learning tools. Needs only a small amount of training data. This is very important. When you're talking about machine learning, they're usually not talking about huge amounts of data. We're talking about maybe your spreadsheet from your business and your totals for the end of the year. When you're talking about neural networks, you usually need a large amount of data to train the data. So there's a lot of training involved. If you have under 500 points of data, that's probably not going to go into machine learning. Or maybe you have, like the case of one of the things, 500 points of data and 30 different fields. It starts getting really confusing there in artificial intelligence or machine learning, and the deep learning aspect really shines when you get to that larger data that's really complex. Works well on a low-end systems. So a lot of the machine learning tools out there you can run on your laptop with no problem and do the calculations there. Where with the machine learning, you usually needs a higher end system to work. It takes a lot more processing power to build those neural networks and to train them. It goes through a lot of data. We're talking about the general machine learning tools. Most features need to be identified in advance and manually coded. So there's a lot of human work on here. The machine learns the features from the data it is provided. So again, it's like a magic box. You don't have to know what a tire is. It figures it out for you. The problem is divided into parts and solved individually and then combined. So machine learning, you usually have all these different tools and use different tools for different parts. And the problem is solved in an end-to-end manner. So you only have one neural network or two neural networks that is bringing the data in and putting it out. It's not going through a lot of different processes to get there. And remember, you can put machine learning and deep learning together. So you don't always have just the deep learning solving the problem. You might have it solving one piece of the puzzle. With regular machine learning and most of the machine learning tools out there, they take longer to test and understand how they work. And with the deep learning, it's pretty quick. Once you build that neural network, you test it and you know. So we're dealing with very crisp rules, limited resources. You have to really explain how the decision was made when you use most machine learning tools. But when you use the deep learning tool inside the machine learning tools, the system takes care of it based on its own logic and reasoning. And again, it's like a magic black box. You really don't know how it came up with the answer. You just know it came up with the right answer. A glimpse into the future. So a quick glimpse into the future, artificial intelligence, be using it to detecting crimes before they happen, humanoid AI helpers, which we already have a lot of. There'll be more and more. Maybe it'll actually be androids. That'd be cool to have an android that comes and gets stuff out of my fridge for me. Machine learning, increasing efficiency in healthcare. That's really big in all the forms of machine learning. Better marketing techniques. Any of these things, if we get into the sciences, it's just off the scale. Machine learning and artificial intelligence go everywhere. And then the subcategory deep learning, increased personalization. So what's really nice about the deep learning is it's going to start now catering to you. That'll be one of the things we see more and more of. And we'll have more of a hyper-intelligent personal assistant. I'm excited about that. What we have learned so far. We covered artificial intelligence. In this case, the AI versus the human. We did a lot of that, so we have a page marker of human interaction. We discussed machine learning and all their different parts, and then we discussed the deep learning aspect. We went into AI and machine learning and deep learning, how they're all subcategories of each other. Very important to remember that. Artificial intelligence is a big picture. Machine learning is a category in artificial intelligence, and then deep learning is a tool in machine learning. We talked of all the aspects in the machine learning and deep learning and how they compare, and we took a quick glimpse into the future and all the different, I'm sure you can come up with many more examples of where it's coming out in our future. But we looked at a few of them so you have some ideas of where this is going and all the different wonderful opportunities are going to come out with it. Welcome to today's lesson. My name is Richard Kirshner. I'm with the Simplilearn team. Today we want to discuss the very basics of a neural network and what that is. So, what's in it for you today? What is deep learning? What is artificial neural network? How does neural network work? Advantages of a neural network, applications of a neural network, and the future of neural networks. Let's start with a brief history of the artificial intelligence. Hello, I am the human brain. This one's seeking enlightenment and has sat and meditated. I am the most complex organ in the human body, and I help you to think, understand, and make decisions. And the secret behind all my power is a neuron. I'll get back to that in some time. Ever since the 1950s, scientists have been trying to mimic the functioning of a neuron and use it to build smarter robots. After a lot of trial and error, humans finally designed a computer that can recognize human speech. It was only after 2000 that humans were able to give birth to deep learning that was able to see and distinguish between different images and videos. So looking at that, let's dive into what is deep learning. Now your first thought might be it's the opposite of shallow learning. No, deep learning I liken to a magic box. And let's go in there and just take a look as to why it's kind of a magic box. So what exactly is deep learning? These are the images of dogs. Deep learning is a machine learning technique that teaches computers to do what comes naturally to humans. Learn by example. The robot gets trained with photos as example. Now this is very different than hardwiring a computer program so that it recognizes something. It actually learns. And that's where it's a magic box, because you don't really control how it learns, you control the aspects that go in. The computer comes back and says, wait, I know what you are. It looks at the photograph of the dog and it's able to identify that it saw in the images. It says, you are a dog. Woof woof. So that's an example of deep learning. You'll notice We didn't go in, we'll go into actually how it works behind the scenes for a neural network. But there's a bit of feeling of magic, and that's where the term deep learning comes in. And that's also the term where I like to call it a magic box. You put these things in here into the program, and it starts running the deep learning, and you have to understand those settings, but you don't have to follow exactly what's going on in the deep learning model. That brings us to the question, how does deep learning do it? Remember the neuron? Scientists managed to build an artificial form of it that powers any deep learning based machine. So let's talk about artificial neural networks. What is an artificial neural network? To understand how an artificial neuron works, we need to understand how the real one works. First we have a dendrite, input to the neuron. And you can see these little hairs that come in and they receive information. Then we have the cell body. Information processing happens here. So it takes all these different dendrite and information coming in from the different dendrites and it looks at that information. And then you have your axon, which is the output to the neuron. So there goes your axon and you see it goes all the way out and at the very end it flanges out and each one of those little flanges connects to the dendrite or the hairs on the next one. Now let's see what an artificial neural network looks like. So in an artificial neural network, we have an input layer. So that could be an array of data. Each one of those white dots in the yellow bar would represent, say, a pixel in a picture. Then you have the lines that connected to the hidden layers, which are your weights. And they add all those up on the hidden layers, and each one of those dots, kind of like a cell, does something with all the inputs. And then it puts an output into the next hidden layer, and so on into the output layer. So information processing happens here. Input to the neuron, output to the neuron. So you can see how they are similar. We have an input, which is our yellow bar coming in, and then you liken each of the hidden layers to being a neuron, and it passes it to the next one, and so on, and then you have an output to the next neuron or an output to the real world. A neural network is a system of hardware and or software patterned after the operation of neurons in the human brain. Neural networks, also called artificial neural networks, is a way of achieving deep learning. How does artificial neural networks work? Let us find out, how does an artificial neural network work? Hey Siri, what is the time now? It's 12:30 in the morning. Thanks. Let's find out how she recognizes speech. Here is a neural network and the different layers on it. So we have our input layer, our hidden layers, and the output layer. This is the sentence that needs to be recognized by the network. What is the time? So when it comes in, each one comes in as a pattern of sound. So what is the time? First, let's consider the word what. And you have W-H-A-T. And you can see each one of those in the sound bar, probably looks a little different than that, just a representation, comes in as a different pattern. Now we will split the sound wave for the letter W into smaller segments. So we split off W, and then we take W and we analyze just W. As the amplitude is varying in the sound wave for W, we collect the values at different intervals and form an array. So we have 0.5, 1.5, 1.7, 1.9, that might be the different amplitudes coming in, and we feed the array of amplitudes to the input layer. So each one of those goes into its own box on the input layer. Random weights are assigned to each interconnection between input and hidden layer. So remember all those little lines? I said those are special weights. Now we're going to start by doing it randomly. We always start with random because if you start with some kind of preset identical pattern, like if you set them all to 3, it takes forever to train it and you're less likely to get a good result, where random works really well in this. The weights are multiplied with the inputs and a bias is added to form the transfer function. So we make a sum of all the weights times the value. So you take 0.5, which is your x coming in, and we're going to multiply that by W1, W2, W3, so on. And then when we get to the next level, we're going to add those together coming in, what's coming in. So we add the weight times x. And there's always a bias added in. If you ever build your own neural network, don't forget to add the bias in. Otherwise, it tends to not work quite as well. You need that extra layer in there to help it. Weights are assigned to the interconnection between the hidden layers. The output of the transfer function is fed as an input to the activation function. So the output from one hidden layer becomes the input to the next hidden layer. Acoustic model contains the statistical representation of each distinct sound that makes a word. And so we start building these acoustical models, and as these layers separate them out, they'll start learning what the different models are for the different letters. Lexicon contains the data for different pronunciations of every word. So we have the lexicon at the end, where we end up with the A, B, C, D, and it identifies the different letters in there. Now, the term acoustic model and the term lexicon are specific to this domain, the domain of understanding speech. Certainly when you're doing photographs and other things, you'll have different labels on here, but the process is going to be the same. And finally, we get our output layer. Following the same process for every word and letter, the neural network recognizes the sentence you said. What is the time? So it identifies a W-H-A-T and then identifies that that's one word. What is the time? And so on. It's 12:30. That way Siri can look up the time and read it back to you. So let's look at the advantages of an artificial neural network. So gentlemen, could you tell me the advantages of an artificial neural network? It's amazing how many times I've been in that situation where I have to explain to the people making the decisions in the company. It's amazing how many times I've been in that space where I have to explain to the owner of the company what the artificial intelligence and the neural network actually do. What are the advantages of an artificial neural network and what it can do for them and how it works. So, an artificial neural network, outputs aren't limited entirely by inputs, and results given to them initially by an expert system. This ability comes in handy for robotics and pattern recognition systems. Artificial neural networks have the potential for high fault tolerance. Artificial neural networks are capable of debugging or diagnosing a network on their own. Very common use these days is to go through all the log files and sort them out. Thousands of log files if you're working as an admin. Nonlinear systems have the capability of finding shortcuts to reach computational expensive solutions. So we see this in banking where by hand they have an Excel spreadsheet and then they start building codes around that Excel spreadsheet, and over 20 years they might build a repertoire of all these functions, and the neural network comes up with the same answers done in days, weeks, or even a month for a huge bank. So let's take a look a little bit more, because I mentioned a couple applications of artificial intelligence there, but let's dig deeper into the applications of artificial intelligence. Let's look at some of the real life. This is stuff going on right now in our world. We're in such an exciting time with the neural networks and the machine learning and the artificial intelligence development. So let's take a little look at some of the current applications going on in real life. And you can use your imagination to dig for some new ones that we don't have listed here, because it's so limitless, the amount of applications that are being worked on right now or being implemented. Handwriting recognition. Neural network is used to convert handwritten characters into digital characters that the system can recognize. Stock exchange prediction. If you've ever worked with stock exchange, which I have, it is so fickle to track. I mean, it is really hard to understand. There are many factors that affect the stock market. Neural network can examine a lot of factors and predict the prices on a daily basis, helping the stockbrokers. So right now, it's still at the intro phase where it helps them, and they really have to look closely at it. When you realize that we generate over 3 terabytes a day just from the stock exchange here in the United States, that's a lot of data to dig through, and you have to sort it out before you even start focusing on even one stock. Traveling salesman problem. It refers to finding the optimal path to travel between all cities in an area. Neural network helps solve the problem, providing higher revenue at a minimal cost. Logistics is huge. Just the logistics, if we talk about a salesman traveling from town to town, logistics are used by Amazon. Amazon loves to ship their packages, and they have empty space on their trucks, so they'll pre-ship packages and fill that empty space on who they think will buy it. Saves them a lot of time, and people are a lot happier because they get it tomorrow instead of having to wait 3 weeks. Image compression. Idea behind data compression neural network is to store, encrypt, and recreate the actual image again. So we can optimize our compression in data. Images are the biggest one, but it's used in all kinds of data. Wonderful application to save hard drive and to optimize being able to read it back out again. Those are just a few, and like I said, use your mind to dig deeper. And let's take it even further. We're going to go a step further here, and let's look at the future of deep learning. And here we are. That's not me, thank goodness. A wonderful person there reading her crystal ball. I'll tell you what I see in the future. More personalized choices for users and customers all over the world. I certainly like that when I go in there and whatever online ordering system starts referring stuff to me. Local company here where I live that uses this where you can take a picture and it starts looking for what you want based on your picture. So if you see a couch you like, it starts looking for furniture like that, or clothing. I think it's mainly clothing. Hyper intelligent virtual assistants will make life easier. If you played with Google Assistant or Siri or any of those, you can see how they're slowly evolving, and they're just now getting over that hump where a virtual assistant can do all kinds of things, even pre-write your email response for you. New forms of algorithm for learning methods would be discovered. There's always something rolling out, and they've had some really cool research research in this area. Again, this stuff is we're just in the infant stage of artificial intelligence and neural networks and actually applying them to the real world. Wonderful time to jump in. Neural networks will be a lot faster in the future. Neural network tools will be embedded in every design surface. We already see that you can buy a little mini neural network that plugs into a really cheap processing board or into your laptop. So the hardware is starting to come out that goes right in there where you can dump it on there, and that makes it also faster. So because it's on the hardware instead of the software side. Neural networks will be used in the field of medicine, agriculture, physics, discoveries, just everything you can imagine. We see this today where it's going from a PhD student in medicine trying to understand T cells and understand the statistic analysis of that to cure people, to help keep them healthy, to help find out how we heal, to something that anybody can go access and process the data on. They're working on shared data systems. This concept of it being used in these different fields and these different domains is huge. The world's wide open for anybody jumping out there to start exploring them and start learning neural networks. What's in it for you? Well, today we're going to cover what is a neural network, what can neural networks do, how does a neural network work, types of neural networks, and then we're going to jump into a use case to classify between the photos of dogs and cats. And we'll do that on the Keras with the TensorFlow in the back, but it's a Python script, so that's always my favorite part is when we dive into the actual script. So what is a neural network? So hi guys, I heard you want to know what a neural network is. Here we have, looks like you just went shopping at a red tag sale. My robot's back. So as a matter of fact, you have been using neural network on a daily basis. In today's world, it's just amazing how much we use our new technology. We're not even aware of it. When you ask your mobile assistant to perform a search for you, like saying your Google or Siri or whoever you use, Amazon Web. Self-driving cars, so that's the newest thing coming out. They're just now trying to make those legal in different states in the US and around the world. Even in the UK, they now have self-driving cars going up and down the street. It's pretty amazing. These are all neural network driven. Computer games use it. So a lot of computer games are driven by neural networks in the back end as part of the game system and how it adjusts to the players. And it's also used in processing the map images on your phone. So every time you do a navigation someplace and it opens it up, they now use neural networks to help you find the quickest way to get there. Neural network. A neural network is a system or hardware that is designed to operate like a human brain. In today's development, this is so important to understand because we don't have anything else to compare it to. I'm sure someday in the future, the computer will redefine, or the neural network, or the AI, artificial intelligence, will redefine what these mean. But as far as we can today's world, in today's commercial development, we have to compare it to what humans do. So we want to compare how it operates to a human brain and how it solves problems like a human does. What can a neural network do? And really, we're just going to dive in deeper to what we just covered and look at other examples. So what can a neural network do? Well, let's list out the things neural networks can do for you. Translate text. Boy, we got Google Translate, and Microsoft has their own Translate. They have some really cool, they actually have an earpiece that's supposed to start translating as you talk. What a cool technology, what a cool time to live. Identify faces. Can you imagine all the uses for facial identification? In the case of our sample, or our code that we're going to look at later, we'll be identifying dogs and cats, so not quite as detailed as understanding whose face belongs to who. I'm waiting for the Google glasses to come out so I can see who's who and identify faces as I'm walking around, have a little name tag over them. Not out there yet, but boy, we are close. We can identify the faces, and they have all kinds of technologies to bring that information back to us. Recognize speech goes along with the translate text. So now as you're talking into your assistant, it can use that to do commands, turn lights on, all kinds of things you can do with recognizing speech. Read handwritten text. They're starting to translate all these old text documents that they've had in storage. Instead of doing it individually where somebody's going through each text by themselves in a room, you can picture like an old Raiders of the Lost Ark theme where he's in the back, archaeologist studying the text. Now it's fed into a computer. They take a picture. They even use neural networks to take a scroll that is so messed up that they can't undo the scroll, and they x-ray it, and then they use that x-ray to translate the text off of it without ever opening the scroll. I mean, just way cool stuff they're starting to do with all this. And of course, control robots. What would be a neural network without bringing in the robots? And we have our own favorite robot in the middle who goes to our red tag cell and goes shopping for us. So, these are just a few of the wonderful things that neural networks are being applied to. It's such an infant stage technology. What a wonderful time to jump in. And there are a lot of other things it goes into. I mean, we could spend just forever talking about all the different applications from business to whatever you could even imagine. They're now applying neural networks to help us understand. So now we talked a little bit about all the cool things you can do with a neural network. Let's dive in and say, how does a neural network work? So now we've come far enough to understand how neural network works. Let's go ahead and walk through this in a nice graphical representation. They usually describe a neural network as having different layers. And you'll see that we've identified a green layer, an orange layer, and a red layer. The green layer is the input. So you have your data coming in. It picks up the input signals and passes them to the next layer. The next layer does all kinds of calculations and feature extraction. It's called the hidden layer. A lot of times there's more than one hidden layer. We're only showing one in this picture, but we'll show you how it looks like in a more detail in a little bit. And then finally we have an output layer. This layer delivers the final result. So the only two things we see is the input layer and the output layer. Now let's make use of this neural network and see how it works. Wonder how traffic cameras identify vehicles' registration plate on the road to detect speeding vehicles and those breaking the law? They got me going through a red light the other day. Well, last month. That's like the horrible thing. They send you this picture of you and all your information because they pulled it up off of your license plate and your picture. I shouldn't have gone through the red light. So here we are, and we have an image of a car, and you can see the license plates on there. So let's consider the image of this vehicle and find out what's on the number plate. The picture itself is 28 by 28 pixels, and the image is fed as an input to identify the registration plate. Each neuron has a number called activation that represents the grayscale value of the corresponding pixel range. And we range it from 0 to 1. 1 for a white pixel and 0 for a black pixel. And you can see down here we have an example where one of the pixels is registered as like 0.82, meaning it's probably pretty dark. Each neuron is lit up when its activation is close to 1. So as we get closer to black on white, we can really start seeing the details in there. And you can see again the pixel shows us one up there. It's like part of the car, and so it lights up. So pixels in the form of arrays are fed to the input layer. And so we see here the pixel of a car image fed as an input. And you're going to see that the input layer, which is green, is 1 dimension, while our image is 2 dimension. Now, when we look at our setup that we're programming in Python, it has a cool feature that automatically does the work for us. If you're working with an older neural network pattern package, you then convert each one of those rows so it's all one array. So you'd have like row 1 and then just tack row 2 onto the end. You can almost feed the image directly into some of these neural networks. The key is, though, is that if you're using a 28 by 28 and you get a picture that's 30 by 30, shrink the 30 by 30 down to fit the 28 by 28. So you can't increase the number of input, in this case green dots. It's very important to remember when you work on neural networks. And let's name the inputs x1, x2, x3 respectively. So each one of those represents one of the pixels coming in. And the input layer passes it to the hidden layer. And you can see here we now have 2 hidden layers in this image, in the orange, and each one of those pixels connects to each one of those hidden layers. And the interconnections are assigned weights at random. So they get these random weights that come through. If x1 lights up, then it's going to be x1 times this weight going into the hidden layer. And we sum those weights. The weights are multiplied with the input signal, and a bias is added to all of them. So as you can see here, we have x1 comes in, and it actually goes to all the different hidden layers nodes, or in this case, whatever you want to call them, network setup, the orange dots. And so you take the value of x1, you multiply it by the weight for the next hidden layer. So x1 goes to hidden layer 1, x1 goes to hidden layer 2, x1 goes to hidden layer 1 node 2, hidden layer 1 node 3, and so on. And the bias, a lot of times they just put the bias in as like another green dot or another orange dot, and they give the bias a value 1, and then all the weights go in from the bias into the next node. So the bias can change. We always just remember that you need to have that bias in there. There's things that can be done with it. Generally, most of the packages out there control that for you, so you don't have to worry about figuring out what the bias is. But if you ever dive deep into neural networks, you got to remember there's a bias, or the answer won't come out correctly. The weighted sum of the input is fed as an input to the activation function to decide which nodes to fire and for feature extraction. As the signal flows within the hidden layers, the weighted sum of inputs is calculated and is fed to the activation function in each layer to decide which nodes to fire. So here's our feature extraction of the number plate. And you can see these are still hidden nodes in the middle. And this becomes important. We're going to take a little detour here and look at the activation function. So we're going to dive just a little bit into the math, so you can start to understand where some of the games go on when you're playing with neural networks and you're programming. So let's look at the different activation functions before we move ahead. Here's our friendly red tag shopping robot. And so one is the sigmoid function. And the sigmoid function, which is 1 over 1 plus e to the minus x, takes the x value, and you can see where it generates almost a 0 and almost a 1 with a very small area in the middle where it crosses over. And we can use that value to feed into another function. So if it's really uncertain, it might have a 0.1 or 0.2 or 0.3, but for the most part it's going to be really close to 1 and really close to, in this case, 0 to 1. The threshold function. So if you don't want to worry about the uncertainty in the middle, you just say, oh, if x is greater than or equal to 0, if not, then x is 0. So it's either 0 or 1. Really straightforward. There's no in between in the middle. And then you have what they call the ReLU function. And you can see here where it puts out the value, but then it says, well, if it's over 1, it's going to be 1. And if it's less than 0, it's 0. So it kind of just dead ends it on those two ends, but allows all the values in the middle. And again, this, like the sigmoid function, allows that information to go to the next level. So it might be important to know if it's a 0.1 or a minus 0.1. The next hidden layer might pick that up and say, oh, this piece of information is uncertain, or this value has a very low certainty to it. And then the hyperbolic tangent function. And you can see here it's 1 minus e to the minus 2x over 1 plus e to the minus 2x. And it's very much along the same theme. A little bit different in here in that it goes between minus 1 and 1. So you'll see some of these, they go 0 to 1, but this one goes minus 1 to 1. And if it's less than 0, it's, it doesn't fire. And if it's over 0, it fires. And it also still puts out a value. So you still have a value that you can get off of that, just like you can with the sigmoid function and the ReLU function. Very similar in use. And I believe originally used to be everything was done in the sigmoid function. That was the most commonly used. And now they just kind of use more the ReLU function. The reason is, one, it processes faster because you already have the value and you don't have to add another compute the 1 over 1 plus e to the minus x for each hidden node. And the data coming off works pretty good as far as putting it into the next level if you want to know just how close it is to 0. How close is it not to functioning? Is it minus 0.1, minus 0.2? Usually they're float values. You get like minus 0.00138 or something. So, important information, but the ReLU is most commonly used these days as far as the setup we're using. But you'll also see the sigmoid function very commonly used also. Now that you know what an activation function is, let's get back to the neural network. So finally the model would predict the outcome of applying a suitable activation function to the output layer. So we go in here, we look at this, and we have the optical character recognition, OCR, is used on the images to convert it into a text in order to identify what's written on the plate. And as it comes out, you'll see the red node, and the red node might actually represent just the letter A. So there's usually a lot of outputs when you're doing text identification. We're not going to show that on here, but you might have it even in the order. It might be what order the license plate's in. So you might have A, B, C, D, E, F, G, the alphabet plus the numbers, and then you might have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So it's a very large array that comes out. It's not a small amount of, we show 3 dots coming in, 8 hidden layer nodes, 2 sets of 4. We just show 1 red coming out. A lot of times this is, 28 times 28. If you did 30 times 30, that's 900 nodes. So 28 is a little bit less than that just on the input. And so you can imagine the hidden layer is just as big. Each hidden layer is just as big, if not bigger. And then the output is going to be, there's so many digits. It's a lot. It's a huge amount of input and output. But we're only showing you just, it'd be hard to show in one picture. And so it comes up, and this is what it finally gets out on the output, is it identifies a number on the plate. And in this case, we have 08-D-03858. Error in the output is back propagated through the network, and weights are adjusted to minimize the error rate. This is calculated by a cost function. When we're training our data, this is what's used. And we'll look at that in the code when we do the data training. So we have stuff we know the answer to, and then we put the information through, and it says, yes, that was correct, or no. because remember, we randomly set all the weights to begin with. And if it's wrong, we take that error. How far off are you? Are you off by, if it was like -1, you're just a little bit off. If it's like -300 was your output, remember when we're looking at those different options? Hyperbolic or whatever, and we're looking at the REL. The REL doesn't have a limit on top or bottom. It actually just generates a number. So if it's way off, you're going to have to adjust those weights a lot. But if it's pretty close, you might adjust the weights just a little bit. And you keep adjusting the weights until they fit all the different training models you put in. So you might have 500 training models, and those weights will adjust using the back propagation. It sends the error backward. The output is compared with the original result, and multiple iterations are done to get the maximum accuracy. So not only does it look at each one, but it goes through it and just keeps cycling through the data and making small changes in the network until it gets the right answers. With every iteration, the weights at every interconnection are adjusted based on the error. We're not going to dive into that math because it is a differential equation and it gets a little complicated. But I will talk a little bit about some of the different options they have when we look at the code. So we've explored a neural network. Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN, a neural network. Data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radio basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data, so you want to group things together and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together. And this is a great way, if you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohen's self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Alexa or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches like a filter. This allows a network to remember an image in parts. Convolutional neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so that it can do a face recognition on each person. Applications used in signal and image processing. In this case, I used facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, in individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohennon self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network, where it brings them all together. And no, the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here we have quite a variety of dogs in the pictures and cats, and just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras's website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python, although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the RELU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an RELU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup, and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn, pillow, and h5py are both needed for the TensorFlow and then putting the Keras on there. And then you'll see here, and pip is just a standard installer that you use with Python. And you'll see here that we did pip install TensorFlow, since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in Ubuntu server setup. You'd want to get, I don't think you need the h5py on Ubuntu, but you do need the rest in there because there are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda Navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case I'm using Google Chrome, and in here I could go and just create a new document in here. And this is all in your browser when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential. That's under the models because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense. And you can actually just kind of guess at what these do. We're working in a 2D photograph. And if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image. So it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph. You let the Keras do it. And we're going to run this, and you'll see right here they have some stuff that is going to be depreciated and changed because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this has just imported these packages for us to use. And Jupyter's nice about this that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control Plus. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between 2 things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. You're specific, it's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that is this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. That's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important because after that, Keras knows what your shape is coming in here and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember we talked about the different activations on here, we're using the ReLU model. Like I said, that is the most commonly used now because one, it's fast. It doesn't have the added calculations in it. It just says here's the value coming out based on the weights and the value going in, and from there, you know, it's if it's over 1, then it's good, or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in depth than we're ready to cover in this tutorial. But this is used to convert from the photo because we have 64 by 64 by 3 and we're just converting it to two-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our 2 hidden layers, and they are two-dimensional because we're doing with a two-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, 2. And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimensional instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. Classifier add a flatten setup, and then we're going to also add a layer, a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you. So we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a two-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole nother dimension to it of 3 different values. And we've kind of resized those down to 2 by 2. But now we're just going to flatten it. I don't want to have multiple dimensions being worked on by Tensor and by Keras. I want just a single array. So it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. out. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those different, the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pull it into units of 128. They got that. You're going to say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple of whatever the data shape you're already using is in. And we're using the activation, the RELU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the RELU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network. And we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the Atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on Atom anyway, so they just leave it on Atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually Atom is just fine on there. And then you have 2 more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways to on your back propagation and your training. So we're using the Atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them. And now we've set up our classifier. So we have an object classifier, and if you go back up here, you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the RELU for activation, and then it pulls the data. So this is, even though these are 2 layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2x2. So into a 2-dimensional array from a 3-dimensional array with the colors. Then we flatten it. So there's our adder flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the 2-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the RELU again. And then finally we reduce that down to just a single output, and we use the sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, back propagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have 2 data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from Keras, and let me just zoom in there. I always love that about working with Jupyter Notebooks. You can really see. We're going to come in here. We do the cross pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out. And since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here. We do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator, and we're going to rescale it. And you'll see here we have 1 point, which tells us it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. They're value from 0 to 255. So we want to divide it by 255, and it'll generate a number between 0 and 1. They have shear range and zoom range. Horizontal flip equals true. And this, of course, has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now, though, we're going to just stick with some basic stuff here. And let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter Notebook is saving things to that you create this path, or you can do the complete path if you need to, C:/, etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures. There's all kinds of different settings depending on what you're working with. Now let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to 1 classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing. We've done a train data generator. We've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1 over 255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. And we'll run that, and you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data and making sure it's going in there correctly. And we're actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our back propagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course we're using the training set. Remember, we created the training set up here, and then we're going steps per epoch. So it's 8,000 steps. Epoch means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epoch 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, It says epic 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. That was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epic 8,000, 25 epics, and validation steps 2,000. And I changed these to 4,000 epics, or 4,000 steps per epic, 10 epics, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epic, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epic, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epic. And the epic is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epic, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epic 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epic, and that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epic times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days. A couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor, runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down, and the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACC is for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epic. What's our accuracy at the end of the epic? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Recurrent Neural Network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter notebook. All right, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as a return for the data array. Although, you can use a standard data array from Python. And we have cross, pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the cross processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, we're going to cross is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import NumPy as NP. Expand the dimensions, test image, axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here, we go result equals classifier predict test image, and then we find out, well, what is the test image? And let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog, and if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab. Friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one, because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos. And those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with. So, key takeaways. Well, we covered what is a neural network. We use all kinds of processing, the map images on your phone. We talked about things that a neural network can do. Translate text, identify faces, all the way to control robots. Lots of exciting things. How does a neural network work? So we discussed that with the different layers, going from the picture to the input layer, to the hidden layers and their weights, to the final output layer. We also talked about how it does the math and computing the output as yes or no, categorically true, false. We discussed types of artificial neural networks. A lot of vocabulary there from the feed-forward neural network, which is the most commonly used. That's the neural network we used is a feed-forward neural network that does backward propagation to train. And there's a lot of other ones out there. There's the radial biases, the Cohennon self-organizing recurrent neural network, convolutional neural network, modular neural network. The big one was modular because it incorporates pieces of all the other ones so that whatever you're working on now is a huge conglomerate of multiple networks. Just all cutting edge. All of it's new. People even working on it don't even know where it's going. Again, very exciting times. And finally, we dug through my favorite part. You can see with my latte on one side, my old school pens and pencil and all my sticky notes working away. That's not actually me, by the way. You probably guessed that. And we walked through and actually did a cat and dog photo, a simple cat and dog photo, and you could see where some of the problems are in processing large amounts of photographs and data, where that starts to become going from a single machine on my laptop with its lower amount of resources all the way to big data. How if you're processing hundreds and thousands of these photos, this now needs to be set up on an enterprise machine or even on a cluster of computers. Again, significantly past the scope of this. The neat part about it, though, is once you write this code, most of this code, they now have tools that you can almost take the same ideas, if not the actual code, and push it right onto a cluster computation. So really cool times for this. Python. My name is Richard Kirschner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Although deep learning has been around for a while, it is just in its infant stages of development as far as exploding on the market. I mean, it is. Right now, they're building robots with it. Deep learning is used to train robots to perform human tasks. Music composition. Deep neural nets can be used to produce music by making computers learn the patterns involved in composing music. Image colorization. Neural network recognizes objects and uses information from the images to color them. Machine translation. Given a word, phrase, or a sentence in one language, neural networks automatically translate them into another language. Google Translate is one such popular machine translator you may have come across. And you'll notice in here we didn't show any examples of straight numbers like projective cells in a business, tracking your favorite stock. You can certainly do those with machine languages, but this is the next level. Save that for your regression models, your linear regression, where you're actually processing and crunching just straight numbers. With machine learning and deep learning, we're going to a whole new level as far as what we can figure out on the computer. What's in it for you? We're going to cover what is deep learning. We're going to take a look at the biological versus artificial intelligence. What is neural network? Activation function in your neural network, and the cost function, and how do neural networks work? How do neural networks learn? So there's you'll see a switch right there. We just went from how are they working in the math in the background to exactly how are they learning. We'll be implementing the neural network. We'll do a gradient descent, deep learning platforms, and we'll give an introduction to TensorFlow and implementation in TensorFlow. That's Google's platform that they open sourced recently, and it's probably one of the most cutting edges in deep learning. And even it is still in the infant stage, which is one of the reasons they released it to open source. What is deep learning? Deep learning is a subfield of machine learning that deals with algorithms inspired by the structure and function of the brain. And you can see we have a nice picture here. We have artificial intelligence, which is kind of the big bubble that encompasses all these different things we're talking about. This is the ability of machine to imitate intelligent human behavior. And in there we have machine learning, application of AI that allows a system to automatically learn and improve from experience. And if you looked at any of our other videos, you'll know that machine learning covers a lot. So deep learning is a subcategory of that, but don't forget machine learning has all kinds of other tools that people use to do very basic descriptive and predictive and postscriptive analytics. And then you have deep learning, application of machine learning that uses complex algorithms and deep neural nets to train a model. Let's take a look at the biological neuron versus the artificial neuron. Now remember, in the human brain, and this is true for most animals, there are a lot of different neurons going on. So this is the very basic one. I mean, there's hundreds of different cells involved. So when we talk about neural networks, and this is why I say it's in a very infant stage, they're really basing it on just the most basic thing that we're able to figure out going on in the neural networks. And you can see right here we have dendrites fetch information from an adjacent neurons and pass them on as inputs. So you have your data coming in and your data going out. Any computer model should be looking at that. What's coming in, what's going out. The data is fed as an input to the neuron. So when we look at the artificial neuron, you can see we have our inputs. They come in, each one is specially weighted into the neuron, and then the neuron has an output. The cell nucleus processes the information received from the dendrites, and the neuron processes the information provided as inputs. Axons are the cables over which the information is transmitted, and the information is transferred over weighted channels. So you can look at that, I mentioned weights briefly, but you alter the data coming in. So those weights are what causes different information coming in to be weighted differently and processed differently. And the synapses receive the information from the axons and transmit it to the adjacent neurons. That's in your biological model. And then when we look at the artificial neuron, the output is a final value predicted by the artificial neuron. So as we dig deeper into looking at the theory behind the neural network, and we kind of flip back and forth between these because there's two huge aspects of it. One is from the outside, what are you seeing, and what's going on from the inside, so you can find to do what you need to do and give the best results you can. And we start off with what do we feed? We feed an unlabeled image to a machine which identifies it without any human intervention. And so you can see here we have a circle that comes in at 784 pixels, and it comes in by 28 by 28. And you can see how it colors in the circle on there. And we put a triangle in. The triangle in also comes in as 28 by 28, and it has 784 pixels. So you'll see between these two, both of them are 784 pixels. This machine is intelligent enough to differentiate between the various shapes. So that's what we want to use our neural network to do, is to say, hey, this is a circle, this is a triangle. And that's more of a categorical. You can also do a regression model where you're actually putting out a float value or a numerical value. We'll be looking at the true-false or the categorical model mostly, because that's where you usually start at. There is no real difference when you, as far as the way the internal functioning goes, when you start flipping between them, other than, well, we'll talk about that in just a minute. So you can actually go between the two quite easily. And the neural network provides this capability. So we're going to use this capability to look between those two. One of the things I want you to note in here is that we're looking at 784 pixels. We're looking at 784 inputs. That's very different than stock with a high-low, or last year's cells based on date, where we're looking at just a couple of numbers, and they're very clear, they're numbers, they're very clear what they are, which is something you'd put into a machine learning linear regression model. This is a step up from that in that we're looking at complex patterns, and how do you figure those complex patterns out. So a neural network is a system modeled on the human brain. And we looked at that, comparing the two. Let's go ahead and look deeper into the neural network itself. We have our inputs coming in. So the inputs are fed to a neuron that processes the data and gives us an output. Input and output. This is the most basic structure of a neural network known as a perceptron. So if you see the term perceptron, that's what we're talking about. We're talking about this single node that has inputs and an output. However, neural networks are usually much more complex. Let's start with visualizing a neural network as a black box. And I always love that symbol. It's a black box. It's kind of magical. We have our inputs coming in, and we want certain outputs. The box takes inputs, processes them, and gives an output. Let's have a look at what happens within this box. And you can see me there in my secret agent getup. I got my hidden hood and everything. I guess I'm part of the Black Skull or something like that group. So let's take a look at what happens within this magic box. And remember, we're skipping back and forth between the theory of what's going on in the box, which you have to know how to fine-tune and how to build, versus looking at it from the outside. We're programming this box, and we have an input and an output to the box as a whole. Within the box exists a network that is a core of deep learning. And you can see here we're showing one layer, and we have our grid coming in. The network consists of layers of neurons. Each neuron is associated with a number called the bias. And you can think of the bias, if you overly simplify this, and we're doing a linear regression model, this is your y-intercept in your Euclidean geometry. You have to have something that offsets it, and so you always have a bias in these cells. Neurons of each layer transmit information to neurons of the next layer over channels. And so you can see each of our layers going through from left to right. These channels are associated with numbers called weights. These weights, along with the biases, determine the information that is passed over from the neuron to neuron. So just like the bias is your y-intercept in Euclidean geometry, you could look at the one weight. remember this is very complicated, so we're not looking at just one weight. You can look at the weight as your slope of the line. Or if you're doing x equals my plus c, it would be the m value. Neurons of each layer transmit information to neurons of the next layer. And you can see here as they light up going across into the final layer and then to the output. And in this case, the output is going to be either a square in this one, or it might light up the other one, which is a circle. The output layer emits a predicted output. So in this case, we're looking at a classification, true, false. Is it a circle? Is it a triangle? Is it a square? Let's now go deeper what happens within the neuron. So we're going to dig deeper and start getting a little bit closer to some of the math. Don't worry, you don't have to be a calculus expert or know your differential equations. Even though this is one giant differential equation, you don't need to understand those to understand what's going on. Within each neuron, the following operations are performed. The product of each input and the weight of the channel it's passed over is found. This is simply addition. We're going to sum up the weight times the output from the previous channel, and plus the bias. Sum of the weighted products is computed. This is called the weighted sum. Bias, unique to the neuron, is added to the weighted sum. The final sum is then subjected to the particular function. And we'll discuss that particular function. That part is really important because those functions have a huge impact on how well your model performs under different conditions. The final sum is then subjected to a particular function. This is the activation function. So if you ever hear the term activation function, that's what we're talking about. What activates this cell and what doesn't. As we dig deeper into activation function, an activation function takes the weighted sum of the input as its input, adds a bias, and provides an output. And a lot of times you'll actually see one formula for the sum of the weighted sum and the bias. You'll just see that as a single line of everything added together. In here we've broken it apart because it makes it clear that this bias is not computed the same as the weighted sums. Here are the most popular types of activation function. And I always find these interesting because at one point I was sitting at a table with a gentleman who was finishing his PhD. He was in his last year, and he said he went through all this stuff and he ended up just trying the 4 different activation functions on this particular problem he was working on. So knowing the math behind it doesn't necessarily mean you're going to know it right away. So even somebody who might have a PhD and be doing the calculations on this comes back out of it and ends up just trying the different activation functions to see what's going to make a difference. And a lot of times that's a final step. That's the kind of thing where you built your whole model, you've come back and you're like, wait a minute, can I do a better deal with the sigmoid function or the threshold or the rectifier? Knowing what they're doing is important so you can explain it to somebody else. And again, you probably do this on a small set of data. If you're working with big data, you don't want to take down the full server farm just to test out your 3 different series. You take a small portion of that data, test it, and then you put it through to the big data. So let's take a look at this. We have the sigmoid function, and it's used for models where we have to predict the probability as an output. It exists between 0 and 1. And you'll see that's true of all of our activation functions we're working with. Either the cell's on or off. It's true or false. And there might be a little variation in there, which as an output could be used to compute uncertainty in your solution. So if you're getting a 0.7 with this activation function, it might be, well, I'm not sure if that's really a square, or I'm not sure that's really a triangle. And that might be a flag for it to be looked at by a human observer, at least in today's models where we're at right now. And you can see here where we have the formula is simply equals 1 over 1 plus e to the minus x, where x is your value coming in, and it's going to give you a result that looks very similar to the graph on there, which is somewhere between 0 and 1, and right in the middle you can see that there's a huge you can go through all the different values and uncertainties involved. So the sigmoid function is probably the default on most of them. The next one is the threshold function. It is a threshold-based activation function. If x value is greater than a certain value, the function is activated and fired, else not. Pretty straightforward. Yes, no, true, false. I don't want to test for improbabilities. I just want a straight answer. I don't want to know if there's a partial value on there. It either is true or it's false. And the rectifier function, it is the most widely used activation function. I would debate that. Rectifier is a pretty common one, although I see the sigmoid function used to be the basic one, but it's up there. The rectifier function is very commonly used. It gives the output of x if x is positive and 0 otherwise. And you can see here, again, just like it's either kind of get a value going up there. So max of x of 0. So it's like the threshold function. Yes, no, true, false. It's either 0 or it's some kind of progressive value. And then we have the rectifier function. I would argue with this because the sigmoid function used to be the most common one, but with the rectifier function, it now says it is the most commonly used or widely used activation function and gives an output of x if x is positive and 0 otherwise. This is kind of nice because it now says absolutely not, or it gives you a value of probability. Now when I say a value of probability, be very careful there. I'm not saying that it's going to tell you this is 75% chance of being a circle. I'm going to tell you that it says, hey, if this says 0.1, it probably needs to be looked at, or 0.2 or 0.3. It's going to depend on your data as to what that value means. In general, that just means it's flagging it that if it's not a 1, then chances are it needs to be looked at by a person and reevaluated. And there's a hyperbolic tangent function. This function is similar to sigmoid function, is bound to a range of -1 to 1. So you can see there's our 1 minus e to the minus 2x and 1 plus over 1 plus e to the minus 2x. Again, it's very similar to the sigmoid function. The bonus of the hyperbolic function is you have that variable coming through the middle. So again, you can look at it and you have a little bit more weight as far as you can process that down the line. That's a little bit more advanced than what we're looking at right now, and a lot of times it's not even necessary in a lot of our different uses for these activation functions. Now, we looked at activation functions, and I kind of said those are a little bit like a black box, because even if you know all the math, a lot of times you end up just playing with them to find out what works, and it also depends on what model you're working with, whether you need a flat yes, no, true, false, or you need to have something in the middle that says, hey, this isn't quite a 1, you might need to process this with the human intervention. And you can look at that. One example would be self-driving cars. You don't want a car to be yes, no, I'm going to go through the light. You want it to be like, okay, if it's almost yes, maybe we stop and have human intervention so we don't get an accident. Cost function is something you can really see and measure and is very important. The cost value is the difference between the neural net's predicted output and the actual output from a set of labeled training data. So we have our group of data that's a square, circle, and since we're looking at geometrical shapes, we've had somebody already labeled that data. They've already said this is a triangle, this is a square. And so if this is coming up and it's giving us and it's saying a square is a triangle and it's saying a triangle is a circle, the output is wrong. And so that output can then be measured versus the actual output, and that's the cost. You might also hear this as error, because that's the error value being returned. How far off is it? And what we're looking for is the least cost, or the least error value, and it's obtained by making adjustments to the weights and biases iteratively throughout the training process. And this is called back propagation, and we're going to look in that a little deeper as we look into an example. It's really hard to see when you're just looking at arrows without actual numbers and where that flow is coming from. But you can look at this as here's our inputs. They put out a prediction. The prediction comes out and says, hey, we've already labeled this data because we're in training mode, and the training data is off. This is the cost. Can we send that error or that cost back and adjust those weights? And we do it in very small increments across large amounts of data so that those weights minimize that cost or that error. But what happens within these neurons? So let's look at a little example of this. Kind of helps if you have some kind of visual. Let's build a neural network that predict bike prices based on a few of its features. And we'll see here we have our CC, our mileage, and our ABS, and these are our 3 input layers. And then we have the bike price and the output layer. Now, it doesn't do us very good to just pump it in from the beginning and pump it out. And to be honest, I would use a machine learning linear regression model on this, since these are just straight numbers. But because we want a simple example, we're going to put this through and show you as a neural network what that looks like. And we got to put a hidden layer in there. The hidden layer helps in improving the output accuracy. And you could look at this as a bunch of ORs. So it might say, hey, when we compare these 3 values on the first hidden layer neuron, we're looking at one set of features, and then we might weight them in the second one. So these are a bunch of different ORs, kind of how the math comes out and behind the scenes. And then they go out, of course, to the bike price or the output layer. And each of the connections have a weight assigned with it. And you'll see here we have mileage CC with the weight 1 and weight 2 going into our first neuron. And you'd also have your ABS going in there. And so x1 times weight 1 plus x2 times weight 2 plus the bias of 1. And step 2 is our activation. The activation function coming in there. When does this fire? And the neuron takes a subset of the inputs and processes it. And then we go through and we do that with the second hidden layer neuron and the third one and so on. So you process each layer in order going forward. Now, when I told you this is in its infant stage, they now have neurons that fire into the same layer or back a layer, so that you now have a time series, and there's all kinds of wild things that they're experimenting with on these layers. This basic setup has been around since the mid-90s. It's only now, because of our technology, that it's open to almost everybody to play with it, and that's why I say this is in an infant stage in development. Is this basic math is here, but what we can do with it is amazing, and what they're actually doing with all these different things is amazing. And so we're just at the beginning of how to use all these different tools in our deep learning and our neural networks. And so once we have our hidden layer computed, the information reaching the neurons in the hidden layer is subjected to the respective activation function. And so each one of these fires an activation output, and then those are each weighted to the final output layer. So the processed information is now sent to the output layer, once again, over weighted channels. And you could look at this as each one of these is, I always look at this as like a group of people. They're all looking at the bulletin board, and the first person says, this is what I project sells for the company, and the second person, and the third, and so on. And then their perspectives are weighted based on their expertise. So your accountant might have a very high weight, where the maybe your janitor has a very low weight, because their expertise is not in accounting. And then that goes into the output layer. And once in the output layer, it goes, the output, which is the predicted value, is compared against the original value. So now we have our output layer, and since we have like already a list of bikes with the different setups and what their value is, we can now generate an error from this. The cost function determines the error in prediction and reports it back to the neural network. So this is the cost. This is how far off it is. This is your error coming back. And as you can see, this is back propagation going on. So now our error is going in reverse, because we know we're not completely correct on this particular channel. The weights are adjusted in order to reduce the error. So each time we go back, we are changing those weights to reduce that error, and we change them in small increments. You don't want to fit one input. Remember, you might have a data pool with a terabyte of data. You don't want to solve for the first set of data that comes in and that be the main solution, because everything else will be off. This is going to confuse you. That's also called a bias. So we have the bias in the cell where we're adding a value, the kind of like the y-intercept, and we have a bias of the whole neural network, which means that it's weighted towards one set of answers. So we want to make small changes in these weights so we don't create a bias. And the weights are adjusted in order to reduce the error, or the cost. The network is now trained using the new weights. Once again, the cost is determined and backpropagation is continued until the cost cannot be reduced any further. So let's go ahead and plug in values and see how our neural network works. So here we come in here, and initially our channels are assigned with random weights. This is important because if you assign them all with the same weight, you might be able to reproduce it, but it turns out that if I put all my weights as 1 or all my weights as 0, it takes longer to train. Where if you have random weights, they already have like a little bit of adjustment and ORs built in, and that will give us a better answer and train faster. Our first neuron takes a value of mileage and CC as inputs. So here comes our computation, whatever those inputs are, and we do that again with the second neuron with those values coming in. You can see here we have weight 3 and so on, and then our third neuron coming down, and of course our fourth neuron. So we're adding all these different values coming in here in our hidden layer. The processed value from each neuron is sent to the output layer over weighted channels. So again, here's our weights coming in, and we have N1, N2, N3, and N4. Once again, the values are subjected to the activation function, and a single value is emitted as the output. On comparing the predicted value to the actual value, we clearly see that our network requires training. So here we have it that our bike price we put out, we thought it was worth $2,000 on our random weights, and the bike actually was $4,000 on there. I'm guessing that's not US dollars, because that'd be a very expensive bike, but maybe it is. There's some $2,000, $4,000 bikes out there. The cost function is calculated and backpropagation takes place. And this is pretty simple. You can look at that as our, we're subtracting one value from the other, we square it, and then we take half of that. And that is propagated back up, and each layer generates its own errors. Let's go back one, because you have your predicted Y and your actual Y. That goes back to the first layer. And then then based on the value of the cost function, certain weights are changed. So when we look at the next layer, that error is not the original 4,000 minus 2,000 squared divided by 2. This error is based on the error of each cell generated. How far off is that cell as far as its weights? We're not going to show you. It's actually a very complicated differential equation, and you can probably write it out if you wanted to. You just write out each formula. That goes into the next level, and you add them all together, and you can write it out all the way through. Computers make it so you don't have to. And our neural network is considered trained when the value for the cost function is minimum. So when we get our error way down as low as we can, that's when our neural network is trained. And just recently they've come up with all kinds of different means for measuring that particular value. A little bit beyond the scope of today's neural network, but you can actually see it. How far do you do this until the neural network doesn't need to be trained anymore, and you can overtrain a neural network. Now the tools that we're looking at automatically let you know when to stop, which is really nice. And that is just, like I said, we're at the beginning stages in neural networks, and it's just really cool what they can do now, and how much of it's automated, and how much of it is experimental right now. Let's take a look at gradient descent. But what approach do we take to minimize the cost function? So here we have a nice error thing coming in. This is our cost or our error. Let's start with plotting the cost function against the predicted value. And so you can see they fed in multiple y's, and these are the errors coming in and the cost of each of these inputs and changes going on. Note, we start at a random point on the curve. So usually you put in, you pick up your data and you randomly pick where to start in your data. A lot of times you just run it from the beginning because you're going through so much data, it's not that big of a deal, but you start with one point going in. So your forward propagation goes through, you're going to go ahead and find your cost or your error. It points that on the curve, and you can see how we're plotting it right here. Since the gradient at this point is positive, we may move right. So we're going to move a little bit to the right on here. And this time the gradient is negative, we move a little bit to the left. Eventually we try out the point where the gradient is 0. This is the least value of cost function. You have to be a little careful with this because this particular, they make it look nice and simple in this graph. Sometimes these curves look like stair steps, and so there is global minimums and then there is local. There might be a local point where the gradient is 0, but it's not the global one. So it might be way off to the left where it just happens to step down a little bit and you think you're in the right gradient. And with that we have all the right weights and we can say our network is trained. So here we have just some major, these are some of the big names out there right now in development for deep learning platforms. TensorFlow, which we'll actually do an example in a minute. Deep Learning for J, which is in the Java platform. So if you're a Java programmer. By the way, as TensorFlow is accessed, most people are using Python to access it, but it is a system that's kind of separate from a lot of the programming languages, which makes it a lot more flexible as far as use. Deep Learning for J is Java based. And then Keras is just exploding right now. And this is interesting. Keras is working with TensorFlow. It actually can sit on top of TensorFlow and it can also do its own thing. So if you're studying deep learning, you're getting into it, you want to know the basics of TensorFlow, but you also are going to want to know the upper level of Keras sitting on top of TensorFlow. We're just looking at TensorFlow today though in our example. And there's also Torch on there. There's a bunch more that we didn't list on here. Even sklearn or the side package in Python has a neural network you can program, a very basic one. And it is the same basic one that you could do in TensorFlow if you stripped everything out of it, and then TensorFlow has a lot of tools they've added in, and so has Keras. But we're going to be looking specifically at TensorFlow in our example. And TensorFlow is an open source tool used to define and run computations on what they call tensors. Very common language now. So more and more we see the term tensor as being a standard in the deep learning language. And this was originally developed by Google. So let's take a little bit big in there. What are tensors? Tensors are just another name for arrays. So a tensor of dimension 5. You can see here we have A, B, K, M, Q, whatever. So it's an array coming in. And the tensor of dimension 5, 4, more like a picture. Very common to see that in a picture. You can also see a tensor even more detailed in a picture as we go to the next one, tensor of dimension 3, 3, 3. This is 3D space. You might have a picture that also has colors. That might be the third dimension. You might have 4 dimensions because you have both your grid and your different color channels and your z-plot, you can see where you can now process a very high level set of data coming in, whether as an image or features. They could be features that have nothing to do with images. So there's a lot of stuff you can do now with the tensors coming in. Thus is where the term TensorFlow comes from. So we have right now that TensorFlow is the most popular library in deep learning. And I did mention Keras now works with TensorFlow. So there's a lot of stuff you can do between the two. It's an open source software library developed by Google. So they hit a roadblock and they realized, hey, this is an infant stage technology. You know, we thought it was going to be the next greatest thing and we were going to have a hold on it, but it's really infant as far as how it's applied and what we can do with it. Let's open source it so everybody can work on it. Let's take it to the next level. And that's really what open source does to a lot of these packages when they release them. And you can run on either a CPU or a GPU. So when we look at the details, if you have your graphic processing units, what's nice about those is they run a lot faster. The downside is you have to play with them a little bit to get them up and running, and it's a hardware upgrade. When we run it, I'll be running it in the CPU mode. I have played with it in my GPU on my personal computer. You know, it does increase the processing, but I did run into some version problems with my Python and stuff like that. And when I did finally work it out, I went back to the CPU because it didn't increase my speed enough for what I was working on. But in a larger group, you might be able to put that on. If you're working with a larger stack of computers, you might want to run it in the GPU. You can create a data flow graphs that have nodes and edges. So there's our edges coming in. We didn't talk about edges, but that's a very up and coming way of looking at your analytical data is how do different nodes connect? What do those edges look like in between them? And it's used for machine learning applications such as neural networks. It is mostly a neural network, but they have all kinds of tools which sit on top of our basic neural network. They have new stuff evolving into the TensorFlow library. So it's very much just exploding. Great time to jump into TensorFlow because there's all kinds of cool things they're doing with it and all kinds of cool applications you can now use TensorFlow for. So let's take a look at implementation in TensorFlow. And we're going to build a neural network to identify handwritten digits using the MNIST database, or the MNIST database. And that stands for Modified National Institute of Standards and Technology Database. It is a collection of 70,000 handwritten digits, and the digit labels identify each of the digits from 0 to 9. This is a cool example because it's simple enough that you could actually run this through some basic machine learning categorizing algorithms and train them. And you'll get about the same answer because, again, it's simple grid. The digits on the grid don't have a huge amount of variation like you would, say, an automated driving car looking at the environment. So you could still do this with a lot of your different linear models and stuff like that. You can solve this and you'll get about the same answer. When I ran a comparison between TensorFlow and between some basic regression models or category models in machine learning, they came up pretty even as far as their output. So this is kind of where we start to see the complexity of something coming in this case a tensor, or a grid of information, where the deep learning model does as good as the regular models. And when you get past this kind of complexity and features, suddenly the neural networks come up with better answers, better solutions, and a better build. And that's why there's such a move into neural networks, is we live in a complicated world. And it's just really cool what we can do with this. So the handwritten digits from the NIST database, they come in, the data set is used to train the machine, a new image of a digit is fed, and the digit is identified. And if you've looked at any of our other machine learning tools where we're doing training, where we train our model to fit and then you test it out, this will look pretty familiar. And there is some tools out there for, say, untrained categorizing, where it's just looking for features that fit together. So there are tools that don't need that training. But this is where, when we talk about neural networks, we do need to train them, and this is what we're looking at. So for this, I'm going to use the Anaconda Navigator, just because it's a very nice visual tool. You might be in PyCharm or one of your other IDEs for editing Python, because we are looking at Python TensorFlow. And under Anaconda, we have the Notebook, which is something we use pretty regularly, and they have the Jupyter Lab. The Jupyter Lab is the Jupyter Notebook, but with tabs and a few new features. So we'll be using the Jupyter Lab today. And under the environment, you'll want to go ahead and if you haven't yet, you'll see that I have a number of different setups in here. Right now I have the Python version 3.6 and the TensorFlow. In this case, I have TensorFlow 1.12. If we scroll down, you can see that. Here we go, TensorFlow, and it's version 1.12. And in here, if you haven't yet, you'll need to install those and go in and just open our terminal. And if you've never used the Anaconda, or if you're in your other thing, you might have something simple like pip. Conda is what I use for my install, and you can simply do conda install TensorFlow. And that should bring in the most current version. Now, when I installed this a few months ago, Python version, I'm not going to run this because I already have it installed on here, Python version 3.7, the newest one out, still had a couple glitches with the TensorFlow. I believe they've fixed it as of writing of this, but I'm going to stick with 3.6 just so I don't get any surprises on there. So this is Python version 3.6 with TensorFlow 1.12 on here. And if you haven't installed it yet, you also want to install NumPy for this example. That's numbers Python, or NUMPY. You can just simply run an install on there. Keep in mind, if you're in Anaconda and you've created one of these environments specific to this, keep with Conda. If you're going to use Conda. If you're going to use pip, keep with pip. Don't install one package with pip and one under Conda, because that's how they track those version numbers and how they fit together, and you can end up with a problem. Pip doesn't see Conda and vice versa. So just keep that in mind when you're running your installs. We'll go ahead and open up Jupyter Lab, and we're going to launch that. So here's my Jupyter Lab. One of the really cool features of Jupyter Lab is you have tabs now, so you can open up multiple notebooks. And this is nice because I have my notes I'm working on and then our actual window we're looking in. And we'll go ahead and zoom in a little bit here. There we go. So you have a nice, hopefully easy to see fonts. And then we'll go ahead and do a simple, or get our imports out of the way. And so we're going to import our TensorFlow as TF. That's pretty much a standard for TensorFlow. NumPy, our numbers Python, as PY, and we'll import our matplot library as PLT. Again, these are very common. So if you see TF or PY or PLT, this is a standard that most people use. Do you have to? No. You could just do import NumPy instead of doing as PY. And then from TensorFlow.examples.tutorials, this is always nice because they actually include data set we're going to play with. So we're going to import input data. So there's our data coming in. That's all we're doing is telling it this is where it's coming from. And if we're going to tell where it's coming from, we need to go ahead and create a variable with that information in it. And we'll just call this MNIST or minced. You know, I don't really know how they pronounce that. I should probably look that up. It's a very common data set to use. And there's our input data, and we're going to read data sets. And this is, if you look at this, we imported input data from our TensorFlow. And so this is a TensorFlow read statement for their tutorials. So this isn't like some special Python setup. This is just their setup. It makes it easy to pull it in. So once we get into their data sets, we need to go ahead and tell it what kind of data set. And again, this is what we brought in, but it's going to be the NINST data. And this part is very important. One hot equals true. This means that instead of importing a value from 0 to 9, we evaluate the data set, it's going to bring it in as one hot. Whenever you see one hot encoder, we're flattening that out, and we have true false for 0, true false for 1, true false for 2. So our output, if you remember from our output from the slide we did earlier, in this case I grabbed the one for bike price. Doesn't really matter which one we use. This has one output, so we have our bike price. On this, we're going to have, instead of one output, we're going to have 10 outputs representing each of the digits in there. And this code really isn't going to show us anything. It's good to see what we're actually looking at. So let's go ahead and do a figure. AX equals, go into our plot library, subplots, 10, 10. And that is, if you remember, we talked about tensor being data coming in. This is a 10 by 10 grid, or 100 pixels on there. And if we're going to display it, let's go do K0 for I in range 10. Just a simple loop through on the data. Let's do, what is it, for J in range 10. So I actually misquoted that. 10 by 10 is not the actual size of the pixels. The actual pixels are going to be, when we look at the shapes, and we'll get into that in just a second here. We'll take a quick look at the shape on there. Turns out they're, they are, I believe, 28 by 28. So let's take a look at that. And we're just going to plot these. What are we looking at? What are we working with? As a data scientist, you should always be looking back at your data and seeing what it looks like and get that human perspective, because you just never know. You know, the computer might put something out that makes no sense, and at that point you want to go back and reevaluate what you did. So we're going to go ahead and plot. We're going to plot 10 of the digits by 10 of the digits, and here's our AX. We'll create the IJ on our subplots, and we're going to do an image show. We're going to look at the training image for images of K. And then we want to reshape this. We're going to reshape this, and we're going to reshape this 28 by 28. That's how I knew I had it wrong, is because I looked down my notes and I was like, oh no, that says 28, it's not 10 by 10. And I should know that already because I've done enough messing with this data set that I should have remembered. But it's 28 by 28, and the aspect we're going to do is auto. And this is all, if you look at this, here's our variable NIST. The NIST is coming from data set. So this is all part of the TF TensorFlow learning or examples tutorial in there. And then we'll go ahead and do K plus equals 1. So we just keep paging through our different images. And let's see what that looks like. Let's go ahead and do a plot show. And we'll go ahead and run this so we can take a look and see what we have here. And so we have a nice plot here, and you can just see that we have some random numbers showing up in each one of these little subplots. If you're wanting a copy of this code, put a note down in the YouTube video and let us know, or come visit us at www.simplilearn.com, and we'll send you out a copy of what we're working on. You can get a copy of that for your own setup. So now we've taken a look, and we can just see we have here's our pictures that are coming on. We've plotted them, so we have an idea of what we're looking at. Let's go ahead and let's look at the shape of the features. So when we have this, we have our NIST train images, and we'll do the shape on there. Let's take a look and just see what we're looking at as far as our count and everything. And so you can see here we have 55,000. That's basically how many images we have, and this by 784. And in this data set, there's also our labels. So let's take a look at that. We have our NIST train labels shape. Let's take a look and see what that looks like. And there we have 10, because there's 10 digits. So we brought in, that's our output we're looking at. And so we have, there we go, 55,000. They match. They should match, because you should have equal numbers in both of those. You know, here's our data in, and here's our answer. If you remember, this is a bunch of zeros, and with one, each one will be 0001, would be what, letter 4 or something like that. So let's take a look at what our one hot encoding did for the first observation. And this is, when we're exploring data, you really want to dig in there and just see what the heck am I looking at. So we're going to look at the labels, and this would be the first label that comes up, and we'll go ahead and run this. And we look at that, you can see this is what I'm talking about. 0, 0, or 1 is 0, 2 is 0, 3 is 0, 4 is 0, 5 is 0, 6 is 0, 7 equals 1. So our very first label is a 7, but our very first label comes up that it's a 7. And so we don't have like 0 through 9. We have a bunch of zeros and just the 1 to mark it as a 7 on here. So now we've kind of looked a quick look at the data. And in here you might ask some questions like, what is 784? 24 times 24. Remember, that's the size of our grid on there, or our tensor coming in. So 784 is the setup on there. And we've gone through all this viewing the data. We'll go ahead and start looking at our TensorFlow. So let's take our X variable. This is going to be our training set. We'll do a placeholder, and then we're going to have these come in as float. Now, if I remember correctly, they're actually, 0 or 1 for the values, because they're either, but we have them coming in as a float value, and we have a little bit of a shape coming in here, and there's our 784. So we let it know that this is what our input is for our TensorFlow, and this is our training set. So we'll just put a label on there to help us track that, train set, and then W, and with W we'll go ahead and do TF variables, and we'll do this as zeros. Variables, TF zeros, and we'll set this as 784 by 10, 10 being the output, 784 being our number of variables in, and this is our weights. Remember, we have a bias in there too. And I'll go back over this in just a second as we see how that fits together in our TensorFlow. And we'll do this one with our variables. Again, we have 10, so we're going to do the bias. We're going to do it the same kind of format and setup on here. And so we'll do that as TF zeros of 10. So we'll just create an array of 10 there, and this is our bias. So with these 3 lines, and they're coming out with the eager execution, which would bypass some of what we're doing. But this is important to understand, is the first thing you have to do with TensorFlow is we have to allocate a space for the variables. In our TF placeholder and our TF variable with our weights and our biases, this actually hasn't done anything yet. So all it is placeholders. That's why it's okay to use zeros. You could have just as easily used ones or anything else and it wouldn't matter. The next stage is to go ahead and set up some of the functions going on. But before we do that, just note that this hasn't done anything. Even if I execute it, all it's done is created placeholders until we do the final initialization. And so we need to go ahead and set up, we'll do y equals tf.nn.softmax. And the code for this is tf.matmul xw plus b. And this is our sum. Let's just put a note here so we can keep track of what's going on. We're finding weighted sum of inputs plus the bias. So there's our plus b, the bias. And then we need to go ahead, let's do y underscore, and again another placeholder. And this one will set, it actually will put in as tf placeholder on here. tf placeholder float none 10. There's our one hot encoder going on there. So our 10 values coming out. And we'll do a cross entropy on here. And this is going to be minus tf reduce sum. And we'll do y, here's our y underscore, which is, remember we have your y output and your actual output. So this will be our y underscore times the tf log of y. And then finally, before we do the actual initialization of all our variables, we'll set up our train step. This equals our gradient descent optimizer. Very important. Remember we looked at that chart on our slides? And so we've set up all these formulas, and here's our gradient descent optimizer, and as it keeps looking for that 0 value. That's what we're doing with that particular formula. So let's take a look and see what we're doing here. We just put together all of our pieces for TensorFlow. And the devil's in the details. We have here our training set coming in. We have to put a placeholder on there. We have our variables with their weights. We have our biases coming out. And then we put in our the weighted sum. So here's summizing our summation here. Then we have our y variable output. So there's our y, how it works, and then of course the actual output on there. And then we have our cross entropy coming in, and that's our minus tf dot reduce sum, the y times the tf log of y. And then the training step, gradient descent optimizer. And we're using a 0.01 in this, and we're going to minimize cross entropy, so we're going to let it do all the work. So once we've set up all of these different layers, we've allocated for them, we need to go ahead and initialize them. So we're going to do an init tf initialize, and it's going to be all variables. One of the cool things is they're in the process of doing away with this. So all these steps would be bundled into one instead of having to have placeholders. You initialize them in the same process going on. And then finally, everything in TensorFlow is based on your session. Now this is changing, that there's other options to be able to run this. But we want to go ahead and do session. There's our TF, which is a TF session. And then we want to go ahead and do session run. And what are we going to run? Well, we did initialization of all our variables. So this is what we're running. And this is where actually, once we do this, we actually create our TensorFlow object. So this whole piece of code right here is our TensorFlow object. We have our input coming in with our weighted variables coming in, our softmax for our matmul going out. How does it add it together for our y value? And then we have the actual float value coming out, checking on our all the way down. So you can see all the different stages going through that we're setting up. And this is one of the reasons that a lot of people like TensorFlow, is because you can designate all these different pieces one step at a time. This is also one of the reasons people don't like TensorFlow, is because you have to designate all the different layers coming down. And there's a lot of steps being made right now to minimize this, to make it either easier to automate it or to allow you to do more complicated things. And all those steps are still at play, so it's worth looking into the more advanced version of what's going on with Keras on top of TensorFlow. It's also important to understand what's going on these individual levels if you're going to play with them. It's important to understand, hey, what's going on with the finding the weighted sum of the inputs plus the bias, because there's other ways to do that. There's all kinds of other tools in there now. But this is the basic setup that you want to do on a TensorFlow coming in. And we want to go ahead and just run and init our TensorFlow. So let's go ahead and do that. Let's run this. We do get a warning here because there's a move to use global variables. This is one of the changes they're making. But as far as this example, it's not going to make a difference because we're doing, once we initialize it, this is initializing our variables. And again, these are only placeholders up here until we initialize them. And I would highly suggest put a note down there or go over to Simplilearn.com and let them know and have them email you a copy of the code so you can actually play with this code right here. Because this is the body of what's going on in TensorFlow. This is the build build in neural networks. And then once we've done that, now comes kind of the fun part, is we need to go ahead and train it. So we've created our TensorFlow, we've created our network, and now we need to go ahead and train it. So let's put together that training code, and let's just do for I in range 1000, 0 to 1000. So we're just going to look at the first 1000 in our training. And the way we pull that data from our mince train next batch of 100, so you look at this, we're going to be doing groups of 100, and then there's going to go through 1,000 of them. This is very important that TensorFlow builds this in. This is one of the downsides of doing sklearn or one of the older packages, is they don't let you batch groups in. They wanted to have it all up front, and then you have to build your own batch programs right now. This lets us go ahead and do that, and you can see here we have batch x of s, batch y of s. So there's our x and our y. You can look at this as our training of x and our train of y, or the data in and the answer in. And then we simply do our session run. So here's our session that we've created. We're going to run it, and we want to do the train step. Remember, we initialized our train step up here in our TF, and so there's our train step. Feed is a dictionary coming in, which we're going to create right here. Is x is our batch, x of our sample, comma, and our y underscore is going to be our batch of our y sample. And so this goes through, and we've now hit the run button, and we've trained our session. We've trained this setup on here. And once we've trained it, then we need to go ahead and find out how good our accuracy was and actually start running some predictions through there. So we'll go ahead and create a correct prediction, and this is where our tf.equal, we'll use our argmax y of 1 and tf argmax of y of underscore of 1 to help us get the correct predictions on there. And then we want to use that to feed into an accuracy. And so our accuracy is going to be tf reduce mean, and we'll take that and we'll do a cast, and this is the correct prediction that we're sending in there, and it is a float value. Keep it simple, and let's go ahead and print this out so we can see what we're looking at. So what are we printing out? We need to do a session run. This session run is going to be on the accuracy. Where did accuracy comes from? This is we're casting our TF on there with the correct predictions on that. So here's our accuracy. Feed in, so it needs a dictionary for the data coming in. We're going to create our dictionary, and x is going to be our NIST test images, and y underscore there is going to be our NIST.test labels. Let me just double check and make sure I have that typed in there correctly. There we go, and let's go ahead and run that and see what comes up, and we end up with a 0.9165 for our accuracy, which means our trained neural network does a pretty good job letting us know what these different symbols are, and guessing that a 7 and a 3 and a 4, something that as humans we kind of take for granted. I even have trouble reading this, so I don't know if I would be able, like that first one, I would sit there for a long time figuring out that's a 7 versus a 2. That could have easily been a 2 to me. So you can see we do a pretty good job analyzing this data, and this is used to analyze something very complicated on these images, very different than just a straight value of cost of sales, and here's our return and our marketing. We can now create this nice neural network that does all kinds of cool things.
Today we're going to see what is deep learning very briefly, and then we will talk about what are the various libraries that are available for developing deep learning applications, and then we will focus on TensorFlow and what are the various advantages, why we should use TensorFlow, what is TensorFlow, and then we will talk about what are tensors, which are, as the name suggests, TensorFlow consists of tensors, and then they are executed in a certain graphical format of flow, like a graph, and that's why it is named as such, TensorFlow. And we will see how to write programs in TensorFlow. The programming language, of course, will be Python, but there is a certain way in which you write a deep learning application or a program in TensorFlow. So we will take a look at that. This is a basic introductory session for beginners, and then we will see one implementation of TensorFlow code, one full end-to-end, and that's pretty much it, what you can expect from this. Quickly wanted to mention that there are certain prerequisites before you actually go through this. The expectation is that you at least have some idea about some programming language, and preferably Python. If you know Python, absolutely it will be much easier to understand the code as such. But even if you know any other programming language, I think it will be okay, and you will at least be able to understand the Python code. In addition to that, this also involves, especially the case study or the case implementation, you will be able to understand only if you have some idea about machine learning. So in case you are very new to machine learning and Python, everything, then it may be a good idea to check other tutorials that we have uploaded on, let's say, about Python and also about machine learning, so that you get a basic understanding and then come back here. Otherwise, it may be very difficult to understand this tutorial. Alright, so having said that, let's get started. So what is deep learning? Again, this video is not about deep learning, but there are other videos we have created in detail about what is deep learning. In this video, we'll just touch upon the basics, so that's like a nice segue into TensorFlow. So deep learning is in a way a subset of machine learning, and we use primarily neural networks in deep learning, and the underlying technology behind artificial intelligence is deep learning. And here we teach them how to recognize, let's say, images or voice and so on and so forth. So it is a learning mechanism, but here, unlike traditional machine learning, the data is far more complicated and far more unstructured. Like it could be primarily in the form of images or audio files or text files. And one of the core components of deep learning is neural network. And a neural network somewhat looks like this. There is something known as an input layer, and then there is an output layer, and in between there are a bunch of hidden layers. So typically there would be at least one hidden layer, and anything more than one hidden layer is known as a deep neural network. So any neural network with more than 3 layers altogether, right, is known as a deep neural network. All right. So what are the functions of the various layers? Let's take a quick look. So the input layer accepts the input. So this could be in the form of, let's say, if it is an image, it could be the pixel values of the images. So that's what the input layer does. And then it passes on to the hidden layers. And the hidden layers in turn perform certain computations. And they have what is known as a part of the training, they have these weights and biases that they keep updating till the training process is complete. And each neuron has multiple weights and there will be one bias, and these are like variables, and we will see when we go into the TensorFlow code what we actually mean by that. And so that's what the hidden layer does. It does a bunch of computation and passes its values to the output layer, and then the output layer in turn gives the output. It could be in the form of a class. So for example, if we are doing classification, it tells us which class a particular image maybe belongs to. For example, let's say if this is a image classification application, then the input could be a bunch of images of maybe cats and dogs, and the output will be like, it will say, okay, if this is activated, this gives a 0 and this gives a 1, that means it is a cat. If this gives a 1 and this gives a 0, that means it is a dog. So that is a kind of a binary classification, and that can be extended with multiple neurons on the output side to have many more classes, for example. Or it can also be used for regression as well, not necessarily only classification. Again, since this video is not about deep learning or machine learning or neural network, we will probably not go into a lot of details, but you can check other videos where we have given a lot more details about neural networks and deep learning and so on. So in order to develop a deep learning application, how do you go about? Primarily, there are 2 or 3 components that are required in order to develop deep learning application. You need obviously a programming language. So typically Python is used, and that's what we are going to use in this particular video, but you can also use other languages like Java or C++ and so on. And there are some libraries that are readily available and primarily for doing machine learning and deep learning programming. So these are a list of libraries. These are by no means the exhaustive list, but some of the most common ones like Keras, Theano, TensorFlow, and so on and so forth. TensorFlow has nowadays become very, very popular. This is developed by Google, and it is an open source library. And Keras was there before. Now Keras has actually now become a part of TensorFlow as well. So it is one layer above TensorFlow. So in that sense, they're well integrated. So a combination of Keras and TensorFlow is pretty good. Then of course you have Torch and DL4J and so on and so forth. So there are multiple libraries, but this video is about TensorFlow, and we will be focusing on TensorFlow. What are the benefits of TensorFlow and what are its components? And towards the end, we will show you a code in Python. We've written a code in Python. By the way, TensorFlow can be used with multiple languages. It supports multiple languages, though Python is by far the most popular language. language. So let's take a look at what exactly is TensorFlow and why we are so excited about TensorFlow. So TensorFlow offers APIs. Now we can, earlier when these libraries, none of these libraries were there. Even then people were doing machine learning and deep learning and so on. But the coding mechanism was much more complicated. What these libraries like TensorFlow offer is they provide kind of a high level API so that we don't have to go really deep into writing all the stuff that is required, let's say to prepare a neural network and to even configure or even to program a neuron and so on, right? So these are done by the library. So all you need to do is they offer a higher level API. You need to use that API and call that API and maybe pass the data, and that would it's much easier rather than actually going down and writing everything by yourself. So TensorFlow, that way it offers APIs to write your code in Python or even C++ and so on, other languages, Java as well. It has an integration with R as well, apparently, okay? And it supports CPUs as well as GPUs. Now, deep learning applications are very compute intensive, especially the training process needs a lot of computation. It takes very long, as you can imagine, because the data size is large and there are so many iterative processes. There are so much of mathematical calculations, matrix multiplication, and so on and so forth. So for that, if you perform these activities on a normal CPU, typically it would take much longer. But GPUs are graphical processing units. You must have heard GPUs in the context of games and so on, because where the screen needs to be of high resolution and the images need to be of high resolution and so on. So GPUs, as the name suggests, graphical processing unit, were originally designed for that. But since they are very good at handling this kind of iterative calculations and so on, now they are being used or leveraged rather for doing or developing deep learning applications. And TensorFlow supports GPUs as well as CPUs. So I think that's one of the major advantages of TensorFlow as well. Now, again, what is exactly TensorFlow? It's an open source library developed by Google and open source, and primarily for deep learning development. But TensorFlow also supports traditional machine learning, by the way. So if you want to do some traditional machine learning, we can do it. However, it is probably a bit of an overhead to use TensorFlow for doing traditional machine learning, and this is really good for performing deep learning activities. And again, if you want to get into more details about what's the difference between machine learning and deep learning, there is another video about it. You can probably take a look at that video. What else? It is developed originally for large numerical computation. So originally when TensorFlow was developed, they never thought of it as keeping deep learning in mind, but ultimately it so happened that it's really very good for deep learning development, and therefore Google has open sourced it. And TensorFlow, as the name suggests, the data is in the form of what is known as tensors. These are like multi-dimensional arrays, and they are very handy in handling large amounts of data, and we will see that as well as we move forward. And then of course the execution mechanism is in the form of graphs, so that makes it much easier to execute this code in a distributed manner across a cluster of computers and also using GPUs and so on and so forth, right? So that's a quick overview about what is TensorFlow. We will see a little bit more detail the two major components, that is basically the tensors and the graphs. Let's take a look at what they are. So what are tensors? Tensor is, as I mentioned earlier, it is like a multi-dimensional array in which the data is stored. Now when we are doing deep learning, especially the training process, you will have large amounts of data, and the data is typically in a very complicated format, and it really helps when you are able to use this or store it in a compact way. And so tensors actually offer a very nice and compact way of storing the data, handling the data during computation. This is not really for storing on your hard disk or things like that, but in memory when you're doing that computation, tensors are really very handy in terms of keeping the data compact, because they are like multi-dimensional arrays. So the data is stored in tensors, and then it is fed into the neural network, and then you get the output. All right, so there are some terms associated with tensors. Let's get ourselves familiarized. One is the dimension, and another is the rank. So what is dimension? Typically dimension is like the number of elements in a way. So for example, this is a 5x4 dimension tensor, and then you can have again multi dimensions, right? So this can be like 3x3x3. So that is the dimension. And then you have ranks. What are tensor ranks? Ranks are basically, traditionally we would have thought of as dimensions. That is actually, in this case, it is called rank. So it becomes easier when we see examples. So a tensor's rank is supposed to be 0 when there is only one element. We also call this as scalar. So just one element, and this is not really a vector, it's just an element like 200. It's also known as a scalar. So such a tensor is supposed to be having a rank of 0. Then you have, let's say, a one-dimensional array. This is a vector with a row of elements. This has rank of 1. Now if you have traditionally what we call as two-dimensional, like a matrix for example, then the rank is 2, and in this case the rank is 3. And it can have more ranks as well. As I mentioned, it is like a multi-dimensional array, so you can have rank 5, 6 and so on. Okay, so those are the terminologies in TensorFlow terms, dimensions and ranks. So this is just to make sure that we are speaking the same language, so whenever we talk about a rank of a tensor, you understand what exactly is meant by that. Now, in addition to tensors in which the data is actually stored, all right, so the data is stored in the tensors, and then once you have the data, there is a computation that needs to be done. Now the computation happens in the form of graphs. So what we typically in a TensorFlow program, what we do is, it's not like traditional programming where you just write a bunch of lines and then everything gets executed in sequence. Here we prepare graphs, various nodes, and then these are executed in the form of a session, and they use the data from these tensors. Now I know this is a slightly new concept for a lot of you, so it may be a little difficult to probably understand in the first cut, but when we look at the code, when we go into the tutorial, the code walkthrough, I think that time it will become much clearer as well. But to start with, just we need to keep in mind that we have to first prepare a graph, and when you're preparing the graph, none of the code is actually getting executed. You write the code to prepare the graph, and then you execute that graph. So that's the way, by creating a session, that's the way TensorFlow program works. So, and each of these computation is represented as what is known as a data flow graph. And we will also see that whenever you start TensorFlow, when you create an object, TensorFlow object, there will be what is known as a default graph, and then if required, I know probably in the beginning it may not be required, but in more advanced programming you can actually have multiple graphs. Instead of the default graph, you can create your own graph and have multiple graphs and use it as well. But there is always, whenever you create a TensorFlow object, there will be a default graph, and this will be very nicely illustrated in the example code that we will take to explain this. So there it becomes much clearer than in these slides. So the graph gets executed and it processes all the data that we are feeding. All the external data will be fed in the form of what is known as placeholders, and then you have variables and constants. Again, this will also become clear when we take a look at the code. And once you have the graph, then the execution can be enabled either on regular CPUs or on GPUs, and also in a distributed mode, so that the processing becomes much faster. As I mentioned, the training of the models in deep learning takes extremely long because of the large amount of data, and therefore using TensorFlow actually makes it much easier to write the code for GPUs or CPUs and then execute it in a distributed manner. So this is how the TensorFlow program looks. So there is you need to build a computational graph. That's the first step, and then you execute that graph. So the first step is to write the code for preparing the graph, and then you create what is known as a session, and then in that session you ask the session to execute this graph. So this will again become much clearer when we look at the code. Now, what are the various elements of a TensorFlow program? As I mentioned, TensorFlow program is slightly different from regular programming that we do. So even if you're familiar with Python, this may still be new for you. The way you write a TensorFlow program is different from the regular Python programming that you would have done, or even machine learning program. You would have written some machine learning program using scikit-learn or regular Python libraries. This is different from even that. So let us see what are the various elements. So first of all, the way we handle handle data inside of a program itself is a little different from how we normally do. In a normal programming language, a variable is a variable in your program, right? So you have anything that can keep changing, you just create as a variable, or even constants in fact are actually created as variables. But in TensorFlow, the storage in the program consists of three types. One is constants, another is variable, and the third is a placeholder. So and there is a lot of difference between these types, and we will see how they vary and how they are used and so on. So constants are like variables which cannot be changed. So for example, if you define a constant like this is how you define a constant, by the way. The simplest format is like this, like for example, b is equal to tf dot constant, and then you give a value here. A slightly more advanced version is you also specify the type. So you say tf dot constant 2.0 tf float 32. So the type is of type float. Now, in case of constants, you cannot, during the computation, you cannot really change these values. So for example, if you want to change the value of b from 3 to 5 or any other number, it is not possible. So that is the meaning of constant. All right. So then we have variables. So variables we are all familiar with. What are variables? Whenever we use programming, we use variables. So this is pretty much the same. This is the way you define variables, tf dot variable. Now, one thing you need to note is this is the only type in which we have v capital. Okay, constant has c, small c, and placeholder as small p, but variable has capital V. And tf dot variable, and then you give the value, and then you can specify what is the type, and then you can use the variable, change the variable at any point in time with a different value and so on. You can update the variable and so on. So we will see all of this in the code. I will illustrate how a variable is defined and how it can be changed, whereas a constant cannot be changed, and so on and so forth. And then we have placeholders. Placeholders are really a special type, and this may be something completely new for many of us who have been doing programming, but in TensorFlow this is a completely new concept. So this is very important to understand this. Placeholders are like variables, but only thing is that they are used for feeding the data from outside. So typically when you're performing some computations, you need to load data from a file or from an image file or from a CSV file or whatever. So there is a provision with this special kind of variables which can be fed in a regular basis, because one of the reasons for having this kind of provision is that if you get the entire input in one shot, typically it may be very difficult to handle the memory and so on. So I think that was the reason they came up with this mechanism where you can feed in batches. And there is a certain way of populating the placeholder. We call this feed dict, feed underscore dict, and this is a parameter name, by the way. And you feed the placeholders, right? That is the meaning here. So there is a certain way of feeding the placeholders, and we will again see this in the example code as we move forward. Okay, so there are three types. One is the constant, which cannot be changed once you assign a value. Then you have variables, which are like normal variables we are all familiar with. And then you have placeholders. This is primarily for feeding data usually from outside, but of course you can also, for temporary testing purpose, you can feed within the program as well. But primarily the purpose of a placeholder is to get data from outside. So alright, so those were the constants, variables, and placeholders. That is how you handle data within a TensorFlow program. And then you create a graph, and once you create a graph, then you have what is known as a session, and then you create a session object, and you create a session, and then you run a particular computation or a node or an operation. And so typically what you need to do is every variable or a computation that you perform is like an operation or a node within a graph. So initially the graph will be what is known as the default graph. The moment you create a TensorFlow object or TF, this TF here you see, this is the TensorFlow object. And again in the code, when we go into the code, it will become much easier to understand. So when you create a TensorFlow object, there is like a default graph which doesn't have any operations, no nodes or anything like that. So it's like a clean slate. The moment you assign variables or constants or placeholders, each of them is, in TensorFlow terms, it is known as an operation. Again, you need to get familiar with these terms, and they are not very intuitive. This is not really an operation. You're just creating a constant or a variable, and this C is equal to A into B would traditionally or would intuitively be an operation. Here you're actually performing an operation. But in TensorFlow terms, each of these, everything is an operation. So if you're creating a constant, that is an operation. Another constant or variable, that's an operation. So you can actually run each of these, and they're also known as referred to as nodes. And when you're in your session, you will actually run each of these. You can potentially run each of these nodes. Okay, so a typical example would look like this. So you have two constants created. A is equal to tf.constant, its value is 5, b is equal to this, and then you say c is equal to a into b, and then you create a session. Now remember, all this you're just creating a graph. At this point, no execution has happened. All right, so only at this point, once you create a session and then you say session or ses.run, c is when actually this whole thing will get executed. All right, so that is a different way of programming compared to our traditional way of writing programs. So you need to get used to this new format. And when we look at the code as we move forward, and when we look in the Jupyter notebook, it'll become much easier probably to understand this rather than in the slides. So these are the slides showing the code, but what we can do is go straight into the lab and take a look at the various examples that are there, and starting from the very basic one, how you create variables. And so these are some of the slides that are showing. So this is about how to create variables, how to create constants, and the variables or constants can also be strings. So this is like our first hello world program, and we will talk about placeholders, how to define a placeholder and how to execute and populate the placeholder values into placeholder. We will see these examples in the lab. Actually, I will run the code, and we will also perform a small computation of adding and multiplying these variables, and we will, in the end, we will take up a use case implementation using TensorFlow. So let's first go and see those examples and then come back and I'll explain this use case, and then we will execute the use case in the lab. So let's go and check our lab. Okay, so I'm in the Jupyter Notebook environment, and this is one of the development environments we can use. This is regular Python. Anytime you do Python programming, we use Jupyter Notebook, or there are other ways of using other tools like PyCharm and so on. But for this particular tutorial, I'm comfortable using Jupyter Notebook, so I will show you in Jupyter Notebook. So this is the very basic example to demonstrate how to create variables and constants and placeholders, and what is the difference between them, how they behave, and so on. And as I mentioned, the assumption here is that you know at least some basic Python programming or some programming language, so at least you understand the code here. And first two pieces of code, you will not need a machine learning background, but when we do the use case or the case study, there it is expected that you know at least some basic machine learning concepts. So in case you need to brush up the machine learning part, you may have to do that before you go to the third one. But here, just at least some idea of programming will be sufficient. So what are we doing here in this particular line or in this particular cell? We are importing TensorFlow. It is, as I mentioned, it is a library. So we are importing TensorFlow and we are calling it TF. So this is just a name. You can give it any name, but it is very common, and everywhere wherever TensorFlow programming is done, it is always named as TF, but you can name anything actually. Okay, so this will import the TensorFlow into my session. Now this is the way to create a variable. So let's start by creating a variable, and this is the name of my variable. I'm starting by giving a name called 0, and I say 0 is equal to tf dot variable, and then I'm giving the value of the variable here. So this is the very basic way and the simplest way to create a variable. We will see a little later there are other formats as well, but the bare minimum way of creating a variable is this. So I'm creating a variable by the name 0, and as I mentioned, you need to pay attention to the capital V here. In case of variable, it is a capital V, uppercase. Constant and placeholders are lowercase. Now I'm creating a constant, and the constant I'm naming it as 1, and the way to create a constant is tf dot constant, and then you give the value of the constant. So the value of the variable here is 0 and the value of constant here is 1. And again, constant, you can also have additional parameters like a name and so on. Probably you must have seen in other tutorials or in other places where the code is written. But the basic format to construct to create a constant is this. This is sufficient to create a constant. So I created one variable and one constant. Now, what else can we do? Again, here there is no real execution happening. We are just building a graph. We have not yet executed any TensorFlow code. We are building a graph. And I will show you how the graph looks as well. First, let us understand the constants and variables and so on, and then I will show you how the graph is generated and so on. So what I want to do here is I want to add 0 and 1 and put it into a new variable called new value. So what I do here, TensorFlow offers these methods like add, assign, multiply, or you have matrix multiplication, matmul, and so on, right? So I will use one of those methods, which is tf.add, and then pass these two as parameters. So we can add a variable and a constant. There are no restrictions on that. So this is a variable and this is a constant. So if I do this, it will be okay. I did not execute this code, so it is giving an error. Now we are good. Okay. So what it has done is new value will be equal to tf.add 0, 1. So then we have one variable and one constant. Now let's say I want to change the value of the variable, because that is possible, right? So we want to change the value of the variable to something, some new value. So we have, in this case, new value has 1 because we added a 0 and a 1. So new value has 1. Now I want to assign this to this originally what we called as 0. So I will call that as update is equal to tf.assign. So assign is basically changing the value. So that's what we are going to do here. Now it has not complained. We'll just say fine, right? There are no issues. Now let us try this something similar with this 1 as well. So 0 is a variable. So we were able to change the value, and we will, in a little while, we will see what exactly those values are. But before doing that, now let's say I will uncomment this part and I want to do something similar for my constant, right? 1 is a constant. Now I want to, let's say, change the value of the constant and make that also something different. Okay. So if I execute this piece of code, it will give an error. Now again, the error message may not be very intuitive. This doesn't say that you cannot do this for a constant. It will just say tensor object has no attribute assigned. Now that sometimes may be confusing, especially when you're starting. But the meaning here is that 1 is a constant and you're trying to modify the constant, so it will not allow. That's the reason it is complaining. So let's put that back in the comment, and okay, so that is done. So only variables you can modify. Now what do you have to do? Let's skip this piece of code. I'll come back to this in a bit. But let's say we start by creating, you remember I told you we need to create a session. So the way to create a session, there are a couple of ways of creating a session, but this is for beginners. This is the easiest way. All you need to do is assign a variable called ses, or you can give any name, and that is equal to tf.session. That is the session method here, and you create a session object by the name ses. Now what I'll do is I'll skip this as well. There is a purpose behind that. Now let's go ahead and run this piece of particular operation. You remember I mentioned that everything you need to run. So as of now, the code has not really got executed. TensorFlow code has not got executed. You only created the graph. So only when you run through the session is when actually the program gets executed. So when you do this, now you see, observe that it is giving an error. Okay. The reason behind that is, remember, we skipped these 2 lines of code for variables. Okay. This and then this. Now this is something very, very important to observe. If you have variables in your code, what I mean by that is, let's say you are not using variables, but you have only constants and placeholders, then this will not complain and you will not get this error. But in our case, we also have variables. So whenever you have variables, in that case, you need to do an initialization. And this is just a standard code. There is nothing that we need to add or modify or anything like that. This is a standard piece of code. You create this name, of course, can be anything. You can give us any name, but this global variables initializer is what you need to call tf.global variables initializer. This will kind of initialize all the variables that you may be using. And then again, remember, this doesn't execute anything, right? So all you're doing here is you're creating an operation. But in order to run that operation, you need to also run this known as run init_op. So this operation you need to run after creating the session. All right. So we executed this. Now let us execute this. And now when I run this piece of code, it will run successfully. Okay. I hope you observed that. So it is whenever you use variables, these two lines of code. One is the operation. You need to create an operation for saying global variables initializer. And then you need to run, before running anything else, you need to do a session.run this operation. Okay. Again, only if you're using variables. Of course, you invariably in all your programs, you will use variables. You cannot just write a program with constants and placeholders. So you can pretty much assume that this has to be there in pretty much all the programs. Now again, why this has not been taken care of in the library, that's a different question, but you need to keep in mind. And always remember, if you don't do this for whatever reason, if you've forgotten, you will get an error and the error won't be intuitive. So you need to remember this, that this could be because of the variables. Okay, good. So we have seen how to create a constant, and we have seen how to create a variable, and we have seen that you cannot modify or update a constant. And we have also seen if you have variables that you need to execute or have these two lines of code to initialize the variables. And then we have seen that after creating a graph, how to run the graph in a session. And I will show you a little bit more in detail how exactly the graph gets created and how it gets executed. But this was the first very quick code on creating variables and constants. Now we will keep going, and we will also show you, or I will show you the placeholders. But before that, one more small piece of code. So this is how you write a for loop. Okay, so we are saying 5 times you run this piece of code. Now like any Python program, this is nothing different. So you have a for loop and this is indented, that's the reason. And therefore you say session.run update. So this will run 5 times and it will get printed. That's all. So update will run for 5 times. Each time it will come and do this particular operation. That's all we are asking the system to do. So let me just run that and show you. So it will, okay. So it has done 5 times. That's 4. It is basically adding, if you recall, it starts from 0, it adds 1 to 0, then 1 to 1, 1 to 2, and so on. So it's nothing but it is generating 5 numbers, 1, 2, 3, 4, 5. That's it. Okay. So then you can also have your constants as strings, for example. So you can also work in a similar way. You can work with strings. So most of the computation happens mainly on numerical values. So we normally handle numbers, but there will be situations where you may have to handle strings as well, or text as well. So this is an example of text operation. So you can, similar to numbers, you just create strings or store in constants. Instead of a number, you say hello is equal to tf.constant, and then you assign the string that you want it to be assigned. And then the next one is one more string, which is for world, and then you say add these two. So it is nothing but concatenation of these two words, hello and world. So we will do that. And remember, this is only creation of the graph, right? So in order to actually execute this graph, you need to run the session. Now you need to keep in mind, we don't have to create the session once again, because once you create a session, till you close the session, it remains valid. Okay. So we have created this session here. Now till you say ses.close, it will remain for you. So that's why we did not create one more. So we are just reusing that session, ses.run hello world. So in this hello world, what is the operation that we are doing here? The operation is add these two, concatenate these two. So if I run this, it will print hello world. Okay. Now that's string operation. Now we will take a look at placeholders. So this is slightly more complicated and something new even for people who have been writing programs. So, but I'll just explain it with a quick example. First of all, how do you declare or create a placeholder? You just do tf.placeholder, and the p is lowercase. Only in case of variables, the v is uppercase, but otherwise constant and placeholders, it is lowercase. And you just say, because as I mentioned, this is a placeholder that doesn't have any value. So you, unlike a constant or your variable, you will not specify any value. You just say what type of placeholder you want. And very often, most of the cases, it is a floating point. So we just say placeholder of type float32. So this tf.float32 tells the system that it is a floating point. Okay, and then, so let me just run this, and then you can do some or define some computation, like for example, b is equal to a into 2. Now remember here, right now a has no value, but what we are saying here is at any point later on when a gets some value, then b should be equal to twice the value of a. That's all we are saying here. Okay, and also, as I mentioned earlier, we are not yet executing anything. We are just creating the graph here. Okay, so now you have that. Now how do you feed the value or populate the placeholder? There is a certain syntax in which you can populate the placeholder, and you do that using what is known as a dictionary. You're all probably familiar, those with Python especially must be familiar with dictionaries. So you need to create a dictionary and then pass that in order to feed the placeholder. So in this particular example, if I want to run something, if I want to calculate or compute b, obviously I need to feed the value of a. So the value of a I'm feeding using this dictionary, and I'm saying that a is equal to 3. Now there are multiple ways of populating the value of a, because typically this won't be just a scalar value like in this case, right? Remember scalar, so it's just one value, one number. Typically it would be a vector or a tensor. Very often it is a tensor. So we will see step by step. So we can start with the very basic example where a can be a scalar. So in this case, a is equal to 3. That's what we are saying. Feed underscore dict. In this case, feed underscore dict is the name of a variable, by the way. So you can't give anything else here. So if you just say feed is equal to this, it will give you an error. Alright, so keep that in mind. Either you specify feed underscore dict is equal to and give the dictionary, pass the dictionary, or you straight away, like in this case, this is another format. So let's see. First, let me execute this. It has given 6. Okay, I think let me see if I can clear out this particular cell so it becomes easier to understand. Okay, so it is giving you 6. Let me do that once again. Clear out this and then, okay, and let me change the format. So this is one way of doing it. Another way is you don't even have to specify the name of this parameter feed underscore dict. You just pass the dictionary and it will execute. Okay, but typically this makes the code readable. So that's the reason most of the places whenever you find TensorFlow code, you will see that they explicitly mention feed underscore dict so that the code is readable. Otherwise it can get confusing. So I will also comment this and retain the other format. Okay, so I hope it's clear. So what we are doing here, we are running the operation b, and what exactly is b? B is twice a into 2. So therefore what we are doing, and a has not been, doesn't have any value out here, right? So that's why we are feeding the value of a, and then the operation gets completed. So a gets a value of 3, and then it gets multiplied by 2 because that's what we said here. Therefore b gets a value of 6, and that's what is being fed into result, and that's what is getting printed here. Okay, now as I mentioned, a need not be just a scalar value. It can be a vector with a multi-dimension array and so on and so forth. So let's start showing you examples of that. Again, let me just clear out the outputs. Let me clear this, and let me also clear this for now. Okay, you can also do, before running this, we could also do clear all output clear. It will clear everything, but that we'll have to start all over again. So I'm just doing individually. All right, so in this example we are taking a one dimension array where rank is equal to 1, and I'm feeding 3, 4, 5. Now let us see what happens if I run this, right? As you can imagine, it gets multiplied, each number gets multiplied, so the result is 6, 8, 10. Okay, now as I said, it can get more complicated. Now let's say this is a multi-dimensional vector. So what happens if you feed this? Okay, so as you can see, this is pretty complicated. Now, but if you feed this again, all you're doing is there is a slight change here. Again, you can also create your dictionary outside and feed that here. You don't have to directly do it here, like in this case. You see,
there are variations of the exact syntax in the way you write it, right? So there is a slight variation. So in this case, you are creating the dictionary straight away here, kind of inline, but here you created the dictionary separately because it's more complicated, and then you are passing that dictionary here. So I said dictionary is equal to A, and then I'm saying this is what should be the value of A, and I'm feeding that, and then I'm using directly that dictionary here. Okay, so this is equivalent to putting this code here, right? So if we execute this, what happens? Same. So you get, because A was let's say this is a 3 by 4 by 2, right? So that is 3 by 4 by 2, right? So you see here, this is a multi-dimensional array. So you feed that, and the values you see here, it is 1, 2, 3, it became 2, 4, 6. 4, 5, 6 became 8, 10, 12. 7, 8, 9 became 14, 16, 18, and so on and so forth. Okay, I hope now you got an idea about placeholders. And in real life, what happens is you typically won't create these dictionaries manually. Since this is a quick demo, we did this. You will actually read the data into this dictionary, and then you feed that when you're doing the computation. Okay, so it could be a CSV file, or it could be an image file. So input is basically read and fed in. Usually it is also done in batches, so you don't read the entire thing because there can be a large amount of data. So that is the idea behind having these placeholders, and the way we feed these placeholders, there is a provision, deliberately there has been made a provision for this kind of getting data into the program in chunks. Okay, now in this particular example, we will close the session here, and then I will show you what is the other way of creating a session, right? So now if I close the session here, now if I try to do anything with the session, it will give us an error. So I will probably not do that right now. Now there is another way or another format, and this is a very common way of using the session, but I didn't want to start off with this because this could get a little confusing. A simpler way was to create session saying ses is equal to tf.session, but typically you will do it in what is known as a with block. This is a very common way of creating session. So once you have the graph, you would execute the graph in a session using a with block, and this is the syntax. So you say with tf.session as ses, all right, and then you put all your code here. So what will happen is you don't have to explicitly close the session. The moment this with block gets completed, the session gets closed. Okay, so let's just take a quick look at this example. Now, if we let me clear this current output, be clear. Okay, so this is the hello world example. A little bit earlier we did that. So I'm doing with tf.session as session result is equal to ses.run hello plus world, and then I say print result. Okay, so within this with block, I'm doing all my computation, and this gets executed. Now let's say I try to run. Remember, I created a session here. Now if I want to, let's say, do something like run ses.run a, it is giving an error because the session is no longer valid, right? So you cannot, either you have to run this. If you want to run this, you have to run this in this with block, or you shouldn't have closed the session here, right? You remember this, we said session.close. So since we have closed the session, there is no active session, therefore it is giving an error. Okay, now there is a third way of creating a session, but for now I will skip it because that is very, very specific to notebooks and so on, so we will just avoid it. You start with, for beginners, I think the best way is to start with creating a separate session and then writing your code and then closing your session. Now of course, remember, if you don't do this part, ses.close, it will not give any error or anything like that. Only thing is that it's a good practice and your resources will get released. Otherwise, if you do multiple of these programs, if they are running, then your resources will get blocked. That's the only thing. And to start with, it is simpler to do it this way. So initially when you're doing, you start with this. But as you move forward, as you become familiar with TensorFlow programming, I would recommend all of you to get into this model. Most of the programming, TensorFlow programming, is done like this with tf.session as says. Okay. All right. So that was one book or one page of code that we have done explaining about variables, constants, and placeholders. Now let me explain how the graph works. So in this example, we are going to see how the graph is created, how the graph gets executed and so on. Okay, now that we got a understanding of constants and variables and placeholders. Okay, so we will start as usual by importing our library, and as I said, whenever you create a TF or TensorFlow object, there will be what is known as a default graph, and you can get a handle of that by saying get default graph. So let's do that, and you can display the operations. Remember, every node in the graph is considered as an operation, right? So as of now, as you can see, we have not done anything. We have not created a constant or variable or nothing, right? So there is no operation. So by the way, let's do one thing. Let's start with all output clear so that I don't have to again do individually. So I'll just run these 2 lines of code. Okay, now so we have the default graph, and as of now there are no operations. So there is a method called get_operations which will kind of display or show what are the various operations that have been performed on the graph. So as I said, to start with, there have no operations been performed. So when I try to display, it's empty. There are nothing is there, no operations. Okay, now let's see what happens when we slowly, step by step, start writing or building the graph. So my first step may be to create a constant. Okay, remember in the previous example, I have shown you how to create a constant in the most simple or the simplest way, which is like constant and then the number, right? Now, a small extension of that is you can actually give a name to your constant. Now again, this need not be the same. I can say a is equal to name and xyz. I can give anything here. Okay, this is just for your reference, but here for simplicity, because there is a purpose why I'm using the same name as the name of the variable, and there are other reasons as well why you would give a name again to a constant or a variable. This is again useful when we are using what is known as tensor board. Otherwise it doesn't have much value. This additional name doesn't have much value. In this our case also, we will be seeing the graph, and that's why I'm using this, but otherwise this having additionally a name usually doesn't add much value. All right, so let's create a constant. I created a constant. Now let us see what's going on in the graph. So I will just say operations is equal to get operations, and if you see here, now you remember here it was blank. Now you see the first operation is showing up, and this a, that's the reason I put here, so it is showing as a, and it says that okay, you have performed an operation and there is a constant. You have created a constant. Okay, all right, so let's move on. Let's say we want to create a second constant, and this is b. So if I see what are the operations, list of operations that have been performed, you see here there are 2 of them. So you have operation a, which is a constant, then you have an operation b, another constant. You recall, we in the term operation here is not very intuitive, right? So we are just creating constants or numbers or variables, and it is saying it's an operation, but that's a terminology in TensorFlow. Everything is an operation here. Okay, all right, so then what else? Let's say I want to create a third operation, and that is basically adding, this is a real operation in normal sense as well. So let's say I'm creating C, which is adding A and B, and the C value obviously will be A plus B. Okay, now if we want to see what is in C and we say C, you see here it is not showing 30. It just says it is a tensor and it is of type int32, right? Because we have not executed the graph, we are still only building the graph. I hope this makes it easy to understand. Okay, so we are just building the graph. We have till we do a session and run a particular operation, you're not actually executing anything. Okay, you're just building the graph. All right, so now let us see what are the operations. We have done A, B, and now C. So you will see there are 3 of them, A, B, and C. Okay, now let's do one more operation, which is D, and here I am doing multiplication. Remember we did a tf.add, now I'll do tf.multiply, and I'm multiplying A and B, and I'm calling this operation as D. So A has I think 10 and B has 20, so D will be actually 200 when we execute it. Right now it is just a tensor and it is of shape int32. Okay, and once again we can see what are the operations, A, B, C, D. And let's do one last operation here, which is E, which is once again multiplication of C and D. Now that C has 30, which is A plus B, and D has 200, which is A into B. So now C into D will be 30 into 200, which is equal to 6000. But as we have seen earlier, that multiplication will not happen right now. So now you have built a fairly simple but operation graph, which consists of A, B, C, D, E, 1, 2, 3, 4, 5 operations. Okay, so you built a small, it's not a very complicated one, but a simple graph. Now you need to execute these operations. So what you need to do, you need to create a session. Okay, so ses.tf is equal to session, and then you can run these session, print ses.run e. Now, am I missing something? Do I have to initialize the variables? That's a question for you. Think and tell me. Do I have to initialize the variables? Then remember, I ran one piece of code. I think you must have got the answer. I don't have to, because I'm just using all constants here. I have not used any variable here, right? So I don't have to execute that piece of code to initialize the variables. So I can just create a session and run any of the operations that I want to run. So in this case, I'm running session E, operation E, right? This operation E. Now I can actually run individually. Instead of doing directly E, I could have run only A, or I could have run B, and so on and so forth. But in this case, I have run E, which in turn will do all the required computations, which is, for example, assigning the value to A and B and C, doing the multiplication and so on. All those operations will be performed, which are required to do the computation of E. Okay. Now, there is a small piece of code that you can use to find out what are the various operations that are there in this particular graph. In this case, of course, it was very easy, very straightforward. I have created A, B, C, D, E. But in normal programming, in real life, this can sometimes help to see what is there in your graph, what kind of operations are going on in your graph. So you can write this piece of code, and it may sometimes help debugging as well. Okay. All right. So I finished my session. What do we have to do? We need to close the session, right? Because I did not use the with block. So I need to close the session as a good practice. So I close the session. Good. So that's how the graph works. I hope it was helpful in understanding how variables and constants and placeholders are created in the previous example we saw, and how exactly you create a graph and then you actually execute that graph. That's the way TensorFlow program works. That's the structure of TensorFlow program. Okay, so now that we understood the structure of TensorFlow programming, let's take an example, and a classification example, and take some real data from outside, external data, CSV file, and try to solve a classification problem. For that, let's first go back to the slides and understand what is the problem statement, and then we will come back. Okay, so what is the case here? We have some census data, and which has all these features or variables, like the age of a person, what class, work class, what is his education, what is his marital status, gender, and so on and so forth. So there are a bunch of features that are available, and we have to basically classify, or not classify, we have to build a model for classifying whether the income of this person is above 50K or below 50K. Okay, so there is actually a label data available. We will then try to build a model and then see what is the accuracy. So that this is a typical machine learning problem actually, but as I said, TensorFlow can be used for doing machine learning as well. So we will, as a simple example, we will take machine learning. So this is how the high level the code looks, and in TensorFlow programming we also take help of regular Python libraries, like for example, it could be NumPy, or it could be Scikit-learn, or it could be Pandas in this case. And because before you actually develop, or before you train your model, create your model, you need to prepare the data into a certain format. And sometimes if you're doing machine learning activity, you all are familiar, those familiar with machine learning will know, you need to split your data into training and test data sets. So all that can be done using regular non-TensorFlow libraries, right? So these are like regular Python libraries, pandas, scikit-learn, and so on. So we use that and then prepare the data and then use TensorFlow for performing either the machine learning or deep learning activity. Now, so what is the advantage of using TensorFlow? The main advantage is that TensorFlow offers high-level APIs, right? We talked about that. So in this case, we will be using, I'll explain what is in the slide, but before that I wanted to just show you what is the API that we will be using. So we will be using the estimator API. We will be using the estimator API to create a classifier, what is known as a linear classifier. Now, in order to do that, you need to prepare the data, and you need to prepare the data into a certain structure or format, and the API itself needs to be fed in a certain way. So that is exactly what we are doing before we get into the regular TensorFlow code. Okay, so these slides will quickly show you what exactly is happening, but I will take you into Jupyter Notebook and run that code and show you. So here we are importing the data. The data is, the name of the file is census_data.csv. It's a CSV file, and then there is income bracket is one of the columns, which basically is our target. That is what is used. That is the label rather. But this doesn't have numeric values, so it has the income. So we need to convert that into binary values, either 0 or 1. So that's what we are doing here, and then we are splitting using scikit-learn. We are doing splitting of the data into test and training, right? So this is a standard scikit-learn. People, some of you who are familiar with traditional machine learning, and you have done machine learning in Python using scikit-learn, will immediately recognize this. This is a sklearn is scikit-learn, and there is a readily available method to split the data into training and test. That's what we are doing here. And then you need to create what is known as feature columns and input functions before you can call the API, estimator API. That's what we are doing here. And there are different ways of creating the feature columns for numeric values and for categorical values, or rather for continuous values and categorical values. Okay, so that's what has been two types we are doing here. We will see again in the code as well. And then you create your model. So this is basically model is equal to tf.estimator linear classifier, and then you're feeding the feature columns, and also subsequently you will call the training by passing the input function, and you specify how many iterations to be done for the training process. And again, this is all typical machine learning process, so there is nothing specific for TensorFlow here. And then you evaluate your model, because this is classification model, so you can again take help of the scikit-learn to test the accuracy and get the reports evaluation, perform the evaluation and get the report like this one. Right, so this is the classification report, and you will see what is the precision, recall, F1 score, and so on. Again, this is a standard machine learning process. All right, so that's pretty much as far as the code here is concerned. Once again, let me take you into our lab, and we will get started with this particular code. Now, let me clear out the outputs so that you can step by step you can see the output. So this is our data, and we will actually, this is just a display here. The code starts from here. So before even we start with our TensorFlow part of it, as I mentioned, we now remember in the previous examples, the data was kind of cooked up. Internally, we created some data and we were using it, right? The constants, variables, and so on. Here is a real life example. So you are actually getting data from outside. So, before we get into TensorFlow, this is actually regular Python code. So we are using pandas, for example, to create our data frame. So we will import pandas, and then we will basically read our file into a pandas data frame. And this is how the data looks, right? And if you do ahead, it will give you about 6 readings or observations, 5 or 6 observations. And then you can take a look at how your data is looking. So for example, you have age, work class, education, and so on and so forth. Okay, and you see here this last column, income underscore bracket, it says whether the income is greater than 50k or less than 50k. So this cannot be understood, or this cannot be fed into our model so that's the reason we need to convert this will not be understood, right? So this needs to be converted, saying okay, maybe less than 50k is 0 and greater than 50k is 1. So that conversion needs to be done before we feed it into our model. So that's what we are going to do as we move forward. So this is the code for doing that. Okay, so we take this and then we define a function and then we run that function. So now we have, wherever it is less than 50k, it will have 0, and greater than 50k, it will have 1. So we have now updated the data. Then the next part is to split our data into training and test data set. So how are we going to do that? We'll take the standard Python library, which is scikit-learn, sklearn library, and we use an existing function there, which is train test split. And what we are doing here is basically splitting the data into, I'm sorry, I need to run this and then this. Okay, sorry about that. So once I run this, what are we doing here? Again, those who are familiar with scikit-learn will immediately recognize I'm splitting this into test and train. I'm saying test size is 30%, so 30% of the data should go into test and training should have 70%. Okay, so that's all we are doing. 0.3 indicates 30%. So you can, again, this can be individual preferences. Some people do it like 50-50, some people 20-80, and in our case we are doing 70-30. So training is 70 and test is 30. Okay, all right. So so far we've been doing regular non-TensorFlow stuff. So preparing the data so that we can now use for TensorFlow. And in TensorFlow, what we are doing is we will be using the API called estimator. Now estimator, in order to call estimator, you need to prepare what is known as feature columns. So feature columns have to be in a certain format. Basically, it is nothing but the columns. We have to put them in a certain format. And then when we are calling the training, we need to pass what is known as an input function. Again, a certain way in which you need to pass that function. So that is what we need to do before we create the model and run the model for training. So the next few lines will be doing that. Quick look at, before we even get in once again into the TensorFlow code. So this is just showing us what are the various columns, names of the columns of this data. Okay, so that is what is shown here, and this is more for when I was writing the code, I could copy paste from here. That's the reason this line of code is there instead of typing in these values. Okay, good. So now is where the actual TensorFlow action starts. So I import TensorFlow, and now I will use this feature column functionality to create my feature columns. And there is a certain construct how you create the feature columns. Again, probably the details of that is out of scope here, but just that you need to know that we need to create feature columns, and the way you create feature columns for continuous values and for categorical values is slightly different, and that's the reason you have two different blocks. Okay, so for categorical values you need to use what is known as tf.featureColumn.categorical column with vocabulary list. And again, within this, there are two ways in which you can create for categorical values. One is a vocabulary list where you know how many types are there. So for example, gender column can have only male and female. So in such a case, if there are, let's say, a finite number of values for a given column, then you use a column with vocabulary list. Okay, so and then you say what is the name of the column and what are the possible values. So in this case, male and female. Now there will be situations where the values that this column can have, okay, first of all, it is a categorical column. That means it can have names or some non-numerical values. But the number of values is probably unknown or undefined. So for example, occupation. Now occupation can have any value. It can be self-employed, it can be a software professional, banker, a teacher, doctor. So many possibilities are there, and we don't know in the given data how many occupations have been listed, right? So that is where you use what is known as categorical column with hash bucket, and you specify the hash bucket size. So what this says is there can be a maximum of 1000 such values. So typically, if you give a safe number, safely large number, so that you don't run out of these number of occupations. So I think 1000 is a safe number. I don't think there will be more than 1000 occupations in a given data. So that's the idea behind it, but that's a judgment call we need to take. What should be the size of this bucket size, right? Hash bucket size. So these are two different types for categorical values for creating the feature column. So we will execute this for all the categorical columns. Obviously you need to know the type of the columns, and that is where, if you see right at the beginning, this information was provided. What is the data type, and you see here the column name and whether it is continuous or categorical. This information is provided in the census data wherever we pick this census data from. By the way, this was picked from online from a government website and we stored locally. So on that website it is mentioned, the details of this data were mentioned, and they have mentioned whether each of these columns is categorical or continuous. So that information we have to use, and we have to create feature columns using this categorical method for the categorical type of columns. And then for numeric or continuous values, you just use what is known as feature column dot numeric column. Okay, so these are all continuous or numeric values like age, education number, capital gain, capital loss, hours per work. These are all numerical values or continuous values, right? So you just say tf dot feature underscore column dot numeric underscore column and then give the name of the column. So once you do that, I think I have executed the previous one. Yeah, this one. Now, so your feature columns are ready, and you need to basically create a vector of all these columns, and we call that as feat underscore calls, which is like a short form for feature columns. Now, as you have seen, I've mentioned earlier also, there are two things that are needed. One is the feature columns and the another is the input function. So feature columns to first create the model, and then to train the model you need to create an input function. So now we have the feature columns ready. Next is to create an input function, and there is a certain way in which you need to, this construct is pretty much a very common construct, so we will use that. So the input function takes these x and y values for training and tests. You remember these are, the x train is the x values of the training data set, and y train is the labels of the training data set. So that's what we are using here, x train, y train, and then we specify what is the batch size. Batch size, you remember I mentioned, this is what will say how many records need to be read each time, right? So typically when we are doing the training process, we don't get the entire data in one shot. We do it in batches. So what size you specify here. Number of epochs, in this case we just say none, but number of epochs is again probably the definition is not required here, but at a very high level, how many times the entire data has to be passed through the model, right? So if you have 1000 records and you pass all the 1000 records 3 times for training purpose, then you call that as 3 epochs, right? So there is a difference between the batch size and epochs. So when, let's say we have 1000 records and you're saying batch size is 100, that means there will be 10 batches, right? So if you take 10 batches, then that is 1 epoch gets completed, okay? Then the training obviously doesn't get completed in one round, okay? So you need to pass this data again, maybe a second time or a third time till you get the right accuracy. That is known as epochs, okay? Again, if you need more details about this, you may have to go through the machine learning tutorial. I think it becomes much clearer. Okay, so you have your input function as well. Let's execute that. Okay, and now we are ready to use the API, right? So what will we do? We will create the linear classifier using tf.estimator.linear classifier, and this guy needs feature columns, right? So that's why we did all that, so much of manipulations to create this feature columns. So we have feature columns, so we pass that and we create our model. There may be a few warnings, don't worry about that. So we will just ignore that. And now we use that model, and what we did is we created an instance of the model. We have not really run anything. We just created an instance of the model. Now we will create the node for training. So model.train. And this needs the input function. Remember, we created the input function, so we need to pass the input function, and then we say the steps is now telling how many iterations this training has to be run. So we are saying 5,000, and this it will probably take a little long, so we will, okay, but that's fine. I think we will leave it 5,000. Sometimes if you have probably a less powerful machine, you can cut it down to maybe 1,000 or something like that. But in this case, I have a fairly powerful system, so I think it shouldn't take much long. Let's go ahead and give a couple of minutes for it to get over. Okay, so let us go back. Yeah, I think this is done. You see here the hourglass has disappeared. That means this computation is done. Yes, okay, this is done, right? Saving checkpoint for 5,000. That means it is done. So training is done. So now what we have to do? We need to do the evaluation. So again, this is a standard machine learning method. So methodology rather. So training has been done with the training data set. Now you need to evaluate using your test data set. So that's what we are doing here. For example, you see here x_test is the test data set. Remember, we used scikit-learn to split the data into training and test data set. So x_test. And a quick question, why are we not using y_test here like we did in case of training? Obviously, we are expecting the model to predict the values, y values, right? So that's why we don't pass the y values here. All right. So let's execute this for doing the evaluation. All right. And then we put them in a proper format because the output doesn't come out in a proper format. So we put it in a list format, and then we can just check. Yeah, so this is done, and we can check what is the first element in this, what is the probabilities, and so on. So it's just a quick way to see if the values are there or not. You can take any value here, right? Any element here. All right, now that the testing is done, what we need to do, again, we will probably put them in some kind of this is more of a formatting thing. We will just run through quickly, and then we will use once again scikit-learn for finding out the accuracy and so on, because scikit-learn offers what is known as a classification report functionality. So we will use that and find out how well our model has performed. So you see here again, people with machine learning background will be immediately able to recognize this. So it gives us what is the precision, what is the recall, and F1 score. This is pretty much like you're getting like almost 85% accuracy, which is pretty okay. And there are other ways to increase the accuracy. For example, you can run the training for more iterations. That is one way, get more data and so on and so forth, or use this is a linear classifier. We could have used a non-linear classifier and so on. So again, multiple ways of doing it to increase the accuracy. But the idea here was to quickly show you a piece of TensorFlow code, and that's what we have done here. All right, so let's go back to our presentation and let's see. So what are the key takeaways from this session? We saw what is at a very high level, what is deep learning, and what are the various libraries that are available for writing deep learning programs. And then we focused on TensorFlow. We saw what is TensorFlow, what are the elements of TensorFlow, how to write a TensorFlow program, what are the elements of a TensorFlow program, what are the various storage types like variables and placeholders and constants, and what is the difference between them, and how to construct a graph and execute a graph. So we have seen all of that, and then in the end we went through a case and executed a piece of code for classification. So with that, I hope this was helpful. We come to the end of this. Thank you very much for your attention, and if there are any comments, please put it in the comment section, and if you have any questions, provide your email ID and we will try our best to respond to your queries or questions. Installing TensorFlow. My name is Mohan, and I'm going to take you through the process of setting up this TensorFlow development environment. As some of you may be aware, it's not that easy to set up the TensorFlow environment. There are several components, there are several possibilities. For example, you can set up on Windows, you can set up on Ubuntu. Now Ubuntu has multiple versions, which version to use, and then you have Python, which release of Python to use, whether to do a pip install, whether to do install using Anaconda, and how do you then link it up with Jupyter Notebook. These are multiple possibilities, and it takes up a lot of time to try all of these. So today what I'm going to do is
show you a tried and tested method of setting up the TensorFlow environment. And this will help primarily those who are starting with TensorFlow so that they don't have to waste so much time on setting up the environment and experimenting with the installation and setting up of the environment. Now, what we are going to do is I will show you a method by which it is a tried and tested method. And of course, TensorFlow homepage has an install page and it shows you some ways to install. But again, the challenge is the same. There are multiple versions, multiple methods shown there. So it's highly confusing for somebody who is new as to decide which path to take. So in today's session, what we are going to do is we will set up TensorFlow on Ubuntu, and I'm going to show you in a virtual box. But then if you are using a laptop with Ubuntu installed, you can straight away use the same method. However, we need to keep one thing in mind, that the various releases and versions of Ubuntu and Python and then TensorFlow, not all of them are compatible with each other. So these versions and releases need to be very specific. So I will tell you which is the version and releases, what combination is best suited for you to get started. And later on, of course, you can then experiment with other possibilities and other releases and so on once you get familiar with TensorFlow. To start with, I would also like to mention that it is a good idea to install or start with Ubuntu environment or a Linux, any other Linux also. But here we will focus on Ubuntu rather than Windows. So for those who are already, let's say, using a Windows system, the question may arise, what do we do? But there is an easy option. As you can see, I'm actually using a virtual box. So you need to install virtual box. Let me just show you. So this is the virtual box, Oracle VM virtual box. And there are tons of videos on YouTube how to install a virtual box and how to create a Ubuntu image. I think we will not spend time on that. But if you're using Windows, and my preference would be to set up a virtual box and set up your environment in Ubuntu image. So we will start by assuming that you have an Ubuntu environment, especially release 14.04 LTS. There are multiple Ubuntu versions, and again, we will not try to get the latest and the greatest versions or latest and greatest releases, but the focus here is to take the releases and versions which are working and where you will not waste time. So the setup process will be smooth if you stick to these releases. You can of course experiment later on with other versions and try out, but here we will be working with Ubuntu 14.04 LTS, and we will use Python 3.4, and we will use TensorFlow 1.5. This is a tried and tested combination, and I would also recommend that you use the same if you want a smooth start. And so let's get started with that. Let me log in to my Ubuntu system. Okay, so we have the Ubuntu system running here. Now, if you go to tensorflow.org, there is a page which mentions how to install TensorFlow, and as you can see, there are multiple possibilities. You have Ubuntu, you have Windows and Mac OS and so on and so forth. And if you go to Ubuntu, for example, further you will get multiple options, whether you want CPU or GPU, and whether you want to do pip install or using a virtual native pip, virtual env, Anaconda, and so on and so forth. So all these options are very complicated, or rather they're very confusing, I would say, not complicated, depending on whether you're expert or, of course, I am talking about beginners here. But if you click on some of these options, they may look very easy. So for example, if we go back and if you select, for example, native pip, it may appear like, oh, this is just, one single or two steps and that's about it. Everything gets installed. You see here, it should be just one step install. If you say pip3 install TensorFlow and everything gets installed. Unfortunately, it doesn't work that way. So it's not as easy as, so don't get kind of fooled by the simplicity of the documentation here. Again, it's not their fault because of the multiple combinations of releases and so on and so forth. It is not that easy. So what we will do is we will take a slightly roundabout method, which is using
Anaconda, which has a few more steps, but you're sure that this is going to work. So that is what we are going to do, and that's what I'm going to show you. So what are the steps involved? Of course, I will not go exactly by what they have mentioned here. As I said, I will show you the steps which are again sure shot to work, whereas here again, if you follow just this document, there will be some variations which they have kind of not documented. So that's the reason I will show you the steps separately. All right, so these are the main 4 steps. You need to download and install Anaconda, and then create a virtual environment with Python. And the release, as I mentioned, is Python 3.4, and we will install TensorFlow version 1.5, and then we will install and configure Jupyter, which will be our development environment. All right, so let's get started. This is our Ubuntu, and let's get a terminal started here. And okay, yes, so all right, so we started the terminal, and then what we'll also do is we'll go to the Anaconda website because we need to install Anaconda. We need to download and install Anaconda. So for that, you need to go to the Anaconda website. So you can just open a browser and Google, and you will find the Anaconda website. So this is the site, anaconda.org. Click on this link and it will take you to the Anaconda website. You don't have to sign up or anything like that. Just look for the download Anaconda. So just click on that. It will take you to the download pages, and it automatically recognizes that you're on Ubuntu. So it will show you the links to download. All right. So as you can see, it has recognized that you're on a Linux operating system. So you can just click on this download, and it will start the download. There are 2 versions, of course, Python with Python 3.6 and 2.7. I recommend you start with Python 3.6. Now, just want to clarify that we will be actually using Python 3.4. This is just for the initial installation, but subsequently when we set up the virtual environment, you will see there is one more step there where we set up the virtual environment. There we will actually be using Python 3.4. So just that you're not confused. Alright, so it has started the download. We just say no thanks for this, and it is downloading. While it is downloading, you can click on this link saying how to install Anaconda. So there are a couple of steps mentioned there that we will be using. So let me just in the meanwhile click on this. For some reason the network is a little slow, so it is taking time. Alright, so once the download is done, we will be using the options that are mentioned here. Now the first step, of course, is we are already doing the first step, which is downloading the installer for Linux. The second step is not mandatory, so it's an optional step. Most often you can actually skip that. And third step is what we are going to do. And since we are using, at this point, we are using Python 3.6, we should use this command. So basically, the terminal we have opened here is to use or to run this command. That's the reason I opened this terminal. However, make sure that the download is complete before you run this command. So we'll just wait for a couple of minutes and we'll come back once the download is done. Alright, so as you can see, the download is done. This is a fairly large file, so if you're on a slow internet or low internet bandwidth, then it might take quite a while. It's about 578 MB, and so this is the file. Now what you need to do is you need to go back to this installation steps, and let me minimize this, and yeah. So this is the command that you need to run. So you can just directly copy and paste this command from here. Okay, so I do copy, right mouse click. Now it will ask you a bunch of questions as documented here. So most of them you need to just say enter or yes, and that's about it, except for the last step. I will just show you what I mean. And here you need to press enter multiple times just to make sure you agree to all these agreement, the license agreement and so on and so forth. So once you do multiple enters, it will bring you to the next step. All right. So now here again, they say, do you accept the terms? You just say yes and then press enter. And here it will ask you a couple of questions, and pretty much you need to just go for the default version, press enter to confirm. You just say press enter, and this is primarily when it will pretty much start the installation process of Anaconda. This might take a little while, depending again on your internet speed, so you need to have some patience. We will also probably come back once this installation is done, or if it asks for any further questions. Alright, so here you'll get again one more question. Do you wish the installer to prepend? So you just say yes for this question and keep going. Now the last question, I think we are pretty much at the end, and that is about Microsoft VSS, I guess. Yeah, VS Code. So for this you can just say no, because we will not be using this, and that's it. You're done. So this is completion of installation of Anaconda. So it's always a good idea to exit and start a fresh terminal. Okay, so let's start again a terminal. So we are done with the installation of Anaconda. The next step is to create a virtual environment with Python 3.4. So for that, this is the command conda create -n, and this is the name of your virtual environment. You can give any name, but for easy reference I have given as TensorFlow, and we have to specify the Python version. As I mentioned earlier, we will be using the combination of Python 3.4 and TensorFlow 1.5. Now this is not the latest version. Python has probably 3.6 at this point at the time of creation of this video, and even TensorFlow probably has the latest version as 1.7, but then these combinations sometimes may not work, and I found that after several trials and errors, 3.4 with 1.5 seems to be most reliable, and that's the reason I have chosen this. I would recommend you to try with this first if you're a beginner, and later on maybe you can try out the other permutations and combinations. Alright, one step I just wanted to show you is before we do the installation or creation of the virtual environment, if you want to just clarify or confirm whether Anaconda has been installed or not, you can run what is known as Anaconda Navigator. So you just say Anaconda Navigator. Okay, we need to edit this part. Hold on one second. I guess it is. Alright, so you see here when you start Anaconda Navigator, this Anaconda Navigator will open up. That is an indication that Anaconda has been installed properly. So that's just a quick check, and you don't have to do anything. Just you can go back and close it once this comes up, and then in the meanwhile let me just open one more terminal for the creation of the virtual environment. And yeah, so this is your Anaconda Navigator, and you can just say okay, don't show me, and you just say okay, and then you can close this. You can say file, you can do a file exit, or you can click on the close button, whichever. Alright, so we will exit from here. We have a terminal open here. We will use this for our next steps. Alright, so what we have to do now is type in this piece of code or this command. For some reason copy paste is not working, so it's a small command, so it shouldn't be that big of an issue. So we say conda, and we say create. So this is the command for creating a new environment /-n, and then we give the name of the environment. So we can give any name for convenience. I'm just calling it TensorFlow, but you can actually name it anything. And then we need to specify with which version of Python. So we say pip Python, and then that is equal 3.4. Okay, so it will create an environment. This will take a little while. It'll ask you a question, just say yes, and then it will be done. So this is just a warning. You can simply ignore that. And for the question that it asks, you just say yes, and I think you should be good. All right, so it says, do you want to proceed? You say yes, and then enter. This will again take a little time, so we will probably move forward and then come back once this is done. All right, so the environment has been created. Now, it's always a good idea to, whenever some of these steps get over, or each step gets over, you just exit the terminal and start afresh with a new terminal. For some reason, sometimes it causes problem if you continue. So I found that it is a safe practice to each time exit the terminal and start afresh. Now that we have an environment created, we can, by the name TensorFlow, you can enter that environment by calling the command source activate TensorFlow, or the name, whatever name you have given. So you'll see here, once you do that, you will get this, the name of the environment will be shown here. So it is like your own, again, a special environment within the system. And from here onwards, you can do other stuff like actually installing TensorFlow and so on. And you will see that it has installed Python 3 here, so 3.4, right? So it is installed. That's what we, during creation of this environment, we wanted Python 3.4, so that is what it is showing. But we are not yet done, so we need to still install TensorFlow. So in this environment, you need to run a command which will actually install the correct combination of TensorFlow. Now this is, as you can see, it's a slightly complicated command, pip install -- ignore install. So what we can do is from within here, we can go and go to TensorFlow install page, and there is a sample code there. You can pick up from there so that you don't have to type in so much. So we say TensorFlow.org, and I'll also open up probably a notepad here so that we can construct that command and go here. We say Ubuntu. If you come further down, there will be, by the way, we are doing CPU installation. I think that is clear. We are not, there is a possibility to do GPU as well. We will probably create a separate video for that. And if we go here, yeah, so again, you probably, if you follow the entire document out here, it may still not work. So I do not recommend that for now, at least for beginners. But just to copy this command, because this is a fairly complicated command, so this is much easier to copy it from here. That's the reason I'm on this page. And we will then modify it according to yes. Okay, let's say copy. And don't do it directly here because that is probably not yet the right command. Let us go and create a notepad page, empty document. I'll just say tf.txt. Okay, this is just a temporary file. What we need to do here is we need to adjust this command to suit the versions that we are installing here. So let me just explain what it is, what you need to do. So first thing, you can get rid of this one. Yes, okay. Now here, these parts you can simply ignore. Here you need to go and change it to version 1.5, and I think we are good with that. Okay, so the CP34 indicates your Python 3.4. So later on, when you're trying to experiment and if you want to do other combinations of TensorFlow and Python version, then you can change this. For example, you can change this to 3.6. Both these places you need to change this to 3.6 if you're using with Python 3.6. And similarly, if you want the latest version, which is of TensorFlow, which is 1.7, you need to change this to 1.7 and so on. But at this point, to start with, if you're a beginner, I would recommend that you stick to this TensorFlow 1.5 with Python 3.4. This is tried and tested and it works. Okay, just a word of caution that just by changing these versions, the whole thing will not work. There may be other places where you may have to, some of the steps may change. So just a word of caution that just by changing this, if you want to try out with a different version, some of the steps may also change. So you don't think that just by changing this one particular command you will be fine. Okay, so that's been my experience. So to start with, I would recommend use this particular combination. All right, so it looks good. TensorFlow 1.5, and let me just reconfirm with my notes, and I think it looks good. So this is install, ignore 1.5, CP34, CP34, and so on. Okay, so let's hit enter. So it started the process. Again, this might take a little while, so we will pause the recording and then get back when the installation is done. Okay, so looks like this installation is done, and as always, let us exit and then come back. Now you're currently in the environment, virtual environment, and it's a good practice before you exit out of the terminal to come out of the virtual environment. So just like you did source activate, you need to do source deactivate and the name TensorFlow. Okay, you will come back to the original command prompt, and then from here you can do an exit. Now we need to validate whether the TensorFlow installation has gone through properly or not. So the way to validate is to first start Python and then import TensorFlow library, see if it imports without error. So that's the best way to validate. So we'll open a terminal, and whenever you want to get into the environment, this is how you have to do. Come to environment and then say source, and obviously you can also use existing. So source activate TensorFlow. Okay, so we do this, and you need to run Python from here. And remember, you should say Python 3 because you have installed Python 3.4. Now here, when you say import TensorFlow as TF, when you get back a prompt like this without any errors, that means TensorFlow installation has been successful. If TensorFlow was not installed properly, you will get an error saying TensorFlow is not available or module doesn't exist or something like that. So TensorFlow installation is done, but now we will go through the process of installing Jupyter Notebook so that you can do your development. So let me just exit, and in order to install your Jupyter Notebook, which is going to be your development environment, we will first install IPython using conda. So conda install IPython, and then pip install Jupyter. So let's first do the IPython. Conda install IPython. Again, it will ask you a question saying these are the components. Do you want to install? You just say yes. All right, you say yes. And then once again, it will take a little while, so we might pause the recording and come back once it is done. Great, so that did not take much time anyways. So we will, as usual, we will exit, which is source deactivate TensorFlow, exit, and then we will start a fresh terminal in order to install Jupyter. Now in some places they may say install Jupyter using pip3, but in my experience it did not work with pip3, and that's the reason we will use pip. However, just keep in mind you need to first go to the environment. So source activate TensorFlow, and you need to use this command, which is pip install Jupyter. Usually when you're on Python 3 you use pip3, but as I said, it did not work. So in my experience it works with pip install and not pip3. So pip install Jupyter. I hope you already noticed that it is JUPYTER and not JUPI. So again, it's probably taking a little while. We will pause the recording and come back once it is done. Okay, so Jupyter installation is also done. Once again, you need to It's a good idea, not you need to, but it's a good idea to come out of this terminal session and then start afresh. So we exit and we have a fresh terminal already available here, and we will once again go to TensorFlow and we say Jupyter Notebook. That's how you start your Jupyter Notebook. So this looks good. Now only thing is, since we are running for the first time, what you need to do is, if you come back to your command prompt, it will show you that if you are running it for the first time, it will say that you need to copy paste this link. So you can just, for the first time, only once, you need to do this, copy this and paste it in your browser. And remember, this is only the first time when you're running Jupyter. You need to do this. Subsequently, you don't have to. It will automatically open up. Alright, so now that we have Jupyter installed and it starts up, we need to test whether TensorFlow is working fine or not. And in order to do that, you can create a new notebook and you say import TensorFlow as TF and shift enter. If everything is fine, TensorFlow is installed properly, you don't get any errors, and then it works fine. This is an indication that TensorFlow got installed successfully, and that's about it. So that's all about installing TensorFlow with Python 3.4. So remember, this is installation of TensorFlow 1.5 with Python 3.4 on Ubuntu. And once again, in case you have a Windows system, in fact I have also done it on a Windows system, you can use VirtualBox to create a virtual environment, Ubuntu environment, and then follow these steps. And there are tons of videos to create VirtualBox, and that's the reason we have not included those steps in this. And if there are any comments, there are better ways to do this, please mention it in the comment section below, or if you need any further help, just mention it, and with your email we will respond to you. Diabetic retinopathy is a condition which can lead to blindness, and it is caused, as the name suggests, due to diabetes. And there are ways to detect this early on and maybe cure it and prevent blindness. So how can we do something like that? There is research going on, and one of the techniques used is deep learning, which is a part of neural networks and which is a part of artificial intelligence. The way it works is hundreds of thousands of images known as fundus images are sent to the neural network, and the neural network is trained with this labeled information. Now these images, we know whether they are good or they are defective, or there is a disease in this eye or there is no disease. So that labeling is done. This labeled information is fed to the neural network. The neural network uses deep learning, and it will learn to detect if this from the image to find out if this disease exists, so that when a new image is fed, it will be able to identify whether the eye is healthy or diseased. So that's one of the applications of deep learning, and in today's session we are going to talk a little bit more in detail about what is deep learning, what are some of the libraries that are available to develop deep learning applications, and then we will zero in on TensorFlow. TensorFlow is one of the most popular, and it's growing in popular libraries, open source libraries for performing deep learning and AI. So we'll talk about what TensorFlow is and how to write a code in TensorFlow. The language is Python, but TensorFlow has a certain framework in which you need to write the code. So if you're writing like a regular Python program, it will not work. There's certain structure to writing a program in TensorFlow. So we will talk about that, the various elements of TensorFlow programming, and then we will discuss a little bit about one of the types of neural networks. Now there are neural networks come in different flavors, CNN and RNN and so on and so forth. So we will talk a little bit about recurrent neural networks in this tutorial, and then we will towards the end show you a small demo of how RNN can be used to do some time series analysis analysis and do some predictions. Okay, so with that, let's get started. So what is deep learning? Deep learning is a set or a subset of machine learning. There are certain specialities, there are certain ways in which we perform the machine learning, and that's why it is called deep learning. For example, deep learning uses neural networks, and neural networks are kind of a simulation of the human brain. And deep learning also involves primarily analyzing large amounts of unstructured data compared to, let's say, traditional machine learning where we normally use structured data. So this unstructured data could be in the form of images, it could be in the form of video, it could be in the form of text. So that's what deep learning is about, and the term deep comes from the fact that your neural network can have multiple layers as shown here. That's where the term deep is coming from. So this is known as a deep neural network. Alright, so in order to develop some deep learning algorithms, or not algorithms, but in order to develop deep learning applications, there are certain libraries available to us which makes development of deep learning applications easier. And this is a kind of a list of some of the libraries. This is by no means an exhaustive list. TensorFlow is by far the most popular one, and that is what we are going to focus on in today's tutorial. But there are a few others like Torch and Theano and Keras, and Keras has actually now become a part of TensorFlow. It's now integrated with TensorFlow, and it is like considered one layer above TensorFlow, but it is also by itself a separate library. So this tutorial talk about TensorFlow. First of all, why is TensorFlow becoming so popular? Why should we use TensorFlow? One of the key things about TensorFlow is it makes it easy to develop the code. So there are a lot of APIs readily available which we can use and don't have to rewrite some of the code that otherwise would have been time consuming. And therefore it speeds up the process of modeling and training the model and so on and so forth. So that is one key component. And obviously the chances of errors in the program are also reduced, and other important aspect is it is highly scalable. So you can write your code and then make it run either on CPU or GPU and across a cluster of these systems for doing, let's say, for the training purpose. Primarily training is where a large part of the computation goes. A large amount of effort, time, energy goes into training the model, and of course you don't do it once, but you need to do multiple times because you train it, you test it, you find there are some issues, again go back and train. So anytime you're training the model, it needs a lot of computation power, and TensorFlow actually helps in, and therefore you need distributed computing because if you need to process large amount of data. So TensorFlow makes it easy to write the code in such a way that can be run in a distributed manner, either using CPUs or GPUs. GPUs are graphical processing units. You must have heard about them. They're becoming very popular. NVIDIA is one of the leaders in this space. So they are really very good at performing mathematical computations because it helps in performing like matrix multiplication and so on. So GPUs play a big role in deep learning, and of course it has integration with C++ and Python APIs, so it makes development that much faster. So what is TensorFlow? TensorFlow is an open source library. It's not a separate programming language by itself. It is a library, and you can use any of the common programming languages, and Python is by far the most common language with which TensorFlow programming is done. So you can import this TensorFlow library into your Python program, into your Python environment, and then you can do your deep learning development. And there is a certain way of doing this program, or the way it is executed. So you create first your nodes, and then it goes in a kind of a graphical execution way. So everything is a node, and the data is stored in tensors, and then there is a kind of a data flow along these tensors. So that's the reason why it is also the name comes as TensorFlow. We will talk about what are tensors and how the graph is created and so on and so forth as we move forward. So first of all, what is tensor? Tensor in TensorFlow stands for, it's a mathematical object, and you can actually store complicated data in kind of multi-dimensional arrays. So that is what is tensor all about. So this is like a place where you store your data. That's one of the simplest ways to define a tensor, and this can be in multi-dimension. So that is the more important thing. So for example, you have arrays or just vectors which are one-dimensional, but and then you have matrices which are 2-dimensional, but tensors can be more than 3, 4, 5 dimensions. And therefore, it really helps in keeping the data very tight in one place and then performing all your analysis around that. So this is, for example, a tensor of 5 by 4 dimension, and this is a 3 by 3 by 3 dimension, which is basically the previous one was a 2-dimensional tensor. This is a 3-dimensional tensor, and there can be more dimensions as well. There are certain aspects, or there are certain terms of tensor. For example, what is a tensor rank? Rank is nothing but the dimension of the tensor. It starts with 0. 0 is basically a scalar, which is like, it's not a vector. It doesn't have multiple entries in it. It's a single value. So for example, s is equal to 10. This is a scalar, and this is considered to be, if you're storing it in a tensor, it is considered to have a rank of 0. Then you have a vector with a 1-dimensional vector, let's say. So this is a rank of 1, which means it has a sequence of values in it. Like in this case, it is v is equal to 10, 11, 12. So this is rank 1. Then you can have 2-dimensional matrix, which is supposed to be of rank 2, and then it can have rank 3, and so on and so forth. And then there can be of various data types. You can store data of various data types which are supported by tensor. For example, float 32, 64, int 8, and so on and so forth. So this is a list of data types that are supported. Then comes the graph. So what is a graph? Everything that the program that you write in TensorFlow is actually, first step is building a graph, and then you execute this graph. And therefore what happens is, you will see when we go into the code, it's not like a normal sequential code where one by one the steps are executed. No, the code is written in such a way that you first build the graph, and then you create a session and execute the graph. And what is a graph? Graph has what is known as nodes. So these nodes are operations, and remember, in TensorFlow world, everything is an operation. If you define or declare, not really declare, but if you assign a variable, create a variable rather, that is an operation. So it's not necessarily that you have to add two variables. Even if you create a variable, that is considered as an operation, and that becomes a node in your graph, right? So every time you assign a variable, it becomes a node. And then of course you perform some mathematical operation, that becomes a node, which is like you add two variables, multiply two variables, each of that becomes an operation or a node. And you start by building up these nodes, and then ultimately you execute these nodes in a graphical format. And that is basically how TensorFlow program is structured. So here's one quick example. So let's say you want to perform a calculation like this, where f is equal to 5 times of a plus bc, right? So what do you have to do? First thing you need to do is have these variables a, b, and c, right? So you see here these become, or they translate into 3 nodes actually, right? So, and they are also called operations, by the way, in TensorFlow world. Just having a variable is also an operation. So you have a variable a, maybe you can have a value of 4 here, b has a value of 3, c has a value of 5, and each of these is a node within a graph. So this is the first step of building the graph. So you have your variables. Then the next step of building the graph is to do this multiplication, b into c. So that is a proper mathematical operation. So this is actually also a node. P is equal to b into c. Then the third step is you add a to bc, so which is equal to q is equal to a plus p. So this is 3, this is a 4th node, this is a 5th node. And then you multiply 5 to this, so that is another node, and then you get the result, right? So you see here there are 1, 2, 3, 4, 5, 6 nodes. So your first step you need to do when you're writing your code is actually each of these you define each node, and then as a kind of the last step you say, okay, create a session, and you say you execute this node, which in turn will go back and execute each of these nodes to get those values and so on. So that's the way the program flow happens. Now, there are certain elements of TensorFlow programming. We will talk about that. Unlike other programming languages, variables in TensorFlow are actually of 3 types. Variables are where you store your data within the program, right? You're all familiar with common term. You have variables in your program. Anything you want to store in your program, it's actually a variable. But in TensorFlow, there are 3 types, and variables is actually one of the types. What are the 3 types? You have constants, you have variables, and you have placeholders. So there are 3 types actually. Okay. So we will talk about each of them. Constants are something which you assign a value and you cannot change it during the course of your program. Okay, so this is something like the number of hours in a day, that is equal to 24, and that will never change. Something like that. It's a very quick analogy. So that is what is known as a constant. It will never change. So that if you have something like that in your program, you have to declare that as a constant and assign a value. Okay, so in this case, this is how you assign a constant. So tf.constant, and the value is 2 here, and you can optionally specify the data type. Otherwise, TensorFlow is intelligent enough to say what data type it should be, but if you want to explicitly specify, you can specify data type. So this is one way of creating a variable. Another way is this one, where you don't explicitly specify the data type. It just says 3.0. It is understood, because the value you are assigning is a float, it is understood that the data type is float 32. All right, so this is constants. And now the difference between constants and variables is that these values, for example, the value of a, you cannot reassign. You cannot, throughout the course of your program, you cannot change that the a from 2 to 3 or 5 or any other value. A can have only a value of 2. Similarly, b can have only a value of 3. You cannot change that. That is a constant. Then you can create variables. So variables are like in any other programming language, we have variables. You can assign some initial value and you can keep changing as you, throughout the course of your program, you can keep changing. So, and the way you declare your variable, or you define or you create a variable, is somewhat like this, tf.variable. Now, one thing you need to observe, variable comes with a capital V, whereas constants and placeholders has a small p. This is something initially when you're starting up, this you may have some difficulty. For whatever reason, they have used something like this. But yeah, that's how it is. Just keep that in mind. You may get some error sometimes in the beginning. So variables, when you're creating, the V should be capital V. And the type of the variable can, again, you can explicitly mention, or you just give it a value and it will take the data type. Automatically it will assign the data type. So W in this case is a variable, B in this case is another variable. W has an initial value of 0.3, but then during the course of your program, you can change that. You can reassign some other value. 0.3 can become 0.5. That is all possible because it is a variable. X here is a placeholder. So we'll see what is a placeholder in the next slide. So what is a placeholder? Placeholder is somewhat like a variable, but this is primarily used for getting data from outside. So that was the idea behind creating the concept of placeholders. Now, what is the difference? Typically, when you're performing a deep learning exercise, you cannot get all your data in one shot and store it in memory, because that will become huge. So you typically will get your data in batches. So let's assume you want to train your model and you have 1 million images to perform this training. So one way of doing it would have been, you probably create a variable perhaps and load all these images into that variable, and then you analyze it. But that's not a very smart way, because if you bring all of those million images into memory, it, depending on, of course, the size of your hardware and so on, that might slow down. There may be performance issues and so on. So that's not very smart. So another way of doing it is, instead of getting all the million images, you get, because remember, it is not just storing the images. You need to perform training is an iterative process, and you need to put through these million images maybe another 100 times or 1000 times to train your model. So it's not just the storing of these million images, but then processing of these million images that takes up another large chunk of memory. So overall, not very smart. So they have come up with this fantastic idea of a concept of placeholder, whereby using placeholder you actually read your data in batches, and maybe out of the million images you get 1000 images at a time, process them, and then get the next 1000 and so on. So that is the idea behind the concept of placeholder. So placeholder is primarily used to what is known as feeding your model. So you read from somewhere from outside and then you feed it to your graph using this what is known as a variable name. This is a variable name. Feed_dict is a variable name. So when you're running the session, you specify how you want to feed the data to your session, to your model while you're training the model. So that is the concept of placeholder. Now, I know even if you have a programming experience now, this can be sometimes initially especially a little difficult to understand. But when we move forward, as you see some examples, I think it will become much easier to understand how this is done. Okay, so the first thing to remember here is there are 3 types of of storages within the TensorFlow programming. One is the constants, then we have variables, and then we have placeholders. Now what else? Then we have the other component is the session. As I said, you have now using these, you have created your graph, let's say, and once you created your graph, now you need to execute this graph. The only way to execute this graph is by calling what is known as a session and then the method called run. That's the only way to execute your graph. So that is another component here. So you create a session by, this is a variable. SESS is a variable. You can give any name here, but the method that you need to call is tf.session, and then you have an instance of a session, and then you call the run method and pass the node that you want to execute. Like in this example, let's say you want to do a calculation of c is equal to a plus b. So there are 3 nodes, as I explained earlier. Even a constant or a variable, everything is a node in TensorFlow. So you have a as a node, then b as a node, and both of these are constants. A has a value of 2, b has a value of 4, and then a third node is c, which is actually in real term also it is an operation, which is a mathematical operation of addition of a and b. So we have a node which is c is equal to a plus b. So that is your third node here. And then you are saying, okay, create a session. You're creating a session and you're saying run this node, because that is where you will get the results, right? So you're saying run this node. This in turn will result in executing this as well, whereby a will be created with a value of 2, b will be created with a value of 4, because these are prerequisites, and then c will be, the addition will be done, and then you get the result 6. All right, that is about session. Now let's take a simple example of a linear regression, how it works in TensorFlow. This is a small code example. So if you want to perform a linear regression where obviously the model will be y is equal to mx plus b, and with the given data you want to obviously come up with the values of m and b, which are the coefficients, right? So let's say we want to do something like this. To start with, you can use, again, we use Python here. So the traditional Python libraries like NumPy and Pandas, all of that is available to us. We can use them along with our TensorFlow library, because TensorFlow is nothing but one of the libraries. Okay, let's say we create some random data, test data or artificial data, and this is how you create linearly separated or evenly separated random values, right? Lid space is basically you create random values between 0 and 10 and 10 random values, and they are linearly or evenly distributed. That's what we are doing here. And we are adding some, to give it a little flavor of realness, we are adding some random values as well. Okay, so that is what we are doing here. So this is how the data looks, x underscore data, which is our independent variables, and similarly we are creating some random values of dependent variable as well, right? Y underscore label is our dependent variable. So if we do this and then if we plot, this is how our data looks, right? So if we did not add these randomness, then you would have actually got all the dots in a straight line. So we don't want that. So that's the reason we are adding the randomness as well. So this is how it looks. Now we want to find the best fit for this. All right. And again, some of you are not familiar with machine learning concepts of linear regression and so on. You may want to watch some of our other videos where we have created basics of machine learning and so on. The concept of linear regression, all the algorithms are explained there in detail. But very briefly here, what is a linear regression? Linear regression is the best fit. So you need to come up with an equation of a line which will basically, let's say, pass through these data points in such a way that the error is very minimal, right? So the line obviously will not pass through all the data points, but it will lie somewhere in between, and when you calculate error, it will be minimal. That's the idea of training this. Okay, so how do we do it in using TensorFlow? So we assign some variables. So m is a variable and b is another variable. Remember, this is how we create these variables, right? So tf dot variable tf, because we are creating variables, by the way, because they cannot be constants. The values cannot be fixed. And why are these values 0.39 and 0.2? Again, these are randomly generated. We just use an NumPy random function and we generated this. It can be anything. Initially you can give anything. 0 also can be given, but just to keep it realistic, we actually create some random numbers and assign them those values. Okay, then we find out what is known as the cost function. What is the cost function? Cost function is nothing but the error between the actual value and the calculated value. So with the given values of x, if we feed to this model, it will calculate based on the value of m at any given point in time. It will create what is known as the predicted value, which is y underscore hat. So in this case, when the first run, it will be 0.39 into whatever is the value of x plus 0.2. Okay, and remember, these values will change. That's why I have given as variable. They will not be constant, and the whole training process is to change these values and then come up at the end with some set of values of m and b, such that if you use that in this equation of mx plus b, then the errors will be minimum. That is the idea behind linear regression. Again, this is a little difficult to explain here, but if you actually watch our video on linear regression, it will probably become more clear. So here the assumption is that you are familiar with linear regression. Okay, so the error obviously will be the difference between the calculated value and the actual value. As we all know, we square that. So this indicates a squaring of that so that the negative values don't come into play. All right, then for training purpose, you need to use an optimizer. So what is optimizer? In our case, it is a gradient descent optimizer, and we need to specify the learning rate. So you give the learning rate as, in this case, we are giving as 0.001. Remember what we are doing here? We are just creating a node. None of these are being executed as of now. We are just creating the graph consisting of nodes. So let me go back. Here what I have done is m is created as a node, b is created as a node, and similarly here optimizer is created as a node, which I will show you a little later. And then when we say train, that is again another node, it will call this optimizer function and so on, right? So this is not directly running, but we are just creating the graph, and then this is where we will actually run that graph, and that is where the code will actually get executed. Now before that, one important thing to be remembered: in TensorFlow, whenever you create variables, you need to create a node for initializing the variables, which will be executed in this session. Okay, whatever you can call anything here, this is just a name, but typically it would be called init, and we say tf dot global underscore variables underscore initializer. So all the variables that you would have created anywhere, they get initialized, and it is very important, and it is only for variables. Let's say in your code you only have constants and placeholders, then this line of code is not required. But if the moment you have variables, you have to include this line. Basically, what are you doing here? You're creating a node or an operation. You're not executing anything. You need to create an operation and then execute the operation within your session here. Okay, so this is something you need to remember. So you need to initialize the variables. So this is like you can write once and keep copying and pasting. That's it, right? Because you have this anytime you have variables. Now, all programs may not have variables. So there may be some in your test when you're doing some initial development. You may only do with constants and placeholders. Then you will not need it. But anytime you have variables, you need to do. Okay. All right. Good. So then the next step is to create a session. How do you create a session? This is kind of very, in a way, unique to TensorFlow. You use what is known as a with block. So we say with tf.session as ses, right? So in other words, it is somewhat saying like ses is equal to tf.session. You remember there are a couple of constructs for creating session. Like in the previous example we saw, let me go back here. So here we just directly said ses is equal to tf.session. This is one way of creating a session. But here what we need to remember is at some point, once you're finished with all the code, you need to close the session. Okay. So whereas if you're using something like this with block, you don't have to close the session, because the moment the with block gets completed, right, the session will automatically get closed. So that is the difference and the advantages and disadvantages of using a with block or not a with block. Okay. So here what we are saying is with tf.session as ses. That means it is indirectly we are saying create a session by the name sess, and as long as this with block is running, keep it active. The moment I exit this with block, you close the session, right? So you don't have to explicitly close the session. Okay. Anyway, so to start with, for beginners, just remember you just have to create a with block and then put the code within that with block and you're good. That's it. Okay. All right. So first thing is to start with the initial with block like this. This is the syntax. Then the first line of code will be to initialize the variables. Again, if you have variables. If you don't have variables, you don't have to write these two lines of code. Okay. Then the next is you need to run this training method, right? So remember, as I said, we have created all the nodes and pretty much train was our last node, and there are all other nodes which are dependent, or rather the prerequisites, right, for train. Train is my kind of the last part of the node. So that that is what I will do a run on, because that will give me the results, right? This in turn will execute the rest of the graph. So this train will go back and it will say, oh, okay, I need to do optimizer.minimize. And what is optimizer? Optimizer is gradient descent with a learning rate of 0.001. And then for doing this gradient descent, I have to use this model, which is mx plus b. So I need to calculate and keep changing the values of m and b and feed the values of x and y and so on. So it's like a chain reaction that happens, and ultimately the training gets over, and then you have the values of m and b. Remember, the whole exercise of actually training this is to come up with the right values of m and b. Initially we start with some random values, which is in this case 0.39 and 0.2 for m and b, but the training process, if you have done the machine learning module, you will see that training process basically involves changing these values of m and b so that the error is minimum. So at the end of this part, which is the running of the training session, you will end up with certain values of m and b. Now how do you get those values of m and b? Again, you need to run the session, and this is just a one time, and you say, okay, give me the values of m and b. Okay, so this is all, by the way, this is all within the with block. So the session is still active. Here you're saying run the training method, so it will run the training method, and the training method in turn will keep changing the m and b values based on the error that it is generating, the model is generating. And once the training is completed, and how does the system know the training is completed? We are specifying the epochs. Again, you must have done the machine learning module, so you will be familiar with epochs. Epochs are nothing but how many iterations you need to do. If you pass all the 1000 observations through the model for training, that is called one epoch. And so if you take this 1000 observations and pass it through the training model 100 times, that is 100 epochs. So that is what we are saying here. We are asking epochs is equal to 100. That means you pass this training data through our model 100 times. Once 100 times are over, it will exit. And remember, every epoch, the values of m and b will keep changing so that it is the error gets optimized or error gets reduced. So at the end of the training session, m and b values will have something different from what it has started off with. So those are the values that we will need here, which is basically m is the slope and b is the intercept. So that is the end of the training process. So we can basically display those details. And now you can use this to plot your model, the line that you got, the best fit line that you got. You can use the plot method to plot the line, best fit line. And you will see here, typically this is how it would be, right? So it is passing kind of in between all the data points, so that any point you take, if you calculate the error, it is minimal compared to, let's say, if the line was here, obviously many of them or most of them would have been errors and the error value would have been huge. So that's how you evaluate the results. All right, so this is my Jupyter notebook, and whatever I've shown you in the slide about the linear regression, I will just quickly show you in the actual code as a demo. So we have seen that what we are trying to do is create a model, which is a linear regression model, and train it and then test it. So this is the first section, which is importing the required libraries. And what we're doing here, as you can see, is we have regular NumPy, and we will be using that for doing some generation of data and so on. Then we have matplotlib to plot the results, and then of course we are importing the TensorFlow, which is what we are going to use for creating this linear regression model. So as a first step, we will create some artificial data, which is basically some kind of a dummy data, and we are just using NumPy to do that, and random number generator and a linspace to create some data. So this is how our x underscore data looks, which is our independent data, and the dependent data is y underscore label, which is the label data. In other words, we can also call it as label data, and we have created that, and this is how our data looks if we plot it, x and y. If we plot it, just a quick note, this randomness I also mentioned in the slides, this random form is just added so that the data doesn't look like it is artificial, right? So right now, if you see here, now it looks pretty much like some natural data. Okay, so what do we do now? Next step is to first create some variables, which are basically for our y is equal to mx plus b equation, m and b are the variables. Now there are two ways of doing it. You could have created variables with some 0 or something, both of them being 0, because you need to start with some random value. In our case, what we are doing is we are actually generating a couple of random values, random numbers, using the numpy random function, and we are assigning these two variables, right? So we created one value is 0.25 and another is 0.3, and since this is random, I can change this, but I will not change. Let's assume that this is 0.39, and I can actually, no, let us just change it so you are not confused, because every time you generate a random number, it can be any value. So it is 0.30 and 0.256. Alright, so I will now assign these two. I am creating these as TensorFlow variables. I hope you remember that in the slide I've shown you. These are the two variables. Then we need to create what is known as the cost function. And cost function is nothing but the difference between the generated value or the predicted value or the value created by the model and the actual value. So that is the error. That is the difference between that. And to avoid negative value, we do a square of that. So that's what I have shown in the slides as well. Then we have to define an optimizer. In our case, we will go for a gradient descent optimizer and with the learning rate of 0.001. Alright, so remember all this, what we are doing is we are creating a graph. This is not yet executed in TensorFlow. We are executing in Python, of course, but from a TensorFlow perspective, it is not yet executed. Only in session it will get executed. Right now we are creating a graph. So we created the graph for the training, for optimizer, for the initialize operation. We are creating an operation or a node. Okay, now that's all. It's all done. Now we created all the nodes. We created the graph. Now we have to execute the graph. So this is how we execute the graph. We create a session using tf.session, and then we specify how many iterations or epochs, which is 100, and then we run this. We run the train node. You remember there is the node for train we created, which in turn will go back and assign all the variables and all that stuff. Okay, so once the training is done, it runs for 100 epochs. Then we have certain values of m and b, right? That's the whole process of training. You start off with some random values of m and b, and the training will actually change those values and come up with a particular value of m and b such that the error is minimum. So we are done with that. And now we can check the values of, okay, I think we did not run this, sorry. So we have to run this. So this is run now. So the training is done. So now we will have a value in final underscore slope, which is equal to 0.87. And then in the intercept as well, 0.83. Okay, so we got m and b that we wanted. Now we want to evaluate the result. So we want to see using our test data whether this is doing, how this is doing. So we just generate some test data as well, and this is our test data looks. And if we draw the plot of our model, this is how it looks. So pretty much expected. The line lies in between all the data points, and this is the best fit line such that the error is minimal. Alright, so let's go back to the presentation. Now let's talk a little bit about recurrent neural networks. So neural networks are of different types. We have CNN, we have RNN, ANN, and so on. Now RNN is one type of neural network. RNN stands for recurrent neural network. The networks like CNN and ANN are feed-forward network, which means that the information pretty much only goes from left to right or from front to back, whichever way you call it. Whereas in case of recurrent neural network, there will be some information traveling backwards as well. So that is why it is known as a recurrent neural network. And each of these types have a specific application. So for example, convolutional neural networks or CNN are very good for doing image processing and object detection using for video and images. Whereas recurrent neural networks are pretty good for doing NLP or speech recognition and so on. Okay. So for the next few minutes, we will kind of focus on recurrent neural networks, and we will see an example of how we can use RNN to do a time series analysis. So in a typical neural network, this is how it looks, right? So where you have a neuron, and then the inputs are coming to the neuron, and then you have an output which goes to other neurons in the other layers. In case of recurrent neural network, what happens is you have the inputs, let's say at a given point in time, but then a part of the previous output also gets fed in along with the inputs for the given time. Now this can be a little confusing. So let's see if we can take a little expanded view of this. So this is another view of one single neuron, which is what is known as in an unfolded manner. Okay, so if we are getting inputs or data over a period of time, then this is how the neuron will look. Remember, these are not three neurons. This is one neuron, and it is what is known as, it is shown in a unfolded way. Okay, we have unfolded this single neuron over a period of time. So at a given time, let's say t minus 1, an input of xt minus 1 is fed to the neuron, and it gets an output of yt minus 1. Then the next instant, which is xt, at a time t, right, there is an input of xt, and then there is an output of yt. So this is a single neuron, but is displayed in an unfolded way. So this is like expanding it over a period of time. So let's start with this part here. This particular neuron gets an input at an instant t minus 1. Let's say time is equal to t minus 1. It gets an input of xt minus 1, and it gives an output of yt minus 1. Then when we go to the instant t, here it gets an input of xt, and it also additionally gets an input from this previous time frame t minus 1. So this yt minus 1 gets fed here, and that results in yt. All right, then when we go to the time t plus 1, there is an input of xt minus 1 at that given time, plus the input from the previous time frame, which is a time frame of t. That also gets fed in here, and then we get an output of yt plus 1. Okay, so let me explain once again. This is a single neuron. So these are not three different neurons. A single neuron seen over a period of time from t minus 1 to t plus 1. And unlike a regular feed forward neuron which only gets x, in this case the input is x and also another input which is coming from the previous time frame, and that is what this loop is. In this, on the left hand side diagram, this loop is indicating that. Okay, so on the right hand side it is represented in an unfolded way. Okay, so the input, if we take a time frame t for example, is not only xt, which is the input, which is the normal input at the time frame t, but it is also getting an input from the previous time frame, which is this yt minus 1 is also being fed as an input. That is the key differentiator here. Okay, similarly at the instant t plus 1, it is getting a normal input of xt plus 1 plus this yt is actually being fed here, and then the output comes as yt plus 1. Okay, so this is the construct of a recurrent neural network. Now recurrent neural networks again can be of different subtypes. It can be one-to-one, one-to-many, many-to-one, and many-to-many, depending on what kind of application we want to use. One of the examples is like the stock price. So you're feeding, so there is only one input. Only thing is it is spread over a period of time. So you're feeding the stock price input. That is what comes here as an input. And you get an output, which is again the stock price, which is probably predicted over the next 2 days, or 3 days, or 10 days, or whatever. So the number of outputs and inputs is the same. There is only one input, there is only one output. Only thing is it is spread over a time. So variables are not many. Then you have one-to-many. So there is one input, but you're expecting multiple outputs. What is an example of this? Let's say you want to caption an image. So how do you want to do that? What is the input that will go here? It's just an image, which is one input. But what is the output you're looking for? You're looking for a phrase maybe, right? Not just a word, but a phrase. So it's like cat is sitting on a mat, right? So the image is, there is only one image which consists of the cat sitting on a mat, but the output are like maybe 3 or 4 words, which is saying the cat is sitting on a mat. So this is one-to-many, right? Then you can have many-to-one. Examples of this are like you're feeding some text and you want to know the output, whether the text is what kind of sentiment is expressed by the text. It could be positive, it could be negative. So that's the output you're looking for. So you feed a large number of words, maybe the text may consist of words or lines or whatever. So that is what is the multiple inputs. But the output, all it says is the sentiment is positive. So it is just one output, or the sentiment is negative, just one output, right? So this is many-to-one. Then we have many-to-many. So what is an example of this? Let's say you want to do some translation. So how do you do a translation? You feed in a sentence maybe in a particular language, English, and then you want a sentence actually in another language. So that is like there are multiple inputs. One sentence can consist of multiple words, and the output also is a sentence consisting of multiple words. All right. So how do we implement RNN? This is an example of implementing an RNN for for a particular use case. So in our particular example, we have the data about milk production over a few months, and using RNN, we want to predict, because this is time series analysis. So RNN is good to do time series analysis. So using RNN, we want to predict what will be the milk production in the future. So let us see how we can do that. I will first take you quickly through the slides, and then I will actually run this in a Jupyter notebook. The code, I will run it in the Jupyter notebook. So this is how it looks, the code looks. So while this is TensorFlow, you still use the standard Python libraries like NumPy and Pandas and even Matplotlib to do some initial processing, getting the data, processing it, cleaning it, whatever. All that can be still done within the same program. So that's what we're doing here. We're importing some libraries like NumPy and Pandas, and then we read the data file. And if we plot the data, we see here it is the data for the years 1962 to 75, and we can see that there is a certain trend, right? So this is how a typical time series data would look. Again, some of you, if you're not familiar with time series and time series analysis and so on, I would recommend you to go through some videos around that, which will make it easy to understand this. So this is how a typical time series data would look. In this case, it is nothing but there is only one variable, which is milk production, and it is spread across several years. So it's going from 1962 to 75, and that value has been plotted. So if you see, there is a certain kind of a trend here, which is basically going upwards, and there will be some seasonality. So time series data has these three components, right? So it will have a trend, it will have a seasonality, and then it will have some randomness. So that's what this graph is showing. And now if we want to perform analysis on this, time series analysis on this, first thing we need to do is split the data into train and test. And in this case, we will just use a straightforward method, which is taking the data for the first 13 years. So the idea here is we need to train our model, right? This is time series data. So and we want to predict for the future. So the way we need to use this is we have to take the data for a certain period of time and train our model. And then we use a part of the known data so that we can then ask our model to predict for that duration and compare it with the known information. So what do we mean by that? So here, if you see this data, I will show you in the notebook as well, Jupyter notebook as well. This has 13 years of data. So what we are doing is we are taking the first 12 years and using that as our training set, right? So 12 years we are doing, and this has about, I think, 14 years of data. So we are taking 13 years of data for training purpose, and then we are using the last 1 year, remaining 1 year of data for testing purpose. Because here what we can do is this 1 year data, we know the values, right? Because if we want to compare the accuracy or anything like that, we need to know the values. So in this case, we know the values of this one particular year. So we will use that. But at the same time, we train the model for 13 years of data. And for the 14th year, we will ask our model to predict and then compare it with this known value so that we know how accurate our model is. I hope that makes sense. Okay. So that's what we are doing here. 156 is nothing but 12 into 13. On a monthly basis, we get the data. The next step is to scale the data. This is all regular data manipulation, data munching activity. And then you split it. You are basically assigning the train and test data to the scaled variables. And then you need to read the data in batches. So it is very important, as I mentioned earlier also, that instead of reading the entire data in one shot, you feed the data in batches. So in order to do that, we are writing a function for that. That's all we are doing here. So that is still here what we have done is regular Python programming. There is no TensorFlow as of now here. Okay, so far what we have done is preparation, data munching. Now what we are doing is actually training our model. So this is where TensorFlow now comes into picture. So we are importing, first step is to import the TensorFlow library. So this is how you do it, import TensorFlow STF. And then you can define some variables or constants, whichever way. Now here, of course, there are a couple of ways of doing it. You can create them as TensorFlow nodes, but that is a little bit of an overhead. We will just use the regular Python variables or constants. So here I am creating regular Python variables and I'm saying number of inputs is 1. So instead of hard coding, I'm just storing them as variables. So this is number of inputs is 1, number of time steps is 12, number of neurons is 100, and so on, right? And then learning rate is 0.03 and number of iterations we are saying is 4000. Then we create placeholders. Now we will be storing the independent variables in X and the dependent variables in Y, and this we will read from an external file. Remember, I told you placeholders are used for getting data from outside and then feeding it to our model. So that's the reason we have two placeholders, one for reading the X values and another for reading the Y values. In this step, we are only just creating the nodes, right? So this is just creating the graph. And similarly, we are mentioning what is the loss function and what is the optimizer and how to run the optimizer. And once that is done, you are initializing the variables and then you're creating a saver variable or a saver instance. So saver is basically nothing but in machine learning, you can train your model and you can save it for later use. So that's where the saving comes into play. We will see how to use that as well. And then the last step is to create your session and run this graph, right? So we are initializing the variables. Remember this, we run init, so which is nothing but this one. So we are initializing the variables, whatever are there. Instead of hard coding, remember in earlier case we were hard coding how many iterations. So here we are saying for the given number of iterations which are stored in this, maybe how many iterations we said is, what is the value of iterations? This is training iterations is 4000. So we specify that based on the number of training iterations. Next batch will basically fetch the data and then we run the session. We are basically saying train is the node which we will run in the session, and this will basically train our model, and this is more for printing. Every 100 times you print it. That's all. There's nothing more to it. So for example, the output would look somewhat like this. This is for 0, this for 100, next for 200 and so on. Okay. And then you save the model. You remember saver we created. So you save the model for later use. So this is our test data. Remember, we are doing this on training data, right? So once the training is done, we then try to create the inference on the test data so that we can compare how accurate this is. Right. So this is how the test set would look, and then we will basically restore this model, okay, because in the previous slide we created the model and we stored it. So now we have to restore the model and then run our test data against it and see what are the values that are predicted, what are the Y values, and then compare with X to see the accuracy. So train seed is what we are seeing here. So that is what will have the predicted values, and these predicted values, what we want to do is we want to create an additional column, because remember we need to compare, because we want to find out the accuracy of this model. So we need to compare the predicted values with the actual value. So what we are doing here is adding another column called generated and assign a value to that. All right. So this is the result of the prediction. And then if we need to reshape, because we have to show this in the form of monthly results. So that's what we are doing here. And once we generate the results and then display it, we can actually see it month wise here, and the actual and the generated values. Okay, so we create a data frame which is a combination of the actual values and the predicted values from the test set. And then we can plot to see how the trend is. As you can see, pretty much the actual value is in blue color and the generated or predicted value, the curve is in yellow color. The trend is maintained. So it will probably, it's not 100% accurate, but the trend is maintained. All right. So let's do one thing. Let's go into the Jupyter notebook and take a look at how this works in TensorFlow environment. Actually, the code, I will walk you through the code. This is my Jupyter notebook, and the data is taken from this particular link. In case you're interested, you can download it from there. And this is the data for the years 1962 to 75. The first thing we do is import these libraries, because before we start with the actual TensorFlow activity, we need to prepare the data and so on. So for that, you can use your regular Python libraries, which are like NumPy, Pandas, and so on. So that's what we are doing here. And then we read the data using Pandas into a data frame. So this is a data frame, milk is a data frame, and we will do some quick exploratory analysis just to see how our data is looking. Initial 5 records that we'll get, 1, 2, 3, 4, 5, that is the head. So it goes from 1962 January to 1962 May. Once we rechange, or basically we need to split this into month specifically separately. So that's what we are doing here, date to time. So we kind of do a little bit of a reindexing, and then if we plot this, this is how the data look. As you can can see there is a clear upward trend, and there is some seasonality and so on. But anyway, we will not break that up into those components. We will just use RNN to predict and test. Okay, so the next thing is to check some, if we can run like an info, it will tell us what is the information about this data set. So let us just run that. Okay, so it is just telling us how many total columns and what is the size of the file and so on and so forth. Again, in case you're interested in doing some exploratory analysis. So what we'll do next is we will take the 13 years of data for our training data set. So what are we going to do now? Let me step back. So what have we seen here? We have seen that there are 168 records, so which is nothing but 14 years of data. We now have to split this into our training and test data set. So how do we do that? I think in case of time series, we cannot do it like 80-20 like we do in normal splitting in normal machine learning process. Here it is time series data. So what we are going to do is we will take out of this 14 years, we will take the first 13 years of data and we will use that for training, and then we will test it with the last, which is the 14th year data. We will use it for testing. Okay, so that's what we are going to do here. So let's split that. So training set will consist of my 156 records, which is nothing but 13 into 12, right? My 13 years of data I'm taking for training, and then my test set will consist of the bottom 12 observations, which is last 1 year of data, which is the 14th year. Okay, so that's now done. Training and test splitting is done. The next step is to do some normalizing, which is basically we'll use our scaling, rather we will use min-max scaler, and we will just scale the data. And now we do it for both test as well as train. Now we are ready to create our RNN model. But before that, one quick thing: in order to fetch the data, we have to create a function. So that's what we are doing here. We create a function called next batch, and how you want to fetch the steps, they are all defined as our constants, if you remember, and that's what this function is all about. So we define that function. We will be calling that in our training method. All right, so from here onwards up to there, we are done with the preparation of the data and whatever functions or whatever are required. From here onwards is where the TensorFlow part starts. So the first thing we do is import the TensorFlow library. Typically this is a very standard way of importing the library. We say import TensorFlow as TF. Now TF is nothing but a name, so you can change it to TF1 or ABC or XYZ, whatever. So this part you can change, but by and large everybody uses this, so I would rather recommend you also use the same syntax. So you say import TensorFlow as TF, so it's very easy for others to understand as well. And then you declare or define a bunch of constants. That's what we are doing here. Like for example, the number of time steps, in this case it is 12, number of neurons, there are 100, number of outputs, it is only 1, and so on, right? And then the learning rate and all that, we are declaring or defining those variables in this particular block. Next is to create placeholders. You remember the placeholders are used for feeding the data. So we have X and Y. X is for the input, which is the independent variable, and Y is the output, which is the dependent variable. And in our case, these are not different characteristics or features, but it is the same one feature or one variable, but it is over a period of time. So that's the only difference. So that's what we are doing here. And now we need to create our network, right? The neural network. So in our case, we said we will create a RNN layer. Now there are different ways or different formats of RNN, which is probably not in scope of this module. So for now, we will just assume we are creating one RNN layer, and one type of RNN is GRU cell. So we will use GRU cell, and we use this APIs for creating our layer. So each cell will be with an output projection wrapper. There is a need for doing that. And again, the details of this we will probably do in another video where we talk in detail about RNN. So for now, we are creating a GRU cell with the wrapper, and the syntax for creating the GRU cell is like this: the number of units, which we said there should be 100 neurons. What will be the activation function? In this case, it is ReLU, and then number of outputs. In our case, it is only 1. Okay, so we create the cell here. Okay, then we got the GRU cell, and then we say what is our output, which is nothing but we get the outputs and the states and their states, and which is the way we get that is tf.nnn.dynamic_RNN. So if we call this and we pass the cell and the data, which is basically in placeholder. So again, remember, all we are doing here is we are creating just the nodes for the graph. So nothing is actually getting executed from a TensorFlow perspective. Okay. All right. So once that is done, now we need to pass this, calculate the outputs and the states using the dynamic underscore RNN method, and we pass the cell as a parameter and then the X values as a parameter. And if we run that, we will have the outputs and the states, and this is where we actually run the training method. So, or create, not really run the training method, but we create the nodes for the training and the optimizer. Then we have the initialization of the variables, and we save this model. We create a saver object just to save the model, because we will then restore it and run it to do our predictions. So this is what we will do here. So that is another node, and this is where we actually create a session and run the training. Okay, so let's go ahead and do that. That will take a little while because we said 4000 iterations. So we will allow it to finish. We will probably come back once the training is completed. All right, so the training is done. Now let's go and run this on the test data. So let's just quickly take a look at the test data set. So this is our 1 year data for the year of 1975. So if we see this is from January, February, and so on. And we will pass this to our model. So what are we doing here? We are restoring the model here, for example, right? This is the path that we have given when we were saving the model. Let's go back once and show you, let me show you where we did the saving of the model. Yes, so we saved the model here. So that again, we will restore that and we will use that to run it on our test data and see how well it predicts. So let's go ahead and run this. And this is just 12 records, so this will not take time. Remember, I told you training is what takes a lot of time. The regular inference, this is called inference, doesn't take much time, right? So it just depends on how much data. There were only 12 records here, so it was very quick. But in training, what we do, we pass this multiple times. There are iterations, 4000 iterations we did, for example. So that takes longer. And in general, in machine learning, deep learning, training is what takes the maximum amount of time. All right, so let's go ahead and see the results. We will, in order to plot it, we will have to kind of adjust the format of the results. Otherwise, we will not be able to see it in a proper way. And then we will, so this is our, so what we have done is we created a data frame which consists of the predicted value and the actual value. So this is the data frame. So this is the actual value. This is 834, 782, and so on. This is what our model has predicted. So it may not be so easy to see in a tabular format. So let's go ahead and plot it so that we can compare these two. So when we plot it, you will see that the trend is more or less maintained, right? So we go from the blue color is the actual values, and the yellow color or the orange color, whatever is it, is the one which is generated by our model. So it pretty much is following the actual trend. So not bad for such a quick iteration and training. So that is basically it on RNN. And let's go back to our presentation. Okay, so let's summarize. So what have we done so far? We talked about what is deep learning, briefly touched upon deep learning, and then we talked about what and why of TensorFlow, and what are the various other libraries other than TensorFlow for doing deep learning. And we saw a quick use case for linear regression, and then we did a quick use case for recurrent neural networks as well. So with that, I would like to conclude the session. Thank you very much for viewing this. And there are any comments or questions, please feel free to write it at the bottom. In case you want a response, you can put your email ID so that we can respond to you.
Mathematics for machine learning. My name is Richard Kirshner with the Simplilearn team. That's Get Certified, Get Ahead. We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, And then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So when we talk about types of data, we have in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range if you have 10,000 to 20,000. Number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true-false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative, numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's where we're talking about a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary. This is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have 2 variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept, which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. They kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had a reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, small case a for the top row. Or, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have two matrices of 2 by 2, and you just add each individual number in that matrix, and then when you get to the bottom, you have, in this case, the solution is 12, 10 plus 2 is 12, 5 plus 3 is 8, and so on. And the same thing with subtraction. Now again, you're counting matrices, you want to check your dimensions of the matrix. The shape, you'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at two variable. So this is a two variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5, 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. And it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of two matrices. Okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind, because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time, where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one. And it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to eigenvectors vectors and eigenvalues values. Eigenvectors vectors, the vectors that don't change their span while transformation, and eigenvalues, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigenvector. 2 is the eigenvalue. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigenvalue. And you can see here, vector after line transition, we have 3a. A is the eigenvector, 3 is the eigenvalue. So A doesn't change. That's whatever we started with. That's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigenvalues. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create two different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our two arrays, 10, 15, 29. And I went ahead and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as A plus B, I can also do A plus B dot T. And you're going to see that that will come out the same, the 30, 24, whether I transpose A and B or transpose them both at the end. And likewise, we can very easily subtract two vectors. I can go A minus B. And we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down the scalar so you can remember that. And what we're talking about here is I have this array here, U, and if I go A times U, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a two-dimensional vectors. It is the equivalent to matrix multiplication. And remember, we were talking about matrix multiplication, where it is the, well, let's walk through it. We'll go ahead and start by defining two NumPy arrays. We'll have 10, 20, 25, 6, or our U and our V. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of U comma V. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess, because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is, of course, 10. 10 minus 8 is 2. 4 minus 46 is minus 42, and so forth. So same as the subtraction as before, we just call it matrix subtraction. It's identical. Now, if you remember up here, we had scalar addition, where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply, if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication, and you can mix and match. When you get into really complicated back-end stuff, this becomes more common, because you've got layers upon layers of data, and so you'll end up with a matrix and a set of vector matrices that you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn, where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times, you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do, up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this, where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers, and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1, depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here. is that you create this preset matrix, and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind, 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then, of course, it equals the dot, A inverse of A with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go ahead and have here's our array. We'll go ahead and run this. And you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably really is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up, or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So it helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic. Traffic opens up, and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it'd go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here, and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that, and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. It looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from c to d and a to b of f of x of y dx dy equals the sum of a to b, sum of c to d of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals a change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick, and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff, because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x 2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits and built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught. There's your start value. So your function, your start value, there's all kinds of things that come in here that we can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. What this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does that come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you got to be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call her expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say, this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So we talk about the mean. It is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was at one point $24,000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where like you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, it's we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed, and then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is, and then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have like if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools, as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code, so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, whoops, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000. So the halfway mark is significantly below the average. Why? Because we have somebody in here who makes 189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample. And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000. So half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode, although the standard one's pretty good. We can of course do the range, which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in pandas. And so in pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which would just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it. of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically. But just in case, I always put it in there. Import matplot library, pyplot is PLT. That's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary df salary.plot history title, salary distribution, color gray, plot AXV line, salary the mean value. So we're going to take the mean value. Color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. You have our, in this case we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AXV line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, it doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all of that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. Nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about a hypothesis, you're usually trying to disprove it. If you can't disprove it, and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who are given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now, Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e., whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e., his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states whenever something is happening, a new theory is preferred instead of an old one. And so the 2 hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these 2 have 0 relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is a probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value. It is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. And the t-value, comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure our true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 2-300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95%. You have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated as under 1 in trillions upon trillions. So the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. There's how often you're going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this as one of the cases is rolling 2 dice and gambling. There's also a binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means that each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. Clearly 0.75 plus 0.25 equals 1. So that accounts for 100% of the game. Probability for getting K wins in N matches is calculated. And we're talking like, so if you have 5 games and you want to know if I play, how many wins in those 5 games should I get? What's the percentage on those? And the probability for getting K wins in N matches is calculated by Px equals K equals NCK, P to the K, Q to the N minus K. Here, P is the probability of success and Q is the probability of failure. And so we can do total games of N equals 5, where K equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers, and we end up with a 0.0009765,625. So a very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the P equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the number of wins to the probability and how that pans out with our binomial case. Continuing in our important terminology. Location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, if you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between 1 standard deviation. Around 95% of the results are found between 2 standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's that kind of funky U. It just means the mean. And then the sigma is the standard deviation, and that's the O with the little arrow off to the right, or the little waggly tail going up, the O with the line on it. So mu minus 2 sigma is your 95% of the results are found between 2 standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma, with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if we're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is a probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula. And it's really, it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math. But it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but you know, it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A. Prior probability of 10% people having lung disease. And then probability B. Probability that a patient smokes is 15%. And the probability of B, if B then A, the probability of a patient smokes even though they have lung disease is 5%. And probability of A is B, probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back-end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set my list. The result is 1, 2, 3, 4. So it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there. Is 3 in? Usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see in this case when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. And you remember we had a slide on this earlier where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set which is the product of the dice faces repeat equals in dice. And we'll go ahead and just run this. And you can see here it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence, and as you can see here when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something, let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y, remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome so we can see what that looks like. There we go. And of course I did forget to add the print in the middle because we're looping through and putting an end on the setup on there, so we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability, last line, so we can just type it in, we end up with a 0.3333 chance. And it's roughly a third. And we might want to make this look nice, so let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3? And so we're just going to divide those two numbers, and you can see here we get 0.116255, or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have, and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. I mean, a false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you know, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take, and there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing with the viruses, you really want this to be a high number. You want this true that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict quickly with our model. So test positive is the test positive plus the false negative on there. And we'll want to go ahead and do a demo on the naive Bayes classifier. Before I get too far into naive Bayes classifier, because we're going to pull it from the sklearn or the scikit, let's go ahead. Kind of an interesting page here for classifiers. When you go into the sklearn kit, there's a lot of ways to do classification. And I'll just zoom up in here so you can see some of the titles. There's everything from the nearest neighbor, linear, but we're going to be focusing on the naive Bayes over here. And this is just a sample data set that they put together, and you can see how some of these have a very different output. The naive Bayes, remember, is set up as probably the most simplified calculator or set of predictions out there. And so what we've been talking about with the true false and stuff like that, where there's a belief that there is a independent assumption between the features, where the features are very assumed to have some kind of connection, then we can go ahead and use that for the prediction. And so that's what we're using as a naive Bayes classifier versus many of the other classifiers that are out there. For this, we're going to use the social network ads. It's a little data set on here. And let me go ahead and just open that up, the file. Here we go. It has user ID, gender, age, estimated salary, purchased. And so we have, you can see the user ID, male, 19, estimated salary, 19,000, and purchased 0. So it's either going to make a purchase or not. So look at that last one, 0, 1. We should be thinking of binomials. We should be thinking of simple naive Bayes classifier kind of setup. So if we close this out, we're going to go ahead and import our NumPy as NP. We're going to have a good visual of our data, so we'll put in our matplot library. Here's our pandas, our data frame. And then we're going to go ahead and import the data set. And the data set's going to be, we're going to read it from the socialnetworkads.csv. Then we're going to print the head just so you can see it again, even though I showed you it in the file. And x equals the data set iLocation, 2, 3 values, and y is going to be the 4, column 4. Let me just run this so it's a little easier to go over that. You can see right here we're going to be looking at 0, 1, 2 is age and estimated salary, so 2, 3. And that's what iLocation just means, that we're looking at the number versus a regular location. Regular location, you'd actually say age and estimated salary. And then column 4 is, did they make a purchase? They purchased something. So those are the 3 columns we're going to be looking at when we do this. And we've gone ahead and imported these and imported the data. So now our data set is all set with this information in it. And we'll need to go ahead and split the data up. So we need from the sklearn model selection, we can import train test split. This does a nice job. We can set the random state so it randomly picks the data. And we're just going to take 25% of it's going to go into the test, our X test and our Y test, and the 75% will go to X train and Y train. That way, once we create our model, we can then have data to see just how accurate or how well it has performed with our prediction. The next step in pre-processing our data is to go ahead and do feature scaling. Now, a lot of this will start to look familiar. If you've done a number of the other modules and setup, you should start noticing that we bring in our data, we take a look at what we're working with, we go ahead and split it up into training and testing. In this case, we're going to go ahead and scale it. Scale it means we're putting it between a value of -1 and 1, or someplace in the middle ground there. This way, if you have any huge you don't have this huge setup. If we go back up to here where salary is 20,000 versus age 35. Well, there's a good chance with a lot of the back-end math that 20,000 will skew the results and the estimated salary will have a higher impact than the age, instead of balancing them out and letting the calculations weigh them properly. And finally, we get to actually create our naive Bayes model. And then we're going to go ahead and import the Gaussian naive Bayes. And the Gaussian is the most basic one. That's what we're looking at now. It turns out, though, if you go to the sklearn kit, they have a number of different ones you can pull in there. There's a Bernoulli, I've never used that one, categorical, complement, and here's our Gaussian. So there's a number of different options you can look at. Gaussian, when you come to the naive Bayes, is the most commonly used. So we're talking about the naive Bayes. That's usually what people are talking about when they're pulling this in. And one of the nice things about the Gaussian, if you go to their website, to sklearn, the naive Bayes Gaussian, there's a lot of cool features. One of them is you can do partial fit on here. That means if you have a huge amount of data, you don't have to process it all at once. You can batch it into the Gaussian NB model. And there's many other different things you can do with it as far as fitting the data and how you manipulate it. We're just doing the basics. So we're going to go ahead and create our classifier. We're going to equal the Gaussian NB. And then we're going to do a fit. We're going to fit our training data and our training solution. So X train, Y train. And we'll go ahead and run this. It's going to tell us that it ran the code right there. And now we have our trained classifier model. So the next step is we need to go ahead and run a prediction. We're going to do our Y predict equals the classifier.predict X test. So here we fit the data, and now we're going to go ahead and predict. And now we get to our confusion matrix. So from the sklearn metrics, you can import your confusion matrix. Just as saves you from doing all the simple math, it does it all for you. And then we'll go ahead and create our confusion metrics with the Y test and the Y predict. So we have our actual and we have our predicted value. And you can see from here, this is the chart we looked at. Here's predicted, so true positive, false negative, true negative. And if we go ahead and run this, there we have it, 65, 3, 7, 25. And in this particular prediction, we had 65 were predicted the truth as far as a purchase. They're going to make a purchase. And we guessed 3 wrong. And then we had 25 we predicted would not purchase, and 7 of them did. So there's our confusion matrix. At this point, if you were with your shareholders or a board meeting, you would start to hear some snoozing if they were looking at the numbers. And you say, hey, here's my confusion matrix. So let's go ahead and visualize the results. We're going to pull from the Matplot library colors, import listed color map. And this is actually, my machine's going to throw an error because this is being, because of the way the setup is. I have a newer version on here than when they put together the demo. And we need our X set and our Y set, which is our X train and Y train. And then we'll create our X1, X2, and we'll put that into a grid. And we set our X set minimum stop and our X set max stop. And if you come all the way over here, we're going to step 0.01. This is going to give us a nice line, is what that's doing. And then we're going to plot the contour, plot the X limit, plot the Y limit, and put the scatter plot in there. And let's go ahead and run this. To be honest, when I'm doing these graphs, there's so many different ways to do that. There's so many different ways to put this code together. To show you what we're doing, it's a lot easier to pull up the graph and then go back up and explain it. So the first thing we want to note here when we're looking at the data is this is the training set. And so we have those who didn't make a purchase. We've drawn a nice area for that. That's defined by the naive Bayes setup. And then we have those who did make a purchase, the green. And you can see that some of the green dots fall into the red area and some of the red dots fall into the green. So even our training set isn't going to be 100%. We couldn't do that. And so when we're looking at our different data coming down, we can kind of arrange our X1, X2 so we have a nice plot going on, and then we're going to create the contour. That's that nice line that's drawn down the middle on here with the red-green. That's what this is doing right here with the reshape. And notice that we had to do the dot T. If you remember from NumPy, if you did the NumPy module, you end up with pairs, X1, X2, X1, X2, next row, and so forth. You have to flip it so it's all one row. You have all your X1s and all your X2s. So this is what we're kind of looking for right here on this setup. And then the scatter plot is, of course, your scattered data across there. We're just going through all the points. That puts these nice little dots onto our setup on here. And we have our estimated salary and our age. And then, of course, the dots are, did they make a purchase or not? And just a quick note, this is kind of funny. You can see up here where it says X set, Y set equals X train, Y train, which seems kind of a little weird to do. This is because this is probably originally a definition. So it's its own module that could be called over and over again. And which is really a good way to do it, because the next thing we're going to want to do is do the exact same thing, where we're going to visualize the test set results. That way we can see what happened with our test group, our 25%. And you can see down here we have the test set, and if you look at the two graphs next to each other, this one obviously has 75% of the data, so it's going to show a lot more. This is only 25% of the data. You can see that there's a number that are kind of on the edge as to whether they could guess by age and income they're going to make a purchase or not. But that said, it still is pretty clear. It's pretty good as far as how much the estimate is and how good it does. Now, graphs are really effective for showing people what's going on, but you also need to have the numbers. And so we're going to do from sklearn, we're going to import metrics, and then we're going to print our metrics classification report from the y-test and the y-predict. And you can see here we have precision. Precision of zeros is 90. There's our recall, 0.96. We have an F1 score and a support. And we have our precision, the recall on getting it right. And then we can do our accuracy, the macro average, and the weighted average. So you can see that it pulls in pretty good as far as how accurate it is. You could say it's going to be about 90% is going to guess correctly that they're not going to purchase. And we had an 89% chance that they are going to purchase. And then the other numbers as you get down have a little bit different meaning, but it's pretty straightforward on here. Here's our accuracy, and here's our micro average and the weighted average and everything else you might need. And if you forgot the exact definition of accuracy, it is the true positive, true negative over all of the different setups. Precision is your true positive over all positives, true and false. And recall is a true positive over true positive plus false negative. And we can just real quick flip back there so you can see those numbers on here. Here's our precision, here's our recall, and here's our accuracy on this.
RNN tutorial. That's the Recurrent Neural Network. My name is Richard Kirschner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you? We will start with, of course, the fundamentals. What is a neural network and popular neural networks? It's important to know the framework we're in and what we're going to be looking at specifically. Then we'll touch on why a recurrent neural network, what is a recurrent neural network, and how does an RNN work. One of the big things about RNNs is what they call the vanishing and exploding gradient problem. So we'll look at that. And then we're going to be using a use case study. It's going to be in Keras on TensorFlow. Keras is a Python module for doing neural networks and deep learning. And in there, there's what they call long short-term memory, LSTM. And then we'll use the use case to implement our LSTM on the Keras. So when you see that LSTM, that is basically the RNN network. And we'll get into that. The use case is always my favorite part. Before we dive into any of this, we're going to take a look at what is an RNN, or an introduction to the RNN. Do you know how Google's autocomplete feature predicts the rest of the words a user is typing? I love that autocomplete feature. As I'm typing away, it saves me a lot of time. I can just kind of hit the enter key and it autofills everything and I don't have to type as much. Well, first there's a collection of large volumes of most frequently occurring consecutive words. This is fed into a recurrent neural network. Analyzes the data by finding the sequence of words occurring frequently and builds a model to predict the next word in the sentence. And then Google, what is the best food to eat in Las, I'm guessing you're going to say Las Mexico. No, it's going to be Las Vegas. So the Google search will take a look at that and say, hey, the most common autocomplete is going to be Vegas in there. And usually it gives you 3 or 4 different choices. So it's a very powerful tool. It saves us a lot of time, especially when we're doing a Google search, or even in Microsoft Words has some people get very mad at it because it autofills with the wrong stuff. But you're typing away and it helps you autofill. I have that in a lot of my different packages. It's just a standard feature that we're all used to now. So before we dive into the RNN and getting into the depths, let's go ahead and talk about what is a neural network. Neural networks used in deep learning consist of different layers connected to each other and work on the structure and functions of a human brain. You're going to see that thread, human and human brain and human thinking, throughout deep learning. The only way we can evaluate an artificial intelligence or anything like that is to compare it to human function. Very important note on there. And it learns from huge volumes of data, and it uses complex algorithms to train a neural net. So in here we have image pixels of 2 different breeds of dog. One looks like a nice floppy-eared lab, and one a German shepherd. Both wonderful breeds of animals. That image then goes into an input layer. That input layer might be formatted at some point because you have to let it know, different pictures are going to be different sizes and different color content. Then it'll feed into hidden layers. So each of those pixels or each point of data goes in and then splits into the hidden layer, which then goes into another hidden layer, which then goes to an output layer. RNN, there's some changes in there which we're going to get into. So it's not just a straightforward propagation of data like we've covered in many other tutorials. And finally you have an output layer, and the output layer has 2 outputs. It has one that lights up if it's a German Shepherd and another that lights up if it's a Labrador. So it identifies the dog's breed. Such networks do not require memorizing the past output. So our forward propagation is just that. It goes forward and doesn't have to rememorize stuff. And you can see there, that's not actually me in the picture. Dressed up in my suit. I haven't worn a suit in years. So as we're looking at this, we're going to change it up a little bit. Before we cover that, let's talk about popular neural networks. First, there's the feed-forward neural network, used in general regression and classification problems. And we have the convolutional neural network, used for image recognition. Deep neural network, used for acoustic modeling. Deep belief network, used for cancer detection. And recurrent neural network, used for speech recognition. Now, taken a lot of these and mixed them around a little bit, so just because it's used for one thing doesn't mean it can't be used for other modeling. But generally this is where the field is, and this is how those models are generally being used right now. So when we talk about a feed-forward neural network, in a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers. So each one of those connects and then connects to the next hidden layer, connects to the output layer. And of course we have a nice simplified version where it has a predicted output, and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers only the current input. So if you have a series of things, and because 3 points back affects what's happening now, and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed-forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed-forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H, going to Y. That's your feed forward. But right in the middle it has a value C, so there's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the U.S. produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those 3 words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of, because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in and then the X goes in. So the X is going upward bound and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the Y and the H value are connected to each other. They're not necessarily the same value because H can be its own thing. And usually we draw this or we represent it as a function. H of T equals a function of C where H of T minus 1, that's the last H output, and X of T going in. So it's the last output of H combined with the new input of X, where HT is the new state, FC is a function with the parameters C, that's a common way of denoting it, HT minus 1 is the old state coming out, and then X of T is an input vector at time of step T. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is, like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one to many, so you have a single input and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank, a thief. The students who got into engineering with blank from Asia. And you can see in here we have our X value going in, we have the previous value going forward, and then you back propagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief. And the student who got into engineering with a blank were from Asia. Consider the following example, the person who took the bike. So we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to backpropagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution, the solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the backpropagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers, make those smaller. And finally is a gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the option problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the LSTMS. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. LSTMs help us solve this problem. So the LSTMs are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. LSTMS are a special kind of recurrent neural network, capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is as you look at these layers, not only does the propagate through the first layer, goes into the second layer, back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long short-term memory network, there's 3 steps of processing in the LSTMS that we look at. The first one is we want to forget irrelevant parts of the previous state. A lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h at t minus 1, and the current input, x at t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f, the h at t minus 1, and then x at t, plus, of course you have a bias in there with any of your neural networks, so we have a bias function. So f at t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an LSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x at t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are two parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the two formulas that come up. The I of t equals the sigmoid of the weight of I, h at t minus 1, x at t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h at t minus 1, x at t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint, as I step out of my suit again. Consider the current input at x of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First, we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There could be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John, awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match. So you look at this and you can start to train this neural network. So it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective. John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, the case study. Use case implementation of LSTM. Let's predict the prices of stocks using the LSTM network based on the stock price data between 2012 and 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of LSTM. Let's dive in. We're going to import our libraries. We're going to import the training set and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda navigator. When we go under environments, I've actually set up a Keras Python 3.6. I'm in Python 3.6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python in different environments. Anaconda now has a nice interface. And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. You can go in here and open a terminal window, and then in here, once you're in the terminal window, this is where you're going to start installing using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to application, and that's the environment I've loaded on here, and then we'll click on the Launch Jupyter Notebook. Now I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN stock. And let's just take a look at start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now the first half is kind of boring when we hit the run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas as PD. And when I hit run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if I was to divide this up, oops, I'm going to actually, let's overlap these, here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with, the evaluate is the next biggest piece. So the actual code here, Keras is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas.readCSV, and it's a Google stock price train.csv. And so under this we have training set equals dataset train.ilocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad and text editor just so we can take a look at it. Certainly you can open up an Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, or the most basic set of information you can look at in stock. It's all free to download. In this case we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a dataset train equals PD_CSV. And if you noticed on the original frame, let me just go back there, they had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code, and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. We want to do what they call feature scaling. And in here we're going to pull it up from the sklearn or the skKit pre-processing import min-max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100 and another stock has a value of 5. you start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1, or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we've telling it's going to be from 0 to 1. We want to take our training set and we're going to create a training set scaled. And we're going to use our scalar, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object. We'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise, you'll get a pointer error. And then we're going to take our xtrain and we're going to append training set scaled. This is a scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go. We go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally, we have ytrain.append training set I to 0. And if you remember correctly, I to, or I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the ytrain. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60 since that's the value over here, and it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded two arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199, and we're making sure that that is shaped correctly. So the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers. And so the end layer needs to be one value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our LSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the LSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and that'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting-edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Pi is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Pi now if you wanted to. Not a big deal, we're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in. And you'll see that we have the LSTM and then the dropout. LSTM, then dropout. LSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model, and we'll run that and load that up. And then we're going to start adding our LSTM layer and some dropout regularization. And right there should be the cue, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here, let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them, so let me go ahead and put all 3 of them in, and then we can go back over them. There's the second one, and let's put 1 more in. Let's put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in. And then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first LSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout, and that's what's coming into this one, and so on and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer, the dense layer. And if you remember up here, we had the 3 layers. We had LSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our X train and our Y train. We have our source of data and the answers we know so far that we're going to put in there. We've reshaped that. We've come in and built our Keras. We've imported our different layers. And we have in here, if you look, we have 5 total layers. Now, Keras is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Keras is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Keras. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fit, fitting the RNN to the training set. We have the regressor.fit, X-train, Y-train, epochs, and batch size. So we know where this is. This is our data coming in. For the X-train, our Y-train is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of X-train. So this is each of those rows, which includes a time sequence of 60. And batch size, another one of those things where Keras really shines, is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because there's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. And give it a second to kick in there. There we go. All right, so we have epoch. So this is going to tell me it's running the first run through all the data. And as it's going through, it's batching them in 32 pieces. So 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by 1. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through, and you can see we've run it through 100 steps, or 100 epochs. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. it kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epoch pretty close since our losses remain the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. You see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, data set, test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. You see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test and we're going to load that in, and then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat, and we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2, but we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our concatenated our two data sets together. We have our inputs equals data set total length minus length of data set minus test minus 60 values. So we're going to run this over all of them. And you'll see why this works. Because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshape, so reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1. And finally, we want to go ahead and take our x test, and we're going to create that x test, and for I in range 60 to 80. So here's our x test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our x test, we convert it to a numpy array. We do the same reshape we did before, and then we get down to the final two lines, and here we have something new. right here on these last two lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts x test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplot library.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red. So it's going to be in bright red, and we're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph, I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. And like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's whether how many volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there, there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bend here does not quite match up with that bend there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data. Not so good for doing a quick tutorial like this. So we covered a lot of really cool things in this tutorial today. Hopefully you'll be able to get rich predicting stock, or maybe get a job if you are familiar with the stock domain and business domain. But you can see how this can be applied to all kinds of different tools and trades across different domains. So the biggest takeaways are we had an introduction to the RNN and its setup on there. We went over the popular neural networks that are out there. We discussed what is a recurrent neural network. We went into one of the big problems with the RNN, and that's the exploding gradient problem. We also discussed the long short-term memory networks, which is part of what we're working on. That's the LST, which is part of the RNN setup. And finally, we went through and we predicted the Google stock to see how it did. Convolution Neural Network tutorial. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get it certified, get ahead. Today we're going to be covering the Convolutional Neural Network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in. So it takes that graphic and puts it into the input layer. You have all your hidden layers. And then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulation. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist. So we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer. ReLU is how that is pronounced. And that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN. What is convolution neural network? How CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for. And you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto It's pixel values represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by doing multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first three elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match three different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now obviously when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works, is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges, it might be looking for different parts. We'll cover that in a little bit more detail in a minute. Right now we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, it's going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we say linearity, we're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or that backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here is turn it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have a rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel, and we just do every other one. And this reduces our rectified feature map, which, as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value, a little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value, and then we're pooling those features together. So instead of thinking of this as image of the map, think of this as how valuable is a feature in that area. How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image, and then it skips over and says, I see a 3 in this image, and it says, oh, this one is rated as a 4. We don't want to sum it together, because then you might have like 5 1s, and it'll say, 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say, probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolutional neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data. And so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image. And if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there just looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening is a process of converting all of the resultant 2-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7, and we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value, which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there because it's all building multiple layers off the different filters. Then goes through the ReLU as this activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it, and then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So a great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see in our data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the image using Matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but Matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember Matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what was going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape, we're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You could look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let's just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. You'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what X0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images. It's very easy to look at them, and they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out, and we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a numpy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. Let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self all train batches. So we're going to make an array of all those different images. And then of course we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up the self-training images at this point, and that's going to go to a NumPy array VStack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a NumPy array. And then it's always nice to get the training length, and that's just a total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course we want to go ahead and they run this where we say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once. So we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self I equal to 0. So what we're looking at here is we're going to create X. We're going to get the next batch from the very initialized. We've already initialized it for 0. So we're going to look at X from 0 to batch size, which we've set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self I plus batch size because the self I is going to keep changing. And then finally, we increment the self I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in, and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the cfar helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into 2 parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, since we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float64 to float type, or is treated as an NP float64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals tf placeholder tf float32. We just talked about the float64 versus the NumPy float. We're actually just going to keep this at float32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches. That's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder tf float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this. We don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes is looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this. So it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically. But we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. We're going to go ahead and work on our convolutional 2D, our max pool. So we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions. And let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. We just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. Usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the Conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias, shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it, and of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes, and then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2 or whatever it is, that's what goes into the pooling, or what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here we're going to create our normal full layer. So at some point we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out, create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2 by 2, and we put in the convolutional one that we just created, the convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so notice to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4 by 4 going in, let's do 8 by 8 by 64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling, and then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat, and then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, d-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the y-predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer. And then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there. They change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. An exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy, or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights and your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here. And we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there, which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and graph as just general graphing. But they talk about a graph session. So we're going to go ahead and run the model. And let's go ahead and walk through this, what's going on here. And let's paste this data in here. And here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run. So we're going to do with TF session as session right here. We've created our variable session. And then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. In the first process is we're going to do a session run. We're going to take our train. We created our train variable or optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created. And we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf.equal tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run accuracy feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this. Oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0, it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we would be looking the other way. But 0.05, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. You can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we seed the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We've trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is. And now that we have a solid running model and accuracy, let's go ahead and take a look at what we covered today. We did cover a lot because this is a very complicated subject, and it's not so much complicated in any individual step. It just has a lot of steps involved. So today we covered what is a convolutional neural network. And you can see we have the pictures coming in to the input layer, to the hidden layers, to the output layer, and then orchid or rows. We talked about the very basics at the beginning. And we discussed how a CNN recognizes images. And the very basics is we converted the image into a pixel map of zeros and ones. Then we dived into layers in a convolutional neural network. And we had our convolutional layer, our fully convected layer, our ReLU layer, and our pooling layer. And we looked at pooling layer. It reduces the data down to a smaller amount by finding the, first it finds the matches and then it finds the maximum value in that match. And we discussed all the different layers in there. We went into the fully connected layer, which is the neural networks you're probably used to dealing with, where we're just building a forward propagation neural network. And we connected them all together. And you can see here, we took the bird, we did our feature extraction in multiple hidden layers, where we had our convolution, which then generated those little individual filters, and we had our ReLU, and then we took the ReLU, we max pooled those, and then we took all of those pooled values at the end, so they've been reduced to smaller mappings. We've reduced that, and then we fed that into the fully connected layer. And then finally, we went into the use case implementation using CNN, and we walked through a full demo on the coding on there.
Today we are exploring Hugging Face, an amazing tool that makes working with language and AI super easy. If you are curious about using advanced technology to understand or create text, this video is perfect for you. Hugging Face is a company that helps people use AI models for language tasks like translation, text analysis, or even generating new text. They have created a library called Transformer which comes with pre-trained models, so you don't have to build everything from scratch. It's simple, powerful, and perfect for developers, researchers, or even beginners. So in this video, I will show you 3 cool things you can do with Hugging Face. Speech to text, turn spoken words into written text easily, great for captions or voice apps. Second one is sentiment analysis. Find out if a text is positive, negative, or neutral. Helpful for understanding reviews or comments. The third one is text generation. Create human-like text that sounds natural. Perfect for chatbots or creative writing. I will also explain some important basics like how pipelines make using Hugging Face models super easy and how tokenization helps AI understand text. By end of this video, you will know how to use Hugging Face to start building your own projects. It's simple, fun, and really powerful. So welcome to this demo part of this video. So here, as you know, we will be doing 3 things. First thing, speech to text recognition. The second thing, text generation from a particular sentence or a word. And the third thing, we will do sentiment analysis. Okay, so we will perform this one by one. So let's start with something called speech to text recognition. Okay, using Hugging Face. So first I will rename this. I'll write here Hugging Face speech to text. Okay, yeah. So first I will install Transformers library. It is already installed on my system, but again, just for you guys, I'm doing this. Okay, pip install Transformer. So now let's see what is Transformers. So Transformers is a powerful Python library created by Hugging Face. So that allows you to download, manipulate, and run thousands of pre-trained open source AI model. Fine. So as you can see, requirement already satisfied. It means like already installed. So these transformer models cover multiple tasks across modalities like NLP, natural language processing, computer vision, audio, and multimodal learning, like many things. Fine. So now I will do from transformers import pipeline. Okay, so now let's run it. So now what is pipeline? Okay, so a transformer pipeline describes the flow of data from origin system to destination system. Fine, because you already know transformer means you can run or manipulate thousands of pre-trained open source AI model. So pipeline describes the flow of data from origin system to destination system and defines how to transform the data along the way. Okay, so let's check the versions. Transformers version. Okay, that long tab. Okay, why it is coming? Import transformers. Yeah, so we have currently 4.42.4 version of the transformer. Okay, so I'm using Google Colab. Okay, so you can use either Jupyter Notebook, Visual Code Studio, or Colab. Okay, so now let's import libraries. Import Librosa. Okay, so what is Librosa? So Librosa is a Python package for audio and music analysis, right? Because we are doing speech to text, so we need this. So it provides various functions to quickly extract key audio features and matrices from the audio files. Okay, and this Librosa can also be used to analyze and manipulate audio files in a variety of formats such as WAV, MP3, M4A, and like that. Okay, so next we will import torch. I hope everyone know torch. So torch is nothing PyTorch. It is a machine learning library based on the torch library used for applications such as computer vision and NLP. And originally it was developed by the Meta AI and now the part of Linux Foundation, umbrella. Let's import one more thing. Import. So now let's import IPython. Okay, capital IPython dot display as display. So now you will be wondering what is this IPython display. Okay, so it is an interactive command line for the terminal for Python, and it can provide a IPython terminal and the web-based notebook platform for Python computing. And this IPython have more advanced features than the Python standard interpreter, and we quickly execute a single line of Python code. Nothing. Okay, for that I'm using this. And the next is from transformers import WAV to vectorizer for CTC and WAV to vectorizer to tokenizer. Okay, so now what is this? So WAV2 vectorizer for CTC is supported by the notebook on how to fine-tune a speech recognition model. Okay, and this tokenizer. So tokenizer is nothing. Tokenization is a conversion of a text into meaningful lexical tokens belonging to categories defined Lexa program. In case of NLP, so those categories include nouns, verbs, adjective, punctuation, etc. Okay, now, and the last library, let's import NumPy as NP. I hope everyone know NumPy. What is NumPy? Again, NumPy is a Python library used for working with arrays. It also has a function, for working in domain like linear algebra, Fourier transform, and matrices, and many others. Fine. I hope everyone know about these library which we have imported. Okay, so let's move forward by tokenizer equals to 2 to tokenizer dot from pre-trained. This is why I love this Google Colab. You will decide just some words and it will show the suggestions. Facebook. So this is again one pre-trained model. Okay, so we are just importing it. Base 968. This is nothing, the name. Okay, then model equals to WAV2 for CTC dot from pre-trained, then Facebook WAV2 vectorizer 2, then base 960. Fine. Now let's run it. So now you can see. So we are loading this. Okay, they are downloading. Okay, so you can ignore these warning. So now let's load the audio file. So here I will write audio sampling rate equals to librosa dot load. Okay, so you know about librosa, right? Then I have v dot m4a. So I have already one speech or one audio, you can say. So I will play it, don't worry. Before the final output, I will show you 16,000. Okay, so now I will write. Okay, I've already loaded, I guess. Okay, no issues. I will load again. Okay, the file is loaded. I will rename it to V. Yeah, fine. So now the error won't come again. We have v.mp4a. Okay, so now we have to do. Okay, let me try it. We have v.mp4a, but I don't know why it is not coming. Okay, let me copy the path. Now it will run, I guess. It's running. Yeah. So now I will write here audio, comma, sampling rate. Okay, now listen carefully. Then I will write display dot audio, then path, comma, autoplay equals to true. Okay.
Hello and welcome. This is an AI voice message.
I guess you heard, but again, let me play it again.
Hello and welcome. This is an AI voice message.
Okay, so it is saying ki, hello and welcome. This is an AI voice message. Fine. So now what I will do, I will input some values. Input values equals to tokenizer, then audio, comma, return tensors equals to pt. Fine. Dot input values. Okay, then here input values. Okay, input values. Okay, yeah. So now logits will come here. So we have to now store the logits, which means non-normalized predictions. Okay, so logits equals to model input values dot logits. Okay, then here I will write logits. Okay, it's running. Done. So now what we will do, we will store predicted IDs, then we will pass the logits to values to softmax to get the predictive value. Okay, so here I will write predicted IDs equals to torch dot argmax. Okay, then logits, comma, dimension equals to -1. Okay, then I will pass the prediction to the tokenizer decode to the transcription. Okay, so here I will write transcriptions equals to tokenizer dot decode predicted IDs to 0. Running fine. So now let's see our output transcriptions. So now you can see hello and welcome. This is an AI voice message. So now let's play it again.
Hello and welcome. This is an AI voice message.
Amazing, right? So this is how you can use Hugging Face for the speech to text recognition. It's a very small code, line of code, as you can see. Okay, so now let's move forward and do the sentiment analysis, okay, or text generation. So let me open new drive. So yeah, so now I will write here, I will write sentiment slash text generation Hugging Face. Okay, so first of all, let's import the files. So first I will write import warnings, then warnings dot filter warnings. Okay, I will write here ignore, then we'll import numpy. You already know what is numpy, and import panda. So these are some basic Python library, and I hope everyone knows. And import matplotlib for the plots, matplotlib dot pyplot as plt. Then I will import seaborn for the graphs, the statistics graph. Okay, SNS, then SNS dot set. So now we'll import sklearn model train trace split. So sklearn is nothing, scikit-learn is probably the most useful library for machine learning Python. So this library contains a lot of efficient tools for machine learning and statistical modeling, including classification you can do, regression you can do, clustering you can do from this sklearn. Okay, from sklearn dot model selection import train trace split from sklearn dot matrix import f1 score comma confusion matrix comma ROC AUC curve or score. So again we'll import teams from transformers, import pipeline, everyone know what is this, then import torch. Okay, now let's run it. You have too many active session, terminate existing to continue if you are interested in using one more session. Okay, wait. Yeah, fine. Now which one is open, bro? Terminate this, terminate this, terminate this. No. Okay, fine. So now let's do sentiment analysis. So we will explore sentiment analysis using a pre-trained transform model. Okay, The Hugging Face library provides, convenient pipeline, as you already know, function that allows us to easily perform sentiment on the text. So now let's first import the necessary dependencies and create a sentiments pipeline using this line. So I will write here classifier equals to pipeline sentiment analysis, then type classifier. Okay, so it will download the pre-trained sentiment analysis pipeline. Pipeline is not defined. How? Okay, error is there. I hope it will run now. Yeah. So now we can pass a single sentence or a list of sentence to the classifier and get the predictive sentiment labels and associate confidence score. Fine. So now just for the testing classifier, so let's write this is a great movie. Okay, now let me run it. So now you can see here label positive. So label positive typically refers to the outcome or a class of interest that the model is designed to predict. So here we are just checking the sentiment analysis model. Okay, so this is why I wrote this. Okay, so let's check one more. This was a great course. Then I did not understood any of it. Now let's check this. Yeah, perfect. And the score, you can see the accuracy score 99%, which is almost close to 100%, and which is amazing. So now you have access to a GPU, so you can also utilize it for the faster processing by specifying the device using the parameter. Okay, so now what I will do, first I will, okay, wait, yeah, fine. So now I will import dataset airline tweets equals to pd dot read. PD means pandas library here we are using. Okay, now first import, I will import here itself. So I have tweets.csv. Okay, tweets.csv. Let it upload. Yeah, done. So now let me airline tweets dot head. Why dot head? Means it will show me the top 5 rows. Okay, 0 1 2 3 4 5. Okay, you can see tweet ID, airline sentiment, neutral, positive, neutral, negative, then this is this. Okay, so now let's do something. Okay, so what I will do, df means data frame airline tweets, then I will write airline sentiment. We have airline sentiment, this column. Okay, comma text. I need these 2 columns. Okay, df dot head 5. So yeah, so airline sentiment is neutral, and this is what this text is. all about. Okay, because these two are the main things, text and the sentiment. So now let's make plot, count plot. Then I will write df comma x equals to airline sentiment. Then palette equals to with its. Then here I will write plt dot x label airline sentiment. Okay, then plt dot y label count plt dot show. So it will draw one graph. Okay, spelling is wrong. Yeah, so it will show neutral, positive sentiment and the negative. So as you can see, the negative sentences or the sentiments are the more. Okay, so we have now three classes which do not match the two class available in the Hugging Face pipeline. So therefore we will filter out all the rows which have been labeled as neutral. Okay, so df equals to df and again df airline sentiment, fine, was not equals to neutral. Okay, then df target equals to df airline sentiment dot map. Then I will write here positive 1 and the negative 0. Fine, negative will be 0. Okay, then print number of rows comma df dot shape. Okay, so now you can see number of rows are 11,541. Okay, so now I will write predictions 5. It will, okay, predictions is not defined. Okay, so now what I will do, so here I will write text equals to df text and to list dot to list. Then here I will write predictions equals to classifier text. Okay, so here write probabilities equals to predictions, then score if predictions label dot starts with P means positive. Okay, else 1 minus prediction score. Okay, then I will write for prediction and prediction. Why it is not running? This is taking time, too much time. I don't know why. So as you can see, finally we have the output of predictions values. So this depends on system to system. My system took almost 17 minutes 47 seconds to complete. Okay, so now let's run it. Okay, predictions is not defined. Pro now predictions. Yeah, so now I will write here predictions equals to np dot array. Np means numpy dot array. Then I will write one if prediction label is positive dot starts with p, okay, else 0 for prediction and prediction values. Yep. Okay, fine. So now let's check the accuracy of our model. Print accuracy. Okay, then I will do round up the values. So here I will write np dot mean, then df, then the target, right? Yeah, then I will write equals to predictions, then I will write into 100 comma 2, then I will write percentage. Okay, fine, looks good. Yes, so as you can see, our accuracy is 88.99%, which is very good again. So now let's do some confusion matrix. Confusion matrix, then df target comma predictions comma normalize equals to true. Okay, then I will plot confusion matrix. Okay, df then target comma predictions comma normalize equals to true. Okay, my bad. Right here, confusion matrix comma labels. Okay, so here I will plot a confusion matrix using Seaborn. Okay, so here I will use ARGS, which is confusion matrix np.array, so which is labels list. So I will write plt dot figure, then figure size equals to 8,6. That's SNS dot set font scale equals to 1.4. Okay, then let's create the heat map. Confusion matrix comma and not will be true. Okay, then I will write fmt equals to g, then confusion map equals to blues, then x labels equals to labels, then y labels equals to labels. Okay, yes. So now I will write plt dot title will be confusion matrix, then plt dot x label will be predicted values, then plt dot y label will be actual values, then plt dot show. Okay, why the chart is not coming? Okay, so I have to write plot confusion matrix, then I write cm, then negative, comma, positive. Okay, now the chart will come. Okay, yeah. So now you can see here, this is actual, and this is a confusion matrix, and the negative and the positive ratio is there. Okay, so now let's print the now let's check the ROC AUC score. So I will write here print ROC AUC score, then here I will write ROC AUC score, then TF target, comma, props. Okay, so 94. Okay, so first let me tell you what is this ROC AUC score. So this is the area under the ROC curve. So what it does, it sum up how well a model can produce relative scores to discriminate between positive and the negative instance across all the classification thresholds. So with this ROC score of 94, 0.94, which is 94%, we can conclude that a pre-trained sentiment analysis model has achieved a high level of accuracy and effectiveness. So in predicting the sentiment labels. So this indicates that the model is capable of accuracy classifying text into positive or the negative sentiment categories. Okay, so now we'll do text generation. Okay, so text generation involves generating creative and coherent text-based thing. So I will write here text. Okay, so text generation involves generating creative and coherent text based on a given prompt or starting point. So what we will do first, we will import the necessary dependencies and load the data set of the poem. Okay, so here I am write poems. Let me write poems equals to pd.read.csv. Don't worry, I will give you these files. Okay, description box below I will add. So here I will write robot frost, okay, .csv. Fine, and then I will write poems dot head 5, or head, just have to write head. Module pandas has, okay, not dot underscore csv. Yeah, okay, it will show the top 5. Stopping by woods on a snowy evening, fire and ice. The aim was song, collection, content, year of publication. Okay, so now what we will do, we will write content equals to poems content dot drop NA to list. Okay, so to generate text, we extract individual lines from the poems and use the pipeline text generation function to create a text generation pipeline. Fine. So here I will write lines equals to, then I will write for poem and content. Okay, for line and poem dot split into next line. Okay, then lines dot append, then I will add line dot right strip. To the right it will add. Okay, fine. So now lines equals to line for line and lines if length of line 0, then show me the lines 5. Okay, so now you have seen here whose woods these are, I think I know. Then the next line, his house is in the village though. That's the next line, he will not sing. Okay, like this. So now let's import that pipeline text generation module. Okay, gen equals to pipeline. So these are the some pre-trained model. You already know generation. Okay, so now I will write here lines. Let's run it. Yeah, done. So in line 0 we have whose votes these are, I think I know. Okay, so now we can now generate text by providing a prompt and specifying the parameters such as max length and num return sequence. Okay, why? Because we have imported this text generation module. Okay, for example, see lines 0 dot max length equals to 20. So now it will generate this to the maximum 20. Okay, till 20 word maximum length. Okay, check. Okay, okay, expression cannot contain perhaps double equals to where? Okay, wait, now it will run. So see, the line was this much only. Whose words these are, I think I know. Whose words these are, think I know. But here, the generated text, I wish to go to church because I feel like. Okay, this is how you can do, text generation. Now let's check for the more. Gen lines 1. Okay, then max length equals to 30, comma, num return sequences equals to 2. Okay, so our first line was this: his house is in the village though. Okay, 0 1 2 3 4 5. Okay, so here you can see his house in the village though. However, you might say that the place was the same with the place this. So these are the generated text. Okay, and this is another return sequence second. So there are two, one and the second. Okay, so now let me import text tab. Okay, then creating function wrap x. I don't need this. Then return text wrap dot fill x comma replace white space equals to false, comma fix sentence endings equals to true. Okay, so now out equals to generated lines 0 to maximum length equals to 30, then print wrap out to 0, then generated text. Okay, so now we are setting the pad tokens to EOS tokens. Okay, so whose these are, I think I know, and this is the maximum 30 till 30. Okay, so now I will write here, okay, preview equals to, okay, so now what you can do, you can generate a prompt to generate text on a specific topic like this. Prompt equals to transformers have a wide variety of application in NLP. Okay, so this is my prompt. Okay, this I'm not importing from the data set. Okay, so I will write out equals to gen prompt comma max length equals to 100, print wrap out. Okay, here I will write, anyways, here I will write generated text prompt. Okay, so it is running. Let's wait. Yeah, so okay, some error is there. Okay, so here the issue is with 100 words. Will go till 50. Yeah, so let me do it again. 100. Yeah, so now you can see we can generate text by giving a prompt. So we have covered 3 topics in this. First thing is speech to text using Hugging Face. Second thing is sentiment analysis using Hugging Face, and the third is text generation using Hugging Face. Okay, and in this text generation we did with 2 methods, one with the data set and second thing with the by giving prompt, like in ChatGPT you can say.
Do you know, friends, that according to the lending statistics, the demand for AI and ML specialists is projected to surge by 40% between 2023 to 2027. And on an average, an ML engineer is expected to earn around $133 and $336 per year. So if you are an aspiring ML engineer and thinking about what innovative projects you can show in your portfolio, then your wait is over. Because in this video, I'll be covering 8 amazing ML projects that you can showcase in your resume. So guys, let's start first with a beginner level project. And the first project that we are going to encounter, that is home value prediction. So guys, this project aims to develop a predictive model to estimate the value of residential properties. The model will analyze various features such as location, square, footage, number of bedrooms and bathrooms, age of the property, and other relevant factors. By leveraging historical property data, the model will be able to provide accurate home value predictions, which can be useful for real estate agents, buyers, and sellers. So guys, the programming language that we are going to use all over here will be Python, and machine learning libraries that we will be using will be Scikit-learn, TensorFlow, Keras, and for data handling libraries we have Pandas, NumPy, and for visualization we have to use Matplotlib and Seaborn. Now what will be the approach for this one, guys? So guys, the first one that we have a data collection. So here what is going to happen, guys? So first you have to collect the historical property data from the sources like Zillow, retailer.com. You can also get database from the public real estate databases like Kaggle datasets where you have Zillow home value prediction. Ensure that the dataset include features like location where you have latitude, longitude, square footage, number of rooms, year built, property type, and previous sales. The next step that comes is data cleaning. You have to handle the missing values by using imputation techniques or removing incomplete records, removing outliers that may skew the model's prediction, normalize or standardize the data to ensure consistency. The third one that we have is feature engineering. You have to create new features such as proximity to schools, crime rates, and access to the public transportation. Encode categorical variables, example property type, location, using techniques like one-hot encoding. Generate interaction features that capture relationship between existing features. The fourth one that we have is model selection. Use regression models like linear regression, random forest, gradient boosting, neural networks. Experiment with different models to identify the best performing one. Now, in the next phase, all you have to do, guys, is model training and evaluation. Split the data set into training and test sets. Train the model on the training set and evaluate their performance on the testing set using metrics like RSME, which means root mean squared error. You can use cross-validation to ensure the model's robustness and avoid overfitting. The sixth one that we have all over here is hyperparameter tuning. You can optimize the model's hyperparameter using techniques such as grid search or random search to improve accuracy. And if you're looking forward to deploy your model, then you can develop a web interface using Flask or Django to allow users to input property features and get predictions. You can deploy the model on the cloud platform like AWS for scalability. Now, if we talk about the complexity level of this, we all know that it is a beginner level project. Now let us move on to the one more set, that is music genre classification and generation. So guys, this is also one of the most beginner level project. This project aims to develop a system that can classify music tracks into different genres and generate new music composition within specified genre. The goal is to build a model that analyzes audio features to categorize music and uses deep learning techniques to create new music. This project introduces advanced concept of audio processing, deep learning, and generative models. So guys, what will be used in this? So we'll have programming language that will be Python. For audio processing, we'll be using Librosa. For machine learning libraries, we'll be using TensorFlow, Keras, PyTorch. For data handling libraries, we'll be using Pandas, NumPy. For visualization, we'll be using Matplotlib, Seaborn. For the dataset, guys, you can use GTZan music genre dataset, or you can get it from Free Music Archive. So guys, in the first phase, we are going to have data collection. You can obtain datasets containing music tracks and their corresponding genre from the sources, from GTZan music genre dataset and the Free Music Archive. Ensure that a dataset includes diverse genre and substantial number of tracks per genre. Next, we'll go for data preprocessing. Use library Librosa to load and pre-process audio files, including feature extraction such as mil frequency, cepstral coefficients, chroma features, and spectral contrast. You can normalize the extracted features to ensure consistent input for the given models. Now, if we talk about feature engineering, guys, you can extract additional features from the audio files such as tempo, beat, zero crossing rate, etc. Create a feature matrix that represents the extracted audio features. Then go for the model selection. Use convolutional neural network or recurrent neural networks for the music genre classification. Split the dataset into training and testing dataset. Now, if we talk about model training and evaluation, guys, then you can train the selected classification model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and F1 score. Use confusion matrices to understand the classification performance across different genres. Now, if we talk about model selection and training for the music generation, what you will do, guys, you can use the generative adversarial networks or recurrent neural networks such as LSTM, long short-term memory for music generation. Train the generative model on the dataset to create new music sequences. Next, we have model training and evaluation. You can train the generative model on sequences of audio features. You can evaluate the generated music by listening tests and by objective metrics like inception score or Friche audio distance. If I talk about hyperparameter tuning, guys, you can optimize the model. You can use the hyperparameters using techniques like grid search or random search to improve performance. If I talk about deployment, guys, you can deploy these models on cloud platforms like AWS. Now, let us move on to our next project. So, guys, the complexity of this project is at the beginner level. Now, let us move to the intermediate level projects. Next project that we have all over here is sentiment analysis of Twitter data. This project aims to develop a sentiment analysis model that can classify tweets as positive, negative, or neutral. The goal is to analyze public sentiment on various topics or events using natural language techniques. So guys, what will be used all over here? So in this, we will have programming language like Python, okay, NLP libraries, NLTK Spacey. For machine learning libraries, you can use Scikit-learn, TensorFlow, Keras. For data handling libraries, we have Pandas, NumPy. For visualization, we have Matplotlib, Seaborn, and we can use the API Twitter for data collection. Now, how you're going to work on it, guys? So guys, if I talk about the data collection, use a Twitter API to collect tweets based on specific hashtags like keywords or topics. Extract relevant fields like tweet text, user information, timestamp, etc. Then if I talk about data preprocessing, guys, clean the tweet text by removing special characters, links, mentions, hashtags, and stop words. Tokenize the text and perform lemmaization or stemming to reduce the words to their base form. Next, if we talk about feature engineering, guys, you convert the clean text data into numerical representation using TF-IDF, bag of words, or word embedding. Now, if I talk about model selection, guys, you can choose the classification algorithms such as logistic regression, Naive Bayes, or LSTM. Split the data set into training and testing data set. Now, if I talk about model training and evaluation, then you can train the selected model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and F1 score. Use cross-validation to ensure the model's robustness. If I talk about hyperparameter tuning, guys, you can optimize the model's hyperparameters using grid search or random search to improve the performance. For deployment, which can be optional, you can deploy your model on AWS for real-time sentiment analysis. So if I talk about the complexity level, guys, its complexity is intermediate. So guys, our next project is customer segmentation using k-means clustering. This project aims to segment customers into distinct groups based on their purchasing behavior and demographic information. The objective is to understand customer segments and tailor marketing strategies accordingly. So guys, what programming languages we'll be using? So basically, we'll be using Python. For machine learning libraries, we'll have Scikit-learn. For data handling libraries, we'll have Pandas, NumPy. For visualization libraries, we'll have Matplotlib, Seaborn. And the dataset source will be e-commerce transaction data. How we are going to work on this one? For data collection, we can obtain a dataset of e-commerce transactions that include customer demographics, purchase history, and product information. Next, we'll have data preprocessing. For data preprocessing, we are going to do the cleaning of the data by handling the missing values and outliers. Then for feature engineering, we are going to create features like total purchase amount, purchase frequency, and recency of the purchases. Then we are going to proceed for the model selection. You can use k-means clustering to segment the customers into distinct groups. You can determine the optimal number of clusters using methods like elbow methods or Silhouette score. Now, if I talk about model training and evaluation, you can train the k-means model on the processed dataset. You can evaluate the quality of clusters by analyzing intra-cluster and inter-cluster distances. Next, we have the evaluation. You can visualize the clusters using techniques like PCA, Principal Component Analysis, TSNE, etc. Next, we have the hyperparameter tuning. Now you can tune this model and interpret the characteristic of each segment. You can develop a target marketing strategies for each segment based on unique behavior and preferences. Now, deployment is optional. You can develop a dashboard using Flask or Django to visualize customer segments and track marketing campaigns. So guys, if I talk about the complexity of this project, so this is an intermediate level project. So guys, for dataset, you can use the Kaggle's customer segmentation dataset, which is available at the Kaggle's platform. Now, the third intermediate level project that we have all over here is building a chatbot with RASA. This project aims to build an intelligent chatbot using RASA framework. The chatbot will be capable of understanding user queries and providing appropriate responses, making it useful for customer support, personal assistance, or information retrieval. What languages we are going to use? So it will be Python based. We'll have the NLP libraries like RASA, NLTK, Spacy. For machine learning libraries, we are going to have Scikit-learn, TensorFlow, Keras, etc. For data handling libraries, we are going to use Pandas, NumPy. So guys, this was what we are going to do it. And how you can work on this one? By collecting the data, collect the conversation data and FAQs from the target domain. Annotate the data to create training examples for the chatbot. Next comes is data pre-processing. Clean the text data by removing special characters and normalizing the text. You can tokenize and limitize the text to prepare for a training. The third one, we have the models training. You can use RASA's NLU's component to train a model for intent recognition and entity extraction. You can define the dialogue management policies to handle different conversation flows. Next guys, you can perform the feature engineering and integration. You can integrate the RASA's NLU and core components to build complete chatbot. You can connect the chatbot to messaging platform like Facebook, Messenger, etc. For model selection and testing, what you can do guys, you can test this chatbot with various inputs to ensure that it handles the scenarios appropriately. And you can also select the right model using this. Now, if I talk about model training guys, what do you have to do? You have to collect the user feedback and conversational logs to continuously work on training the model. Next, similarly, you have to retrain the model periodically with the new data to see how it is working. So that will be your evaluation. Now, for the hyperparameter tuning, what are you going to do guys? You have to check in those scenarios where it is able to tune up with those scenarios where it can handle the input appropriately. And next is deployment. So guys, for deploying it, you can use AWS. So guys, for a data set, you can use RASA's open source. So that's a very good data set for you to proceed. So guys, if you talk about difficulty of this project, this is an intermediate level project. Now let us move on to the advanced level projects. For advanced level projects, the first one that comes up to my mind is movie similarity from plot summaries. Now, this project aims to develop a system that can find out recommended movies similar to a given movie based on their plot summaries. By analyzing the textual content of the movie, plot summaries, the model will identify similarities and suggest movies with similar themes, storylines, or genres. This project introduces beginners to natural language processing, text similarly measures, and recommendation systems. What languages we are going to use guys? We'll be using Python, NLP libraries like NLTK, Spacy, machine learning libraries like Scikit-learn, data handling libraries like Pandas, NumPy, visualization we can use NumPy, and dataset source will be IMDb or Kaggle. So guys, this process is also involving the data collection, then you have to go for data cleaning, then feature engineering, next model selection. So similar process as I have discussed in other projects, so you have to also go through the same one. Next, what do you have to do guys? Similarly, what do you have to do? You have to train the model, then evaluate the model, then hypertune it, and finally proceed for the deployment. So this is overall process of this project. Try to research on the website a lot, like how you can extract it. So guys, you can use Kaggle or Towards Data Science to research more about this project. Now guys, if I talk about the difficulty of this project, and this is an advanced level project. Now, let us move on to the next one that we have all over here. That is image segmentation project for brain tumor prognosis. This is a very amazing project and definitely you can put up on your portfolio. Basically guys, this project aims to develop an image segmentation model to identify and delineate brain tumors from MRI scans. The goal is to accurately segment the tumor regions which can aid in prognosis, treatment planning, surgical interventions. This project introduces intermediate level concepts of computer vision, deep learning, and medical image analysis. So guys, what we'll be using all over here? For programming languages, we can use Python. For deep learning libraries, we can use TensorFlow, Keras, PyTorch. For image processing libraries, we can use OpenCV, Scikit-Image. For data handling libraries, we can use Pandas, NumPy. For visualization, we can use Matplotlib, Seaborn. Now, if I talk about what is the process of developing this project, the first step will be the same, data collection. So next step, you have to go for data pre-processing. Third step, you have to do the model selection, where you can use CNN models for image segmentation task. Then you go for model selection. Moving ahead, you're going to have the model training and evaluation. You have to split the data set into training and validation and testing data sets. Next, proceed for the evaluation phase. Okay, evaluate the model with certain metrics. So here I can give you certain idea, like you can use dice coefficient, intersection over union, or accuracy. Then go for hyperparameter tuning, where you have to optimize the model's hyperparameters. You can use grid search or random search, as we have discussed. And finally, you can deploy this model on AWS. Now guys, we have come to the final project. This is also a very amazing project, guys. So guys, the complexity level of this project is advanced level. Now, let us move on to our final project, that is the impact of climate change on birds. This is a very amazing project, and definitely you can add it on your resume. This project aims to analyze the impact of climate change on the bird population and migration patterns. By examining various climatic factors and their correlation with bird species data, the project seeks to predict how climate change might affect bird behavior and distribution. This project will introduce you some advanced level concepts like time series analysis, environmental data modeling, etc. So guys, what programming languages we'll be using? For data analysis, you can see we'll have Pandas, NumPy. For machine learning libraries, we are going to have Scikit-Learn, TensorFlow. For visualization, we are going to have Matplotlib, Plotly. For geospatial, we are going to have GeoPandas, Folium. For data source, we're going to have public data sets on bird observation and climate data sources from eBird. Now, what will the process flow for this one, guys? First, you have to proceed for data collection. Gather bird observation from the data like eBird, which provides extensive record of bird sightings. Okay, and for climate data, you can collect it from NOAA, including temperature, precipitation, and other relevant climatic factors over the time. And similar next process will be the data pre-processing. Then you have to proceed for feature engineering. Then you have to go for model selection. Okay, moving ahead, you have to go for model training, then evaluation, then hyperparameter tuning, and finally, you have to deploy the model. So research about this project, see what models you are going to use. Suppose I can give you a hint about this. You can use time series analysis models like ARIMA, or ML models. You can also use random forest or gradient boosting for predicting impact on the bird population. So guys, use Google exhaustively to research about this project. This is also a very amazing project, and it's going to give you a lot of idea. Now, if I talk about the complexity level of this, it is an advanced level project.
Welcome to Deep Learning Interview Questions. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Today we're going to help you prepare for interview questions dealing with deep learning. And we're going to go from the very basics of neural networks and deep learning into some of the more commonly used models, so that you can have an understanding of what kind of questions are going to come up and what you need to know in interview questions. We'll start with a very general concept of what is deep learning. This is where we take large volumes of data, in this case on cats and dogs or whatever. A lot of times you use a training setup to train your model. Remember, it's kind of like a magic black box going on there. And then we use that to extract features or extract information, and in this case classify the image of a cat and a dog. So the primary takeaway when we're talking about deep learning is it learns from large volumes of structured and even unstructured data and uses complex algorithms to train neural network. It also performs complex operations to extract hidden patterns and features. And if we're going to discuss deep learning in this very simplified overview, then we also have to go over what is a neural network. This is a common image you'll see of a drawing of a forward propagation neural network. And it's a human brain inspired system which replicate the way humans learn. So this is inspired how our own neurons in our brain fire, but at a much simplified level. Obviously it's not ready to take over the human population and be our leader yet, not for many years. It's very much in its infant stage. But it's inspired by how our brains work. And they use a lot of other inspirations. You can study brains of moths and other animals that they've used to figure out how to improve these neural networks. The most common one consists of 3 layers of network, and this is generally how you view these networks, is you have an input, you have a hidden layer, and an output. And the neural network is broken up into many pieces, but when we focus just on the neural network, it's always on the hidden layers that we're making all the adjustments and figuring out how to best set up those hidden layers for their functions to both train faster and to function better. When we look at this, of course, we have our input, hidden, and output. Each layer contains neurons called as nodes that perform various operations. And you can see here we have the list of the nodes. We have both our input nodes and our output nodes, and then our hidden layer nodes. And it's used in deep learning algorithm like CNN, RNN, GAN, etc. We'll address some of these models a little closer, at least the most common models, as we go down the list and we study the deep learning and the neural network framework. Let's start with what is a multi-layer perceptron, or MLP, a lot of time is referred to. And you'll see these abbreviations. I'll be honest, I have to write them down on a piece of paper and go through them because I never remember what they all mean, even though I play with them all the time. What is a multi-layer perceptron? Well, if you look at the image on the right, it's very similar to what we just looked at. You have your input layer, your hidden layer, and your output layer. And that's exactly what this is. It has the same structure of a single layer perceptron with one or more hidden layers, except the input layer. Each node in the other layers uses a nonlinear activation function. What that means is your input layer is your data coming in, and then your activation function is based upon all those nodes and weights being added together, and then it has the output. MLP uses supervised learning method called backpropagation for training the model. Very key word there is backpropagation. Single layer perceptron can classify only linear separable classes with binary output, 0, 1, but the MLP can classify nonlinear classes. So let's break this down just a little bit. The multi-layer perceptron with an input layer and a hidden layer and an output layer. As you see that it comes in there, it adds up all the numbers and weights depending on how your setup is, that then goes to the next layer, that then goes to the next hidden layer if you have multiple hidden layers, and finally to the output layer. The backpropagation takes the error that it sees. So whatever the output is, it says, hey, this has an error to it, it's wrong. And then sends that error backwards from where it came from. And there's a lot of different functions used to train this based on that error and how that error goes backwards in the nodes. So forward is you get your answers, backward is for training. You see this every day. Even my Google Pixel phone has this. They train the neural network, which takes a lot more data to train than it does to use. And then they load up that neural network into, in this case I have a Pixel 2, which actually has a built-in neural network for processing pictures. And so it's just the forward propagation I use when it processes my photos. But when they were training it, it used the back propagation to train it with the errors they had. We'll be coming back to different models that are used. For right now, though, multi-layer perceptron, MLP. Put that down as your vocabulary word. And, of course, back propagation. What is data normalization and why do we need it? This is so important. We spend so much time in normalizing our data and getting our data clean and setting it up. So when we talk about data, there's a pre-processing step to standardize the data. So whatever we have coming in, we don't want it to be a 1 gigabyte file here, a 2 gigabyte picture here, and a 3 kilobyte text there. Even as a human, I can't process those all in the same group. I have to reformat them in some way that loops them together so that it's standardized format. We use this data normalization in pre-processing to reduce it and eliminate data redundancy. A lot of times the data comes in and you end up with 2 of the same images or the same information in different formats. Then we want to rescale values to fit into a particular range for achieving better convergence. What this means is with most neural networks, they form a bias. We've seen this recently in attacks on neural networks where they light up one pixel or one piece of the view and it skews the whole answer. So suddenly, because one pixel is really bright, it doesn't know what to do. Well, when we start rescaling it, we put all the values between, say, -1 and 1, and we change them and refit them to those values. It helps get rid of that bias, helps fix for some of those problems. And then finally, we restructure the data and improve the integrity. We want to make sure that we're not missing values or we don't have partial data coming in. One way to look at this is bad data in, bad data out. So you want clean data in and you want good answers coming out. One of the most basic models used is a Boltzmann machine. So let's address what is a Boltzmann machine. And if you know, we just did the MLP, multi-layer perceptron. So now we're going to come into almost a simplified version of that. And in this we have our visible input layer and we have our hidden layer. The Boltzmann machines are almost always shallow. They're usually just two-layer neural nets that make stochastic decisions whether a neuron should be on or off, true, false, yes, no. First layer is the visible layer, and second layer is the hidden layer. Nodes are connected to each other across layers, but no two nodes of the same layer are connected. Hence it is also known as restricted Boltzmann machine. Now that we've covered a basic MLP or multi-layer perceptron, and we've gone over the Boltzmann machine, also known as the restricted Boltzmann machine, let's talk a little bit about activation formulas. And this is a huge topic that can get really complicated, but it also is automated, so it's very simple. So you have both a complicated and a simple at the same time. So what is the role of activation functions in a neural network? Activation function decides whether a neuron should be fired or not. That's the most basic one. And that actually changes a little bit because it's either whether it's fired or not, in this case activation function, or what value should come out when it's fired. But in these models we're looking at just the Boltzmann restricted layers. So this is what causes them to fire. Either they don't or they do. It's a yes or no, true, false, all or nothing. It accepts the weighted sum of the inputs, the bias, as input to any activation function. So whatever our activation function is, it needs to have the sum of the weights times the input. So each input, if you remember on that model, and let's just go back to that model real quick. And then you always have to add a bias. And you can look at the bias if you remember from your Euclidean geometry. You draw a straight line. Formula for that line has a y coordinate at the end. It's always cx plus m or something like that, where m is where it crosses the y coordinates if you're doing a straight line. With these weights, it's very similar, but a lot of times we just add it in as its own weight. We take it as a node of a one value coming in, and then we compute its new weight, and that's how we compute that bias, just like we compute all the other weights coming in. The node which gets fired depends on the y value, and then we have a step function. And the step function, this is where, remember I said it's going to get complicated and simple all at the same time? We have a lot of different step functions. We have the sigmoid function, we have just a standard step function, we have the ReLU, it's pronounced like ray, the ray from the sun, and lu, like a name, so ReLU function. And we have the tangent h function. And if you look at these, they all have something similar. They all either force it to be one value or the other. They force it to be, in the case of the first three, a 0 or a 1, and in the last one, it's either a -1 or a 1. And you can easily convert that to a 0, 1, yes, no, true, false. And on this, one of the most common ones is the step function itself, because there is no middle value. There is no discrepancy that says, well, I'm not quite sure. But as you get into different models, probably the most commonly used, it used to be the sigmoid was most commonly used, but I see the ReLU used more often. Really, depending on what you're doing, you just have to play with these and find out which one works best, depending on the data in your output. The reason to have a non-0-1 answer or something kind of in the middle is when you're looking at this and it's coming out, you can actually process that middle ground as part of the answer into another neural network. So it might be that the ReLU function says, hey, this is only a 0.6, not a 1. And even though the 1 is what's going into the next neural network or the next hidden layer as an input, the 0.6 value might also be going in there to let you know, hey, this is not a straight up 1 or straight up 0, it's someplace in the middle. This is a little uncertain what's coming out here. So it's a very powerful tool. But in the basic neural network, you usually just use the step function. It's yes or no. Let's take a big step back and take a kind of an overview. The next function is what is a cost function that we're going to cover. This is so important because this is your end result that you're going to do over and over again and use to decide whether the model is working or not, whether you need to try a different step function, whether you need to try a different activation, whether you need to try a fully different model used. So what is the cost function? Cost function is a measure to evaluate how good your model's performance is. It is also referred as loss or error, used to compute the error of the output layer during backpropagation. There's our backpropagation where we're training our model. That's one of our key words. Mean squared error is an example of a popular cost function. And so here we have the cost function c equals half of y minus y predicted, and then you square that. So the first thing is, real quick, if you haven't done statistics, this is not a percentage. It's not a percentage of how accurate it is. It's just a measurement of the error. And we take that error if we're training it, and we push that error backwards through the neural network, and we use that through the different training functions, depending on what model you're using, to train the neural network. So when you deploy the network, you're usually done training it, because it takes a lot of computational force to train it. This is a very simple model. And so you deploy the trained one, but we want to know how your error is. And so how do we do that? Well, you split your data. Part of your data is for training, and part of your data is for testing, and then we can also test the error on there. So it's very important. And then we're going to go one more step on this. We got to look at both the local and the global setup. It might work great to test your data on what you have on your computer, but that's different than in the field. So when we're talking about all these different tests in the error test, as far as your loss, you want to make sure that you're in a closed environment when you do your initial testing, but you also want to open that up and make sure you follow up with the testing on the larger scale of data, because it will change. It might not fit the larger scale. There might be something in there in the way you brought the data in specifically, or the data group you used, or any of those could cause an error. So it's very important to remember that we're looking at both the local and the global context of our error. And just one other side note on a lot of the newer models of neural networks, by comparing the error we get on the data, our training data, with a portion of the test data, we can actually figure out how good the model is, whether it's overfitted or not. We'll go into that a little bit more as we go into some of the different models. So we have our output. We're able to figure out the error on it based on the square means usually, although there's other functions used. So we want to talk about what is gradient descent, another vocabulary word. Gradient descent is an optimization algorithm to minimize the cost function or to minimize the error. Aim is to find the local or global minima of a function. Determine the direction the model should take to reduce the error. So, as we're looking at this, we have our squared error that we just figured out based on the cost function. It says, how bad is my model fitting the data I just put through it? And then we want to reduce that error. So how do you figure out what direction to do that in? Well, it could be that you're looking at just that line of data coming in, so that would be a local minima. We want to know the error of that particular setup coming in. And then you have your global minima. We want to minimize it based on the overall data we're putting through it. And with this, we can figure out the global minimum cost. We want to take all those local minimum costs of each piece of data coming in and figure out the global one. How are we going to adjust this model to fit all the data? We don't want it to be biased just on 3 or 4 lines of data coming in. We want it to kind of extrapolate a general answer for all the data coming in. And this, of course, we mentioned it briefly about back propagation. This is where it really comes in handy, is training our model. Neural network technique to minimize the cost function helps to improve the performance of the network, back propagates the error, and updates the weights to reduce the error. So as you can see here is a very nice depiction of a back propagation. We have our predicted y coming out, and then we have, since it's a training set, we already know the answer, and the answer comes back, and based on, in case of the square means was one of the functions we looked at, one of the activation functions based on cost function. That cost function then, depending on what you choose for your back propagation method, and there's a number of them, will change the weights. It will change the weight going to each of one of those nodes in the hidden layer, and then based upon the error that's still being carried back, it'll change the weights going to the next hidden layer. And then it computes an error level on that and sends that back up. And you're going to say, well, if it computes the error into the first hidden layer and fixes it, why would it stop there? Well, remember, we don't want to create a biased neural network. So we only make small adjustments on these weights. We don't make a big adjustment that changes everything right off the bat. So no matter how far back you go, you're always going to have a small amount of error, and that's still going to continue to go all the way back up the hidden layers. For right now, focus on the back propagation, is taking that error and moving it backwards on the neural network to change the weights and help program it so that it'll have the correct answers. So far, we've been talking about forward propagation neural networks. Everything goes forwards, goes left to right. But let's take a little detour and let's see what is the difference between a feed-forward neural network and a recurrent neural network. Now this is in the function, not when we're training it using the back propagation. So you've got new information coming in and you want to get the answer. And there's a couple different networks out there, and we want to know, we have a feed-forward neural network and we have a new vocabulary term, recurrent neural network. A feed-forward neural network. Signals travel in one direction from input to output. No feedback loops. Considers only the current input. Cannot memorize previous inputs. One example of one of these feed-forward neural networks, and we've covered a number of them, but one of the ones that has a big highlight nowadays is the CNN, a convolutional neural network. TensorFlow, the one put out by Google, is probably most known for their CNN, where the information goes forward. It first takes a picture, splits it apart, goes through the individual pixels on the picture so it picks up a different reading, then calculates based on that, goes into a regular feed-forward neural network, and then gives your categorization on there. Now, we're not covering the CNN today, but we do have a video out that you can look up on YouTube, put out by Simplilearn, the Convolutional Neural Network. Wonderful tutorial. Check that out and learn a lot more about the Convolutional Neural Network. But you do need to know that the CNN is a forward propagation neural network only. So it's only moving in one direction. So we want to look at a recurrent neural network. Signals travel in both directions, making it a looped network. Considers the current input along with the previous received inputs for generating the output of a layer. Has the ability to memorize past data due to its internal memory. And you can see they have a nice image here. We have our input, and for some reason they always do the recurrent neural network in reverse from bottom up in the images. Kind of a standard, although I'm not sure why. Your X goes into your hidden layer, and your hidden layer, the answer for part of the answer from that it generates feeds back into the hidden layer. So now you have an input of both X and part of the hidden layer, and then that feeds into your output. Now if we go back to the forward, let me just go back a slide, and we're looking at our forward propagation network. One of the tricks you can do to use just a forward propagation network is if you're in a what they call a time sequence. That's a good term to remember, or a time series, meaning that it's sequential data. Each term comes after the other. You can trick this by creating your input nodes as with the history. So if you know that you have values 1, 5, and 7 going in, and you know what the output is from what those outputs are, you can expand the input to include the history input. That's one of the ways to trick a forward propagation network into looking at that. But when you do it with a recurrent neural network, you let the hidden layer do that for you. It sends that data and reprocesses it back into itself. What are some of the applications of recurrent neural network? The RNN can be used for sentiment analysis and text mining. Getting up early in the morning is good for health. And it's a positive sentiment. One of the catches you really want to look at this when you're looking at the language is that I could switch this around and totally negate the meaning of what I'm doing, so it would no longer be positive. So when you're looking at a sentence, knowing the order of the words is as important as the meaning of the words. You can't just count how many good words there are versus bad words to get a positive sentiment. You now have to know what they're addressing. And there's lots of other different uses. Kids are playing football, or soccer as we call it in the US. RN can help you caption an image. So based on previous information coming in, it refeeds that back in and you have a image setter. And then time series problems like predicting the prices of stocks in a month or quarter or sale of products can be solved using an RNN. And this is a really good example. You have whatever your stocks were doing earlier this month will have a huge effect on what they're doing today if you're investing. So having an RNN model, a recurrent neural network, feeding into itself what was happening previously allows it to take that model and program in that whole series without having to put in a month at a time of data. You can only put in one day at a time, but if you keep them in order, it will look back and say, oh, this is because of what happened yesterday. I need some information from that, and I'm going to use that to help predict today's, and so on and so on. We're going to go back to our activation functions. Remember I told you ReLU is one of the most common functions used? So let's talk a little bit more about ReLU and also softmax. Softmax is an activation function that generates the output between 0 and 1. It divides each output such that the total sum of the outputs is equal to 1. It is often used in the output layers. Softmax L of the n equals e to L of the n over the absolute value of e to the L. So what does this function mean? I mean, what is actually going on here? So we have our output nodes, and our output nodes are giving us, let's say they give us 1.2, 0.9, and 0.4. As a human being, I look at that and I say, well, the greatest value is 1.2, so whatever category that is, if you have 3 different categories, maybe you're not just doing if it's a cat or it's a dog or, let's say it's a cow. Maybe we had cats and dogs earlier. Why the cats and dogs are hanging out with a cow, I don't know. But we have a value, and it might say 1.2 is a cat, 0.9 is the dog, and 0.4 is a cow. For some reason, it thinks that there's a chance of it being any one of these 3 items, and that's how it comes out of the output layer. Well, as a human, I can look at 1.2 and say this is definitely what it is. It's definitely a cat or whatever it is. Maybe it's looking at different kinds of cars. Might be a better, whether it's a car, truck, or a motorcycle. Maybe that'd be a better example. Well, from a computer standpoint, that might be a little confusing because they're just numbers waving at us. And so with the softmax, we want all those numbers to always add up to 1. So when I add 3 numbers together, I want the final output to be 1 on there. And so it goes through this formula, changes each of these numbers. In this case, it changes them to 0.46, 0.34, and 0.20. They all add up to 1. And that's a lot easier to register because it's very set. It's a set output. It's never going to be more than 1. It's never going to be less than 0. And so you can see here that there's probably a pretty high chance that it's the first one. So as a human being, we have no problem knowing that. But this output can then also go into, say, another input. So it might be an automated car that's picking up images, and it says that image in front of us is probably a big truck. We should deal with it like it's a big truck. It's probably not a motorcycle, or whatever those categories are. That's the softmax part of it. But now we have the ReLU. Well, where's the ReLU coming from? Well, the ReLU is what's generating the 1.2 and the 0.9 and the 0.4. And so if you remember, our ReLU stands for Rectified Linear Unit and is the most widely used activation function. We looked at a number of different activation functions, including tangent H, the step function. I remember I said the step function is really used if that's what your actual output is, because then you know it's a 0 or 1. But the ReLU, if you have that as your output, you now have a discrepancy in there, and if that's going into another neural network or another process, having that discrepancy is really important. And it gives an output of x if x is positive and 0 otherwise. So it says my x value is going to be somewhere between 0 or 1. And then the usually, unless it's really uncertain, the output's usually a 1 or 0. And then you have that little piece of uncertainty there that you can send forward to another network, or you can look at to know that there's uncertainty involved. And is often used in the hidden layers. This is what's coming out of the hidden layers into the output layer usually. Or as we referenced the Convolutional Neural Network, the CNN, which you'd have to go to another video to review, the ReLU is the most common used for convolutional part of that network. It has a bunch of little pieces that are very simplified, looking at all the different images or different sections of the map, and the ReLU works really good for that. And like I said, there's other formulas used, but this is the most common one, and you'll see that in the hidden layers going maybe between one layer and the next layer. So just a quick recap, we have our softmax, which means that if you have numerous categories, only one of them is going to be picked, but you also want to have some value attached to it, how well it picked it. And you put that between 0 and 1, so it's very standardized. So we have our softmax. We looked at that. Let's go back 1. We looked at that here, where it transforms the numbers. And then we have our ReLU function, which takes the information and the summation and puts it between a 0 and a 1, where it's either clearly a 0 or, depending on how confident our model is, it'll go between the 0 and 1 value. What are hyperparameters? Oh, this is a great interview question. Hyperparameters. When you are doing neural networks, this is what you're playing with most of the time once you've gotten the data formatted correctly. A hyperparameter is a parameter whose value is set before the learning process begins, determines how a network is trained and the structure of the network. This includes things like the number of hidden units. How many hidden layers are you going to have, and how many nodes in each layer? Learning rate. Learning rate is usually multiplied once you've figured out the error and how much you want to change the weights. We talked about, or I mentioned it early just briefly, you don't want to just make a huge change. Otherwise, you're going to have a biased model. So you only take some little incremental changes. And that's what the learning rate is those small incremental changes. Epochs. How many times are you going to go through all the data in your training set? So one epoch is one trip through all the data. And there's a lot of other things depending on which model you're working with and which programming script you're working with. Like the Python sklearn package will have it slightly different than, say, Google's TensorFlow package, which will be a little bit different than the Spark machine learning package. So these are just some examples of the hyperparameters. And so you see in here we have a nice image of our data coming in, and we train our model, then we do a comparison to see how good our model is, and then we go back and we say, hey, this model's pretty good, but it's biased. So then we send it back and we change our hyperparameters to see if we can get an unbiased model, or we can have a better prediction on it that matches our data closer. What will happen if learning rate is set too low or too high? We have a nice couple graphs here. We have one over here that says the learning rate set too low. You can see that it slowly works its way down the curve. And on the right, you can see a learning rate set too high. It's just bouncing back and forth. When your learning rate is too low, that's what we studied at 2 slides ago, that's what the learning rate was. Training of the model will progress very slowly as we are making very tiny updates to the weights. We'll take many updates before reaching the minimum point. So I just mentioned epoch, going through all the data. You might have to go through all the data 1,000 times instead of 500 times for it to train. Learning rate too high causes undesirable divergent behavior to the loss function due to drastic updates in weights. At times it may fail to converge or even diverge. So if you have your learning rate set too high and it's training too quickly, maybe you'll get lucky and it trains after one epoch run, but a lot of times it might never be able to train because the weights are changing too fast. They flip back and forth too easy. And you see down here we've introduced 2 new terms, converge and diverge. Converge means that our model has reached a point where it's able to give a fairly good answer for all the data we put in. All those weights have adjusted and it's minimized the error. Diverge means that the data is so chaotic that it can never manage to train to that data. The data is just too chaotic for it to train. So we have 2 new words there, converge and diverge are important to know also. What is dropout and batch normalization? Dropout is a technique of dropping out hidden and visible units of a network randomly to prevent overfitting of data. It doubles the number of iterations needed to converge the network. So here we have our standard neural network, and then after applying dropout. Now it doesn't mean we actually delete the node. The node is still there, and we're still going to use that node. What it means is that we're only going to work with a few of the nodes. A lot of times, I think the most common one right now used is 20%. So you'll drop out 20% of the nodes when you do your training. You reverse propagate your data, and then you'll randomly pick another 20 nodes the next time you go through an epoch data training. So each time you go through one epoch, you will randomly pick 20 of those nodes not to mess with. And this allows for less overfitting of the data. So by randomly doing this, you create some, I guess it just kind of pulls some nodes off to the sides and says we're going to handle the data later on so we don't overfit. Batch normalization is a technique to improve the performance and stability of neural network. The idea is to normalize the inputs in every layer so that they have mean output and activation of 0 and standard deviation of 1. This question covers a lot of different things, which is great. It's a great interview question because it pulls in that you have to understand what the mean value is. So a mean output activation of 0, that means our average activation is 0. So when you normalize it, remember usually we're going between -1 and 1 on a lot of these. It's a very standard setup. So you have to be very aware that this is your mean output activation of 0. And then we have our standard deviation of 1. So we want to keep our error down to just a 1 value. The benefits of this doing a batch normalization is it provides regularization, it trains faster, higher learning rates, and weights are easier to initialize. What is the difference between batch gradient descent and stochastic gradient descent? Batch gradient descent. Batch gradient computes the gradient using the entire data set. It takes time to converge because the volume of data is huge and weights update slowly. So you can look at the batch as, a lot of times if you're using big data, batch the data in, but you still go through a full epoch. You still go through all the data on there. So batch gradient descent means you're going to use it to fit all the data and look for a convergence there. Stochastic gradient descent. Stochastic gradient computes the gradient using a single sample. It converges much faster than batch gradient because it updates weight more frequently. Explain overfitting and underfitting and how to combat them. Overfitting happens when a model learns the details and noise in the training data to the degree that it adversely impacts the execution of the model on the new information. It is more likely to occur with nonlinear models that have more flexibility when learning a target function. An example of this would be if you're looking at, say, cars and trucks and motorcycles, it might only recognize trucks that have a certain box-like shape. It might not be able to notice a flatbed truck unless it's only a specific kind of flatbed truck or only Ford trucks, because that's what it saw on the training set. This means that your model performs great on your trained data and great on maybe a small test amount of data, but when you go to use it in the real world, it leaves out a lot and is not very functional outside of your small area, your small laboratory data coming in. Underfitting, doing the opposite when you underfit your data. Underfitting alludes to a model that is neither well trained on training data nor can generalize to new information. Usually happens when there is less and improper data to train a model, has a poor performance and accuracy. So if you're using underfitted data and you generate a model and you distribute that in a commercial zone, you'll have a lot of people unhappy with you because it's not going to give them very good answers. So we've explained overfitting and underfitting, so now we want to ask how to combat them. Combating overfitting and underfitting. Resampling the data to estimate the model accuracy, k-fold cross-validation. Having a validation data set to validate the model. So when we do the resampling, we're randomly going to be picking out data, and we'll run it a few times to see how that works, depending on our random data and how we sample the data to generate our model. And then we want to go ahead and validate the data set by having our training data and then keeping some data on the side, testing data to validate it. How are weights initialized in a network? Initializing all weights to 0. All the weights are set to 0. This makes your model similar to a linear model. So if you have linear data coming in, doing a basic setup like that might work. All the neurons in every layer perform the same operation given the same output and making the deep net useless. Right there is a key word. It's going to be useless if you initialize everything to 0. At that point, be looking into some other machine learning tools. Initializing all weights randomly. Here the weights are assigned randomly by initializing them very close to 0. It gives better accuracy to the model since every neuron performs different computations. And here we have the weights are set randomly. We have our input layer, the hidden layers, and the output layer. And W equals NP random, random N. Layer size L minus 1. This is the most commonly used, is to randomly generate your weights. What are the different layers in CNN, Convolutional Neural Network? First is the convolutional layer that performs a convolutional operation. We have our other video out if you want to explore that more, so we can go into detail exactly how the convolutional layer works in the CNN as far as creating a number of smaller picture windows that go over the data. The second step is as a ReLU layer. ReLU brings nonlinearity to the network and converts all the negative pixels to 0. Output is rectified feature map. So it goes into a mapping feature there. Pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. So we have all our ReLU layer, which is pulling all these little maps out of our convolutional layer. It's taking that picture and creating little tiny neural networks to look at different parts of the picture. Then we need to pool it together. And then finally, the fully connected layer. So we flatten our pooling layer out, and we have a fully connected layer recognizes and classifies the objects in the image. And that's actually your forward propagation, reverse propagation training model, usually. I mean, there's a number of different models out there, of course. What is pooling in CNN and how does it work? Pooling, used to reduce the spatial dimensions of a CNN, performs downsampling operation to reduce the dimensionality, creates a pooled feature map by sliding a filter matrix over the input matrix. I mentioned that briefly on the previous slide. It's important to know that you have, if you see here, they have a rectified feature map. And so each one of those colors, like the yellow color, that might be one of a smaller little neural network using the ReLU. It'll just kind of go over the main picture and look at all the different areas on the main picture. So you might step 1, 2, 3, 4 spaces. And then you have another one that's also looking at features. And it has a 2, 7, 8, 5. Each one of those is a map. So it might be, the first one might be a map looking for cat ears, and the second one looking for human eyes. When it does this, you then have this rectified feature map looking at these different features. And the max pooling with a 2x2 filters and a stride of 2. Stride means instead of skipping every pixel, you're going to go every 2 pixels. You take the maximum values. And you can see over here, when we look at a pooled feature map, one of the features says, hey, I had a max value of 8, so somewhere in here we saw a human eye labeled as 8, pretty high label. And maybe 7 was a human hand, and maybe 4 was cat whiskers, or something that we thought might be cat whiskers. 4 is kind of a low number in this particular case compared to the other ones. So you have your full pooled feature map. You can see the process here as we have our stepping. We look for the max value, and then we create a pooled feature map of the maxed values. How does a LSTM network work? And that's long short-term memory. So the first thing to know is that an LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. We did look at the RNN briefly, talked about how the hidden layer feeds back into itself. With the LSTM, it has a much more complicated feedback, and you can see here we have the hidden layer of t-1, and the hidden layer, that's what the H stands for, hidden layer of t, and the formula is going in. As we can see here, we have the hidden layers. We have t-1 and then h of t, where t stands for time. So this is a series. Remember, we're working with series, and we want to remember the past. And you can see you have your input of t, and that might be a frame in a video. As a frame comes in, they usually use in this one the tangent h activation formula, but you also see that it goes through a couple other formulas, the omega formula. And so when it combines these, that then goes into the next layer, your next hidden layer. That then goes into the data that's submitted to the next input. So you have your x of t plus 1. So when you have that coming in, then you have your h value that's coming forward from the last process. And depending on how many of these omega structures you put in there, depends on how long-term the memory gets. So it's important to remember this is more for your long-term recurrent neural networks. The 3 steps in an LSTM. Step 1 decides what to forget and what to remember. Step 2 selectively updates cell state values. So based on what we want to remember and forget, we want to update those cell values. And then decides what part of the current state make it to the output. So now we have to also have an output on there. What are vanishing and exploding gradients? This is a great question that affects all our neural networks. While training an RNN, your slope can become either too small or too large, and this makes the training difficult. When the slope is too small, the problem is known as vanishing gradient. So our slope, we have our change in x and our change in y. When the slope decreases gradually to a very small value, sometimes negative, and makes training difficult. When the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. The slope grows exponentially. You can see a nice graph of that here. Issues in gradient problem: long training time, poor performance, and low accuracy. What is the difference between epoch, batch, and iteration in deep learning? Epoch. An epoch represents one iteration over the entire data set. So that's everything you're going to go ahead and put into that training model. Batch. We cannot pass the entire data set into the neural network at once, so we divide the data set into a number of batches. And then iteration. If we have 10,000 images as data and a batch size of 200, then the epoch should run 10,000 times over 200. So that means we have our total number over the 200 equals 50 iterations. So in each epoch, we're running over all the data set, we're going to have 50 iterations. And each of those iterations includes a batch of 200 images in this case. Why TensorFlow is the most preferred library in deep learning? Well, first, TensorFlow provides both C++ and Python APIs that makes it easier to work on. Has a faster compilation time than other deep learning libraries like Keras and Torch. TensorFlow supports both CPUs and GPUs computing devices. So right now TensorFlow is at the top of the market because it's so easy to use for both programmer side and for hardware side and for the speed of getting something up and running. What do you mean by tensor in TensorFlow? Tensor is a mathematical object represented as arrays of higher dimension. These arrays of data with different dimensions and ranks that are fed as input to the neural network are called tensors. And you can see here we have a tensor of dimensions 5, 4. So it's a two-dimensional tensor coming in. You can look at an image like this, that each one of those pixels is a different value if it's a black and white. So it might be 0 and 1s, and then each one represents a black and white image. In a color photo, you might either find a different value system, or you might have a tensor value that has the XY coordinates as we see here, plus the colors. So you might have 3 more different dimensions for the 3 different images, the red, the blue, and the yellow coming in. And even as you go from one layer or one one tensor to the next, these layers might change. We might flatten them. We might bring in numerous, in the case of the convergence neural network, we have all those smaller different mappings of features that come in. So each one of those layers coming through is a tensor if it has multiple dimensions coming in and weights attached to it. What are the programming elements in TensorFlow? Well, we have our constants. Constants are parameters whose value does not change. To define a constant, we use tf.constant command. Example, a equals tf.constant 2.0 tf_float 32. So it's a tensor float value of 32. B equals tf constant 3.0. Print AB. If we did a print of AB, we'd have tf.constant, and then of course B is that instance of it. Variables. Variables allow us to add new trainable parameters to graph. To define a variable, we use tf.variable command and initialize them before running the graph in session. Example, w equals tf variable 0.3 dtype tf_float 32, or b equals the tf variable -3, dtype float 32. Placeholders. Placeholders allow us to feed data to a TensorFlow model from outside a model. It permits a value to be assigned later. To define a placeholder, we use tf_placeholder command. Example, a equals tf placeholder, b equals a times 2. With the tf session as SESS, result equals session run b, feed dictionary equals a 3.0, print result. So we have a nice example there of a placeholder. Session. A session is run to evaluate the nodes. This is called as the TensorFlow runtime. So for example, you have a equals tf constant 2.0, b equals tf constant 4.0, c equals a plus b. And at this point, you'd go ahead and create a session equals tf session, and then you could evaluate the tensor c, print session run c. That would input C as an input into your session. What do you understand by a computational graph? Everything in TensorFlow is based on creating a computational graph. It has a network of nodes where each node performs an operation. Nodes represent mathematical operation and edges represent tensors. Since data flows in a form of a graph, it is also called a data flow graph. And we have a nice visual of this graph, or graphic image of a computational graph. And you can see here we have our input nodes, our add, multiply nodes, and our multiply node at the end. And then we have the edges where the data flows. So we have from A going to C, A going to D. You can see we have a 2 flowing, 4 flowing. Explain generative adversarial network along with an example. Suppose there is a wine shop that purchases wine from dealers, which they will resell later. So we have our dealer going to the wine, our shop owner that then sells it for a profit. But there are some malefactor dealers who sell fake wine. In this case, the shop owner should be able to distinguish between fake and authentic wine. The forger will try different techniques to sell fake wine and make sure certain techniques go past the shop owner's check. So here's our forger, fake wine, shop owner. The shop owner would probably get some feedback from the wine experts that some of the wine is not original. The owner would have to improve how he determines whether a wine is fake or authentic. Goal of forger, to create wines that are indistinguishable from the authentic ones. Goal of shop owner, to accurately tell if the wine is real or not. There are two main components of generative adversarial network. And we'll refer to it as a noise vector coming in, where we have our forger who's going to generate fake wine, and then we have our real authentic wine, and of course our shop owner who has to figure out whether it's real or fake. The generator is a CNN that keeps producing images that are closer in appearance to the real images, while the discriminator tries to determine the difference between real and fake images. The ultimate aim is to make the discriminator learn to identify real and fake images. What is an autoencoder? The network is trained to reconstruct its inputs. It is a neural network that has 3 layers. Here the input neurons are equal to the output neuron. The network's target outside is same as the input. It uses dimensionality reduction to restructure the input. Input image comes in, we have our Latin space representation, and then it goes back out reconstructing the image. It works by compressing the input to a Latin space representation and then reconstructing the output from this representation. What is bagging and boosting? Bagging and boosting are ensemble techniques where the idea is to train multiple models using the same learning algorithm and then take a call. So we have in here where we're bagging, we take a data set and we split it. We're going to have our training data and our test data. Very standard thing to do. Then we're going to randomly select data into the bags and train your model separately. So we might have bag 1, model 1, bag 2, model 2, bag 3, model 3, and so on. In boosting, the emphasis is to select the data points which give wrong output in order to improve the accuracy. So in boosting, we have our data set. Again, we split it to test data and train data. And we'll take bag 1 and we'll train the model. Data points with wrong predictions then go into bag 2, and we then train that model and repeat.
That's a wrap on a deep learning full course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply you as soon as possible. Thank you and keep learning with Simplilearn.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.